Machine Learning for Business Analytics, Galit Shmueli. Shmueli, Bruce, Gedek, and Patel's Machine Learning for Business Analytics, Second Python Edition, 2025, is the applied handbook of the analyst trade, a practice-first tour of the whole predictive toolkit, from the first, what does the business actually want question to the deployment that keeps silently scoring in production. The book's wager is that machine learning is not a bag of algorithms, but a discipline with a spine, data partitioned and never reused, performance judged on holdout records rather than fitted ones, and every method measured by what it predicts, not by how elegant it is. Across 8 parts and 24 chapters, the text works the full arc, preliminaries and the supervised/unsupervised distinction, visualization and dimension reduction, performance evaluation, the prediction and classification methods, regression, nearest neighbors, naive Bayes, trees, logistic regression, neural nets, discriminant analysis, ensembles, experiments and uplift and reinforcement learning, the unsupervised mining of relationships, forecasting, network and text analytics, responsible data science and generative AI, and a closing suite of cases. This examination follows that arc in the author's own register. Plain-spoken, problem first, acutely aware of overfitting and its costs, and insistent that every analytic choice be justified against the business goal it serves. Abstract. Machine Learning for Business Analytics, Second Python Edition, 2025, is the applied handbook of the analyst trade, a practice-first tour of the whole predictive toolkit, written for MBA and data science courses, judging every method by what it predicts on data it has never seen rather than by how elegant it is. Across 8 parts and 24 chapters, the text works the full arc, preliminaries and the supervised/unsupervised divide, data visualization and dimension reduction, performance evaluation on the holdout set, the supervised methods of prediction and classification, multiple linear regression, nearest neighbors, naive Bayes, classification and regression trees, logistic regression, neural networks and deep learning, discriminant analysis, ensembles, and AutoML, experiments, uplift and reinforcement learning, association rules and collaborative filtering, clustering, time series forecasting, social network and text analytics, responsible data science, and generative AI, closing with a suite of 10 real cases. This deep examination follows that arc in the author's own register. Plain-spoken, problem first, acutely aware of overfitting and its costs, and insistent that every analytic choice be justified against the business goal it serves. Executive summary. Central thesis. The book's governing idea is that machine learning is a discipline with a spine, not a bag of algorithms. A model is judged by its performance on holdout data, records it has never seen. And the constant enemy is overfitting, the mistake of modeling a sample's noise as if it were signal. Around that doctrine, the authors organize the entire predictive and analytic toolkit, from regression through trees, neural nets, ensembles, clustering, time series, and text and network analytics. Each method presented problem first, with its worked business example, its plain language coefficients, and its limits stated without embarrassment. The deeper claim, carried through the closing chapters, is that the same discipline extends to the consequences of the work. Analytics guides interventions on real people and responsible data science, auditing for the unintentional harm that overall accuracy metrics can conceal, is a continuation of the modeling craft, not a separate duty. Foundational observations. The holdout discipline is load-bearing, not ceremony. Training, validation, and holdout sets each play a distinct role, and using data to choose a model degrades that same data as evidence. Validation selected performance is optimistic, and only a never-touched holdout set gives an unbiased estimate of deployment performance, which is why overfitting is detectable by comparing training against holdout error. Prediction is not goodness of fit. Classical statistics asks how well a model fits the data it was trained on. Machine learning asks how well it predicts new records. The same honest metrics, MAPE, RMSE on the holdout, the confusion matrix, lift, and the same benchmark discipline, the naive average, the naive majority rule, the naive forecast, carry through every chapter. The problem determines the method. profiling versus prediction, explanatory versus predictive modeling, global versus local patterns, precision versus recall, classification versus ranking. Each apparent opposition is resolved by asking what decision the analysis actually serves, so method choice is never a matter of default. Every method has its honest limit. The linear trend that misses the U-shape, the regression tree that cannot draw a diagonal, the neural net that overtrains, the nearest neighbor that is too slow for real-time prediction, the naive Bayes whose propensities are biased, the EUC that hides crossed ROC curves. The book states these limits plainly, and the analysis reads them into the story. The unsupervised chapters complete the toolkit. Association rules and collaborative filtering discover relationships among purchases and people, clustering segments markets by distance, and all three work within the same disciplines of normalization, benchmarking, and validation as their supervised counterparts. Forecasting turns time into data. Time series are dissected into level, trend, seasonality, and noise, judged global or local, partitioned chronologically rather than randomly, benchmarked against the naive forecast, and modeled by regression-based or data-driven methods whose strengths and failures the authors show side by side on the same Amtrak series. The digital age methods and the ethics extend the same craft. Social network metrics feed ordinary classifiers. Text becomes a term document matrix. Responsible data science audits model for the harm overall accuracy can hide, as the Compass example shows. And generative AI, for all its novelty, remains the deep learning of earlier chapters, with the same stakes amplified. Significance and recommendation. This is a book that teaches analytics by doing business, and it is recommended to anyone who wants to understand, rather than merely call, the predictive methods that run modern firms. Students should read it as the practical companion to a first analytics or data mining course, working parts 1 through 3 for the framework, then the methods of parts 4 and V as the business question warrants, and part 6 for forecasting. The cases of part 8 are where the lessons become skills. Practitioners returning to the field will find the interwoven cautions, overfitting, target leakage, proxy discrimination, the short shelf life of models, worth the reread. The book is not a survey of research frontiers, but a working manual. If it reads like a practitioner teaching a discipline rather than a theorist declaiming one, that is exactly the register this examination has preserved. Part 1. Preliminaries. Chapter 1. Introduction. What is business analytics? Business analytics, or more generically analytics, is the practice and art of bringing quantitative data to bear on decision-making, and the term means different things to different organizations. A British tabloid considered itself to be doing analytics by testing which images on its homepage produced more hits, cats, dogs, or monkeys. At the other extreme, the Washington Post, tracking readers by time, location, and subscription, can aim an aircraft carrier advertisement at the handful of legislators who will vote on the Pentagon's budget. Between these poles lies a continuum of methods, much of it only counting, rule-checking, and basic arithmetic. The next level, business intelligence, is visualization and reporting for understanding what happened and what is happening, evolved from static reports into interactive dashboards. Business analytics today typically includes BI alongside the models and algorithms used to explore data, quantify relationships, and predict new records, with the payoff everywhere, from credit scores built on prior repayment data to the IRS being 25 times more likely to find evasion when enforcement was model-guided. The A/B test familiar to marketers extends the toolkit to pricing. Orbitz could charge Mac users more for hotels, Staples more for staplers to distant customers. Business analytics, BA, the practice and art of bringing quantitative data to bear on decision-making, spanning everything from tabloid web page testing to targeted defense advertising. Business intelligence, BI, the layer of analytics concerned with visualization and reporting, understanding what happened and what is happening through charts, tables, and interactive dashboards. A/B testing, a statistical experiment comparing treatments prominent in pricing and marketing decisions. Quote, Successful use of analytics and machine learning requires both an understanding of the business context, where value is to be captured, and an understanding of exactly what the machine learning methods do. What is machine learning? Strictly, machine learning, or data mining, the older term, names the methods that go beyond counts, descriptive techniques, reporting, and business rules, the methods that inform decision-making, often automatically at the individual level. Instead of what is the relationship between advertising and sales, we ask what specific advertisement or recommended product should be shown to a given online shopper at this moment. Instead of an average customer, we cluster customers into personas that receive different treatment. Big data accelerated these methods because their power and automaticity let them cope with huge amounts of data and extract value from it. Machine learning, data mining, the analytics methods that go beyond counts, reporting, and business rules to inform decisions, typically predicting at the individual level. Personas, customer clusters defined by clustering, so each prospect can be assigned a tailored marketing treatment. Machine learning, AI, and related terms. The vocabulary shifts beneath us. Data mining has acquired a hazy, pejorative public meaning and has largely been superseded by machine learning, joined by predictive analytics, predictive modeling, and most recently artificial intelligence. Once the general capability of a machine to act like a human, now loosely used to mean much the same as machine learning. The deeper tension is between statistics and machine learning. Classical statistics grew up when computing was difficult and data scarce, and it focuses on inference regarding an average effect. A $1 price increase will reduce average demand by 2 boxes. Machine learning, with both plentiful, focuses on predicting individual records. The predicted demand for person I given a $1 price increase is 1 box, while for person J, it is 3 boxes. Prejudict's phrase captures it. Data mining is statistics at scale and speed. Even the word inference has split, chance variation for statisticians, scoring new data for machine learners. Data mining, the older term, largely superseded by machine learning. To the public, it carries a hazy, pejorative sense of digging through personal data. Artificial intelligence, AI loosely, all the methods in this book, and the umbrella vision of machines acting like humans that they enable. Statistical model versus machine learning algorithm. Statistics applies global structure, a simple equation, to average effects. Machine learning learns local patterns to predict individual records. Prejudict's statistics at scale and speed. Quote, the general approach to machine learning is vulnerable to the danger of overfitting, where a model is fit so closely to the available sample of data that it describes not merely structural characteristics of the data, but random peculiarities as well. In engineering terms, the model is fitting the noise, not just the signal. Throughout, machine learning algorithm names methods that learn directly from data, especially local patterns, often in layered or iterative fashion, while statistical model names methods that apply global structure expressible as a simple equation. The running contrast is linear regression against K, nearest neighbors. Regression treats every record by one overall equation. K, nearest neighbors, classifies each by its few nearby records. Big data. Machine learning and big data go hand in hand. Big data is a relative term. Data are big by reference to the past and to the methods available to deal with them, and its challenge is characterized by the 4 verses: volume, velocity, variety, and veracity. The scale is best felt comparatively. A traditional study of 15 variables and 5,000 records is the size of a period, while the Walmart database is the size of a football field, leaving out unstructured social media text. The rewards match. OkCupid predicts which message content draws a response. Telenor cut turnover 37% by predicting who would leave. Allstate tripled the accuracy of predicting injury liability by adding vehicle information. Some tasks were infeasible before big data. Web search itself only came into its power once accumulated click data could surface the exact I Love Lucy episode for a query like Ricky Ricardo Little Red Riding Hood. The 4 verses: volume, velocity, variety, and veracity. the defining challenge of data that is big relative to the methods available to handle it. Unstructured text, the part of big data, social media, that does not fit the tidy rows and columns form of a traditional study. Data science. The ubiquity and value of big data gave rise to the data scientist. A mix of skills in statistics, machine learning, mathematics, programming, business, and IT, broader than any earlier analytic term, and rare to find deep in all its parts. Analyzing the analyzers describes the skill set as a T, deep in one area and shallower across the top. A useful correction: most data scientists do not spend most of their time on terabyte-sized data. That scale appears at deployment, where the challenges are mostly IT and programming. This book concentrates on the earlier piloting and prototyping phase. What methods to use with what data, how they work, their requirements and weaknesses, and how to assess their performance. Data scientist, the rare hybrid of statistics, machine learning, math, programming, business, and IT. Classically a T skill set, deep in one area and shallower across the rest. Deployment versus prototyping. Terabyte-scale data live at deployment. This book is about the earlier piloting and prototyping phase. Why are there so many different methods? Each method has advantages and disadvantages, and its usefulness depends on the dataset size, the patterns in the data, whether the data meet the method's assumptions, how noisy they are, and the goal of the analysis. To separate riding mower buyers from non-buyers on income and lot size. One method looks only for horizontal and vertical lines, another for a single diagonal line. Both can work but will not agree everywhere. It is therefore customary to apply several methods and choose the one most useful for the goal at hand. No single best method. Each technique's usefulness depends on data size, pattern types, assumptions, noise, and the goal at hand, so several methods are tried and the most useful chosen. Terminology and notation. Because data science has a hybrid parentage, practitioners use several words for the same thing. Output, target, dependent, and response all name the variable being predicted. Algorithm and model, attribute and feature, case and observation all oscillate. The book standardizes where usage is split. Holdout set for data, reserved to assess the final model on new data. Success class for the class of interest in a binary outcome, which need not be favorable, and notes the sharpest ambiguity. Sample is a collection in statistics, a single observation in machine learning. Here too sit the two distinctions that anchor the book. Supervised learning trains an algorithm on records whose output is known, so it can predict unknown outputs, while unsupervised learning seeks patterns other than the output. Target/response/outcome. The variable being predicted, called different names across the statistics and machine learning vocabularies. Supervised versus unsupervised. Supervised learning trains on records with known output. Unsupervised learning seeks patterns without an output to predict. Conditional probability P of B given A. The probability that B occurs given A has occurred. The anchor of the Bayesian chapters. Roadmaps to this book. The book orients the reader through two maps. One process-based, locating each topic in a project. The other organizing supervised and unsupervised procedures by whether the data and response are numerical or categorical. The parts form the deeper structure. Part 1 is the overview. Parts 2 and 3 cover exploration, dimension reduction, and performance evaluation. Part 4 spans the 8 supervised methods. Part 5 introduces experiments, intervention, and feedback. Part 6 mines relationships. Part 7 forecast time series. Part 8 ranges across networks, text, responsible data science, and generative AI. Part 9 closes with cases. Each chapter stands alone, but parts 1 through 3 should come first, and Chapter 17 before the other time series chapters. 2 maps. A process-based map locates each topic in a machine learning project. A data type map organizes supervised and unsupervised methods by numerical or categorical data and response. 9 parts, from preliminaries through methods, relationships, forecasting, data analytics, and cases. Readable in order, with parts 1 to 3 prerequisite for the rest. Chapter 2. Overview of the machine learning process. Introduction. Before any algorithm can be chosen, the machine learning process must be understood as a whole. A sequence that begins with a clear goal definition and ends with model deployment, passing through data collection, cleaning, pre-processing, partitioning, and evaluation along the way. The core of the book focuses on what has come to be called predictive analytics, the tasks of classification and prediction, as well as pattern discovery, which have become key elements of a business analytics function in most large firms. The chapter's working method is to lay out the steps schematically, explain the concepts behind them, and then demonstrate the whole sequence on a single worked example so that the reader sees the arc before any single technique is studied in isolation. Logistic regression, classification by modeling a categorical outcome. The user specifies predictors and form, so even small datasets suffice and scoring is cheap. 2 steps. Estimate propensities, then apply a cutoff to classify, the default 0.5 or lower for rare important events. Discriminate analysis, a classical model-based classifier used for classification and profiling across species, credit, bonds, fossils, and fingerprints. Nodes and edges. A social network is entities and their connections, the data underlying Facebook's, X's, and LinkedIn's core value. Unintentional bias. Compass is accurate overall, yet its errors harm African Americans, over-predicting their recidivism, under-predicting whites. Core ideas in machine learning. Classification is perhaps the most basic form of predictive analytics, and its shape is everywhere. The recipient of an offer can respond or not respond. An applicant for a loan can repay on time, repay late, or declare bankruptcy. A credit card transaction can be normal or fraudulent. A data packet can be benign or threatening. The common machine learning task is to examine data whose classification is unknown or lies in the future, develop rules from data where the classification is known, and apply those rules to the unknown cases. Prediction is similar except that the target is the value of a numerical variable, the amount of a purchase rather than a class. The machine learning literature sometimes uses estimation and regression for a continuous target and prediction for both. Association rules, or affinity analysis, are designed to find general associations among items in large transaction databases. What goes with what? Informing product placement, weekly promotions, or bundling in a grocery store, and even tracing which symptom is followed by which in a hospital database. Collaborative filtering, by contrast, generates what goes with what at the individual user level. It uses a user's historic purchases, ratings, browsing, or other preference-revealing behavior, together with other users' histories, to deliver personalized recommendations to users with a wide range of tastes. Classification, prediction, and, to some extent, association rules and collaborative filtering together constitute the analytical methods of predictive analytics. The term is sometimes stretched to include clustering and other pattern identification. 2 kinds of reduction prepare the data and improve performance. Data reduction consolidates a large number of records into a smaller set of homogeneous groups, clustering in the method sense, when an analyst would rather model a few groups than thousands of product types or customer records. Dimension reduction cuts the number of variables, a common initial step intended to improve predictive power, manageability, and interpretability. Exploration is one of the earliest stages of engaging with data, aimed at understanding the global landscape and detecting unusual values. It combines data cleaning and manipulation with visual discovery and hypothesis generation. Histograms and box plots for numerical variables, bar charts for categorical ones, scatter plots for pairs of numerical variables, all enhanced by color and interactive navigation. The deepest dividing line among techniques is between supervised and unsupervised learning. Supervised algorithms, classification, and prediction require data in which the outcome of interest is known, called labeled data, because the outcome for a record is often a characterization applied by a human, a document labeled relevant, an X-ray object labeled malignant. The algorithm learns from the training data the relationship between predictors and outcome. It is then applied to validation data to compare models, and if many models are tried, to a holdout sample to see how well the model finally selected will do on genuinely new records. Unsupervised algorithms operate where no outcome variable exists to predict or classify. There is nothing to learn from known outcomes, and cover association rules, dimension reduction, and clustering. The two are often used in conjunction. Clustering separates lone applicants into risk groups, and supervised algorithms are then applied separately to each group. Classification, predicting class membership, respond/not, repay/bankrupt, normal/fraud, from records whose classification is unknown or future. Prediction, estimating a numerical value rather than a class. Association rules and collaborative filtering find what goes with what at the population and individual level. Data versus dimension reduction. Clustering consolidates records into homogeneous groups. Dimension reduction cuts the number of variables to improve power, manageability, and interpretability. Quote, in some cases, the value of the outcome variable, the label, is known because it is an inherent component of the data. Weblogs will show whether a person clicked on a link or not. Bank records will show whether a loan was paid on time or not. In other cases, the value of the known outcome must be supplied by a human labeling process to accumulate enough data to train a model. In either case, the machine learning algorithm can be led astray if the quality of the supervision is poor. The quality of supervision matters. The authors trace how autocorrection cemented the spelling defiantly because too many users lazily accepted Google's a first correction rather than substituting definitely. All those acceptances taught the algorithm the wrong answer. The chapter also places generative AI in this landscape. Large language models trained on text at huge scale produce report-style text in response to a query, using supervised learning as building blocks. They are enormous, compute-hungry, and at this writing, almost exclusively the province of large internet companies, so business users are unlikely to train their own. The steps in a machine learning project. Some of the most serious errors in analytics projects come not from the algorithms, but from a poor understanding of the problem. So the chapter lays out the full sequence of steps a typical effort should follow. 1. Develop an understanding of the purpose of the project, how the stakeholder will use the results, who will be affected, whether the analysis is one-shot or ongoing. 2. Obtain the data, often by random sampling from a large database, pulling together internal and external sources. How well the sample reflects the records of interest governs generalization. Although machine learning deals with very large databases, the analysis usually needs only thousands or tens of thousands of records. 3. Explore, clean, and pre-process the data. Handle missing data, check ranges, spot outliers, review the data graphically, a matrix of scatterplots. Ensure consistency of field definitions and units, and derive new variables from existing ones. 4. Reduce the data dimension if necessary, eliminating unneeded variables, transforming variables, creating new ones, while knowing what each variable means and whether it is sensible to include it. 5. Determine the machine learning task, translating the general business question into a specific task. Classification, prediction, clustering. 6. Partition the data for supervised tasks into training, validation, and holdout sets. 7. Choose the machine learning techniques. 8. Use the algorithms to perform the task, iterating over variance and parameter settings, with validation feedback refining the parameters. 9. Interpret the results. Choose the best algorithm to deploy and test it on the holdout data, remembering that validation data used for tuning has become part of the fitting process and will underestimate deployment error. 10. Deploy the model, integrating it into operational systems and scoring new records to produce decisions and actions. These steps are encompassed in the industry standard methodology CRISP-DM, CIROS Industry Standard Process for Data Mining. CRISP-DM, the industry standard process, purpose, data, cleaning, dimension, task, partition, technique, algorithms, interpretation, deployment. Partition before modeling. Supervised tasks split data into training, validation, and holdout sets, with validation feeding tuning and holdout reserved for final assessment. Preliminary steps. The chapter's concrete work begins with how data are organized. Datasets are nearly always constructed with variables in columns and records in rows. The West Roxbury home values example has 14 variables for over 5,000 homes, the outcome typically first or last. The narrative then walks through the West Roxbury setting itself. How Zillow built its Zestimates from publicly available city tax assessment data, redirected the traditional 6% realtor commission to itself, and later faced Redfin's salaried agent competition. A simple, naive, model-less baseline would use the city's assessed values as they are, but those values miss properties and remodeling and may not reflect market values. The city data serve instead as a starting point for a model. In Python, the data are loaded into a pandas data frame. The chapter shows basic data handling, finding dimensions, viewing and slicing rows and columns, computing summary statistics, and cautions about Excel's behavior with .csv files, stripping leading zeros from zip codes, saving only display digits. The lock and iLock accessors matter. iLock excludes the end index in a slice. Lock includes it. Sampling from a database is a constant necessity, since algorithms vary in what they can handle and run faster on smaller samples. Accurate models can often be built from a few thousand records. The chapter distinguishes a random sample, oversampling, giving the rare class extra weight, as with houses with over 10 rooms, and stratified sampling grouped by a variable of interest. Oversampling rare events is treated with unusual emphasis. In direct response, advertising 1 or 2 responders per 100 records is common, and the cost of failing to identify a responder far outweighs the cost of reaching a non-responder. The danger is that, absent asymmetric costs, the highest accuracy model is the one that calls everyone a non-responder. Low misclassification rate, 0 value. Pre-processing covers the types of variables: continuous, integer, categorical, nominal or ordinal, date time, text, and their handling. Continuous variables suit most routines. The naive Bayes classifier is the prominent exception, dealing exclusively with categorical predictors. The roots of machine learning lie in categorical outcomes, while the roots of statistics lie in continuous ones. Nominal categorical variables must usually be decomposed into dummy variables. Regression models use only m-1 of m dummies because the last is implied, while nearest neighbors must use all m. The redundant one-hot encoding causes no problem there. Parsimony guides variable selection. The more variables included, the more records needed to assess relationships reliably, and models built on many variables are often less robust. The chapter offers the practical rule of thumb of roughly 10 records per predictor. Domain knowledge is repeatedly invoked. Someone who knows the business process must be consulted, because knowing what variables represent is critical for building a good model and avoiding errors and legal violations. The target leakage warning is sharp. If a predictor like shipping amount is a percentage of purchase amount, a model using it cannot predict purchase amount because the shipping figure is unknown until the transaction completes. Similarly, a model built only on approved loan applications cannot predict default at application time. In credit scoring, gender and race are legally prohibited. Outliers are values lying far from the bulk of the data, an admittedly arbitrary designation. Their purpose is to flag values needing review, and domain knowledge decides whether a misplaced decimal, a wrong reading, or a genuinely interesting anomaly explains them. Missing values, if rare, can be omitted, but with 30 variables and only 5% missing, nearly 80% of records would carry at least one missing value. So imputation, mean or median, or even a regression-based fill, is often preferable, with the honest caveat that imputation adds no information about how the variable affects the outcome. Some variables simply carry too many missing values to be useful, and a proxy or a data collection investment may be the better answer. Normalizing, subtracting the mean, and dividing by the standard deviation, producing z-scores, and risk scaling to 0-1 bring variables onto a common scale, essential for clustering, where a dollar variable in the thousands would otherwise dominate a distance measure. But normalization is an option, not an automatic feature, because sometimes we want each variable to contribute in proportion to its original scale. Data organization, variables in columns, records and rows. The outcome usually first or last. Sampling and oversampling. Random samples, weighted oversampling of rare classes, and stratified sampling keep the valuable few visible to the model. Parsimony. More variables need more records and invite overfitting. Roughly 10 records per predictor is the rule of thumb, and target leakage. Using a predictor unknowable at prediction time is the trap. Outliers and missing values. Values far from the bulk need review and domain judgment. Missing values can be omitted or imputed, with imputation adding no information. Predictive power and overfitting. The central question of supervised learning is how well a model will perform on new data, and the two concepts that answer it are generalization and overfitting. The more variables a model includes, the greater the risk of overfitting. Fitting the sample so closely that the model captures random peculiarities rather than structure. The chapter's illustration is a scatter plot of advertising against sales. A complicated function can interpolate every point with zero error, yet it is hard to believe that moving from $400 to $500 in advertising decreases revenue. The complex curve overreaches. It models chance variation and mistakes noise for signal. Adding predictors likewise sharpens performance on the data at hand, while promising disaster beyond it. A charity donation model that picks up height as predictive among 100 individuals will not travel. The danger grows as the dataset approaches the number of predictors. A very large dataset forces each predictor to earn its keep across many cases. Surprising but true. Even when a higher degree curve is known to be the right model, a lower degree function may predict better when data are thin, and overfitting can also result simply from trying many models and keeping the best fitting one. Creating partitions directly addresses overfitting. Using the same data to develop and assess a model introduces an optimism bias, because the winning model's performance comes partly from a genuinely superior model and partly from chance aspects of the data that happen to match it. A problem especially serious for structure-free techniques like trees and neural nets. Partitioning mimics deployment. Build on training data, then try the model on held-back records and measure performance. 3 partitions play distinct roles. Training partition, typically the largest, contains the data used to build the models under examination. Validation partition, used to compare models and choose the best one, and in some algorithms, trees, k-nearest neighbors, to tune parameters automatically. Holdout partition, used only at the end to assess how the chosen model performs on new data it has not seen. Why both validation and holdout? Because using validation data to choose among models reintroduces a lesser facet of overfitting, chance aspects of the validation data that happen to match the chosen model. So the chosen model's validation performance is overly optimistic. The holdout data, never seen during development, provide an unbiased estimate. When only training and validation are used, the emphasis is on finding the best model rather than knowing exactly how well it will do. Cross-validation extends partitioning for stability. The data are split into k-equal folds. The model is fit k times with each fold serving once as the validation set. And the predictions are combined, especially valuable when the sample is small and a single partition would leave too few records per side. Overfitting, fitting the sample so closely that noise is modeled as signal. A complex curve can fit perfectly yet predict badly. Optimism bias, choosing the model that fits best inflates apparent performance from chance matches. Partitioning mimics deployment by holding out data the model has not seen. 3 partitions. Training builds models, validation compares and tunes them. Holdout estimates new data performance. And probing validation many times silently overfits it. Cross-validation, fitting a model k times with each fold serving once as validation stabilizes performance estimates when samples are small. Building a predictive model. The chapter demonstrates the whole sequence, the West Roxbury example, end-to-end with multiple linear regression. Determine the purpose, predict home value for new records, obtain the data, small enough to use entire, explore, clean, pre-process, read the data dictionary, exclude tax for its circularity. The tax is a function of the assessed value we're trying to predict. Check for outliers like a 15-floor home that is really 1.5 floors. Create dummies, keeping only the 2 regression. Dummies from remodels 3 categories. Reduce the dimension, already low. Determine the task, supervise prediction. Partition into training and holdout. Choose linear regression. Fit it, and score new records. The worked output shows fitted values and residuals for training, holdout predictions, and the prediction error metrics. Mean error is small and near 0 in both cases. Predictions average about right, the errors balance, but it says nothing about error magnitude. RMSE takes the square root of the average squared error and gives the typical error in the outcome zone units. $43,000 on training, $42,700 on holdout, close enough that the model is clearly not overfitting. The lesson is general. After choosing the best model, lowest validation error, remembering that simpler is better. Test it on fresh holdout data, then deploy it, scoring new records. Predictive tasks yield predicted numerical values. Classification tasks yield classes and propensities. Worked regression walkthrough. The West Roxbury housing data show the full sequence. Purpose, data, cleaning, dimension, partition, fit, error metrics, deployment by scoring. RMSE versus mean error. Mean error reveals only bias. Errors balance. RMSE gives the typical error in the outcome zone units and exposes overfitting when holdout far exceeds training. Using Python for machine learning on a local machine. The heavy-duty analysis does not necessarily require huge data. Applying linear regression or a classification tree to a sample of 20,000 is likely to be as accurate as using the whole data set by the same principle as polling. A judicious sample of 2,000 voters estimates the population's opinion within a point or two. In most cases, the records required for each partition fit comfortably within a local machine's memory. For genuinely big data, removing unused objects and calling garbage collection can help, though it is usually unnecessary. Automating machine learning solutions. Automating machine learning, MLOps, or AI engineering, recognizes that most supervised applications aim at a model that runs continuously on new records, not a one-time analysis. The IRS, receiving hundreds of millions of returns a year, wants the fraud probability computed as part of the normal filing environment, not by pulling each return out for separate analysis. Pandora and Spotify need recommendations in real time from millions of users. The answer is a data pipeline. The algorithm is embedded in the operational setting, communicating through APIs that fix the exact predictor variables, their order, their formats, and the form of results, and governed by business rules. If no predicted fraud, continue routine processing. If fraud is predicted, alert an examiner. The work does not end at deployment. Models have a short shelf life. One leading consultant finds they rarely function effectively for more than a year. So they must be periodically checked and reevaluated, and once performance flags, it is time to return to prototype mode. The chapter grounds this in 2 examples. For Sirikvina, a Norwegian hydroelectric company supplying 7% of the country's power, an engineering checklist failed to exploit hundreds of sensors producing tens of thousands of readings a day. Elder Research built a system that predicted generator failure proactively, handling not just model fitting but sensor collection, data transformation, alerting, visualization, anomaly case management, and analyst added labels. Its tool stack, infrastructure, security, monitoring, automation, resource management, testing/debugging, data collection with a raw, immutable data store, and an analytic base table, data EDL with a verification step wired into monitoring. The modeling layer with its own model monitoring, and a delivery layer shows that the predictive models occupy only a small part of the pipeline. Uber's Michelangelo is the far-reaching counterpart, an MLOps environment for driver matching, pickup time prediction, route pricing, and delivery time estimation, supporting both batch and low-latency online processing, standardizing feature storage, and recording for each model who trained it, its configuration, its datasets, feature importances, accuracy metrics and learn parameters, with facilities to compare predictions to outcomes and alert operators when the performance margin degrades. MLOps/data pipeline, embedding the model in the operational system, with APIs fixing predictor order, format, and result rules. The IRS fraud screen and Pandora/Spotify recommendations in miniature. Model shelf life. Deployed models degrade about a year per one consultant and need periodic rechecking and reevaluation. Michelangelo and Cyril Vina. Uber's MLOps environment and Elder Research's preventive maintenance system show the model is a small piece of a much larger stack. Quote, "You should be aware, though, that most of the actual work of implementing a machine learning solution lies in the automated deployment phase. Much of this work is not in the analytic domain. Rather, it lies in the domains of databases and computer engineering to assure that detailed nuts and bolts of an automated data flow all work properly." Ethical practice in machine learning. Prior to the internet-connected era, the biggest source of big data was public interaction on the web, and social media users made an implicit deal with the companies providing services, powerful search, shopping, and social tools for free in exchange for access to user data. Since the first edition appeared in 2007, ethical issues in machine learning have received increasing attention and new rules and laws have emerged. The responsibility is twofold: for the business analytics professional to know and follow the rules, and to think about the implications and uses of the work beyond the prototyping phase. It is now common for organizations to require explicit incorporation of ethical principles and audits into machine learning and AI applications. Chapter 22 treats the subject in detail. Part 2, Data Exploration and Dimension Reduction. The implicit data deal, free powerful tools in exchange for user data, now governed by new rules and by ethical principles and audits built into AI applications. Chapter 3, Data Visualization. Uses of data visualization. A picture is worth 1,000 words. The saying captures why visualization matters. It condenses diffused verbal information into a compact, quickly understood graphical image. And for numbers, it is both a powerful tool for exploring data and an effective way to present results. Where does it sit in the machine learning process? Primarily in the pre-processing portion. Visualization supports data cleaning by finding incorrect values. A patient whose age is 999, a negative value, missing values, duplicate rows, and columns with no variation. It supports variable derivation and selection, determining which variables to include and which are redundant. Choosing bin sizes when a numerical outcome must become a yes/no decision, and combining categories during data reduction. And if the data have yet to be collected and collection is expensive, visualization on a sample can reveal which variables and metrics are worth gathering. Exploration itself is a mandatory initial step whether or not more formal analysis follows, combining free-form exploration, understanding structure, cleaning, identifying outliers, discovering initial patterns, with focused questions tied to a specific goal. Throughout, the discussion is organized by machine learning goal, distinguishing supervised from unsupervised learning, and within supervised, classification, categorical outcome, from prediction, numerical outcome. A terminological note matters. Graph in statistics has two meanings: any figure for data and the network data structure, so the chapter deliberately uses chart and plot for the visualizations. The Python ecosystem is canvassed. Matplotlib at the flexible base with Seaborn, Pandas, ggplot after the grammar of graphics, and Bokeh, and Plotly for interactive web-based plots. Pre-processing role. Visualization finds incorrect values, missing data, duplicates and invariants, and guides variable derivation, selection, and binning. Exploration goals. Free-form exploration of structure, cleaning, outliers, and patterns combines with focused questions tied to a specific modeling goal. Data examples. 2 data sets carry the chapter. The Boston housing data, census tract measurements like crime rate, pupil/teacher ratio, and the median value of owner-occupied homes, support 3 distinct tasks: predicting MEDV, numerical, classifying whether a track's homes exceed $30,000, binary category, and clustering tracks. The second, Amtrak ridership, monthly riders between January 1991 and March 2004, sets the time series forecasting task. Both recur throughout the book. Boston housing, one data set, three tasks, predict MEDV, classify high/low, cat_EV, cluster tracks. Amtrak ridership, monthly ridership sets the time series forecasting task, reused throughout the prediction chapters. Basic charts, bar charts, line charts, and scatter plots. The three most effective basic charts are the bar chart, the line chart, and the scatter plot. The most commonly used in the business world for exploration and presentation alike, pie charts remain popular, though usually ineffective. Basic charts display one or two columns of data at a time, which suits the early stage of becoming familiar with the data structure, the volume and types of variables, and missing values. The machine learning task shapes usage. Supervised learning focuses more on the outcome variable. In scatterplots, the outcome typically sits on the y-axis, while unsupervised learning prefers charts that convey relationships, such as scatterplots. Line graphs are used primarily for time series, with the time frame chosen to match the forecasting horizon. Bar charts compare a single statistic, average, count, percentage, across groups. The x-axis should hold only categorical variables, since bar order is interchangeable. The chapter's Boston examples show both uses of the bar chart. For prediction, the average MEDV against whether a tract bounds the Charles River. For classification, the percent of tracts above $30,000 by the same river variable, revealing that river-bounding tracts are far more likely to exceed $30,000. Scatter plots require two numerical variables, so a basic scatter plot cannot show the relation between a categorical outcome, cat_MEDV, and its predictors that awaits the enhancements of the next section, but it is central for prediction, MEDV against LSDAT, and useful unsupervised for studying association and spotting clusters. Before multidimensional investigation, two distribution plots matter, the box plot and the histogram, each displaying the entire distribution of a numerical variable rather than a single aggregation. Both are useful in supervised learning for choosing methods and transformations. A skewed variable may warrant a logarithmic scale when used in methods that assume normality, like linear regression or discriminant analysis. A histogram shows the frequencies of all values with connected vertical bars. A box plot encloses the middle 50% of the data, marking the median inside, with whiskers covering the rest and outliers as points. Side-by-side box plots compare distributions across subgroups, revealing not just that river-bounding tracts have a higher average MEDV, but that their whole distribution is higher. Information that identifies potentially useful predictors and suggests how to bend numerical variables. Heat maps use color to denote values, and in a machine learning context, they serve two purposes: visualizing correlation tables and visualizing missing values. A correlation heat map of 13 variables makes it easy to spot the strong and weak pairwise correlations at a glance. A missing value heat map codes missing cells and reveals patterns of missingness, variables missing nearly everywhere, clusters of rows missing many values, guiding whether to drop variables or records, impute, or take other action. Heat maps are not a replacement for precise displays, because color differences cannot be perceived accurately. They excel at scanning a large table. 3 basics. Bar charts compare a statistic across groups. Line charts show time series. Scatter plots relate two numerical variables. Outcome on the y-axis. In supervised work, the outcome typically sits on the y-axis. Basic charts can't yet encode a categorical outcomes relation to predictors. Distribution plots. Histograms and box plots display an entire distribution, flagging skew that argues for transformations and revealing separable predictors via side-by-side box plots. Heat maps, color-coded tables for correlation and missing value patterns, fast to scan, but not a replacement for precise displays. Multidimensional visualization. Basic plots can convey far richer information through features such as color, size, shape, and multiple panels, and through operations such as risk scaling, aggregation, and interactivity. The design principle is rooted in how visual perception works. The purpose is to make information more understandable, not merely to represent it in more dimensions. Three-dimensional plots are usually ineffective visualizations. Additional categorical information is best shown with hue, shape, or multiple panels. Additional numerical information with color intensity or size. Temporal information with animation. Color coding transforms the scatter plot from a prediction tool into a classification tool. A scatter plot of two numerical predictors, LSDAT against NOx, color-coded by the categorical outcome, ket_MDV, shows whether the class is separate. In prediction, color-coded scatter plots help assess whether interaction terms are needed. Is the MEDV LSDAT relationship different for tracks near the river? When a color-coded bar chart grows too crowded, multiple panels, trellising, split the observations by categorical variable and draw one small multiple per category. A bar chart of MEDV by highway accessibility broken into river/near-river panels reveals behavior hidden in the aggregate and suggests both an interaction term and condensing rare categories. The scatterplot matrix lays all pairwise scatter plots into one display. Panels below the diagonal show the plots. The diagonal shows each variable's distribution, and the cells above the diagonal show correlation coefficients. Different shapes reveal different relationships. An exponential MEDV, LSDAT curve, a skewed crim, Indus cloud, and thus needed transformations. Size adds a numerical variable to scatter plots, creating bubble plots. Rosling's animated scatter plots of world demographics are famous, but serve statistical storytelling more than exploration. The manipulation section is where pre-processing thinking and plotting converge, because most machine learning time is spent on pre-processing. Rescaling to a logarithmic axis can rescue an unreadable plot. Points crowded against the y-axis spread into a visible log relationship, and box plots rescaled in log units become comparable. Aggregation changes the granularity of the display. For time series, aggregating monthly to yearly reveals the global trend, and aggregating by month of year exposes the seasonal peak. A moving average window smooths the series to expose the trend. For non-temporal data, aggregation works when a meaningful hierarchy exists. Geographical, tracks within zip codes. Organizational, people within departments within units. Zooming and panning reveal detail and outliers. A power distributor only found its troubling electrical frequency anomalies by zooming to an extremely micro scale, and the level of global versus local behavior visible in the data helps choose between model-driven methods, regression, and data-driven ones, exponential smoothing, k-nearest neighbors. Filtering removes noise to focus attention, supporting the same pattern detection. Trend lines and in-plot labels are references that help. Overlaying a polynomial trend makes the shape of a pattern accessible by eye. Labels on a utility scatter plot, fuel cost against sales, make the emerging clusters and their members visible, ready for formal clustering. Large datasets defeat plots that draw every point, so the options are sampling, smaller markers, transparent or unfilled markers, breaking the data into panels, aggregation, bubble size as an observation count, and jittering, adding a little noise to uncover overlaid points, as with the lone acceptor cloud dominated by non-acceptors. The parallel coordinates plot takes multidimensional display one step further. A vertical axis is drawn for each variable, and each observation becomes a line connecting its values across the axis, forming a multivariate profile. Splitting the Boston tracks into two panels by ket_MDV shows that expensive tracks consistently have low crim, low LSDAT, and high RM compared with cheaper tracks. An immediate red on which predictors distinguish the classes. Reordering the columns can reveal observation clusters, which makes the plot useful in unsupervised work as well. Interactivity, finally, is key to gaining information from graphical visualization. Its three principles: making changes to a chart easy, rapid, and reversible, combining multiple concurrent charts on one screen, and linking visualizations so that an operation in one display is reflected in the others. A static histogram must be replot for every new bin choice. An interactive 1 ins under a slider. Static software demands new variables for each temporal aggregation and manual axis changes for zooming. An interactive interface provides temporal hierarchies and zoom sliders. Static plots resist interplot linkage and require regeneration on each selection. Linked interactive plots highlight the selected observations everywhere at once. As Ben Schneiderman puts it, dimension encodings, hue, shape, and panels for categoricals, color intensity and size for numerics, animation for time. Operations, rescaling, aggregation, zooming, panning, and filtering expose patterns and distinguish global from local behavior. Parallel coordinates, 1 axis per variable, each record a connecting line, a multivariate profile that reveals which predictors separate classes. Interactivity, rapid, reversible changes, multiple linked charts, shared highlighting across views. An interface is worth 1,000 pictures. Quote, a picture is worth 1,000 words. An interface is worth 1,000 pictures. Commercial tools like Spotfire and Tableau have invested heavily in such interfaces, which remain hard to replicate in a programming language. Though the Python community, via Plotly and Bokeh and still emerging higher-level tools, is moving steadily in that direction. Specialized visualizations. Beyond time series and cross-sectional structures lie data forms ordinary plots handle poorly. Network, hierarchical, and geographical data. A network diagram draws nodes, actors as circles and edges, relations as connecting lines. A social network of Facebook friends, an eBay marketplace of sellers and buyers, a product network of Amazon recommendations. The eBay network of Swarovski bead auctions shows a marketplace dominated by a few high-volume sellers with many buyers interacting around each, suggesting possible partnerships. Network plots also aid association rules. In grocery data, a beer and diapers combination appears as a highly connected pair and a nearly universal item like milk as a very large node. Tree maps are built for large hierarchical datasets, rendering hierarchy as rectangles nested within rectangles. In a tree map of nearly 11,000 eBay auctions ordered by category, subcategory, and brand, rectangle size encodes average closing price and color intensity, the percentage of sellers with negative feedback, and it visibly concentrates the fraudulent seller's signal in expensive luxury watch auctions, directly useful for a classification task. Plotly gives the best interactive tree maps in Python. Map charts plot data on a geographic background, ideal when a variable like zip code carries many categories that resist ordinary analysis. The chapter shows a scatter-over map of statistics.com students' and instructors' locations and world choropleths comparing well-being scores with GDP, where darker shading means higher values, and even the choice between the high-level plotly.express and lower-level plotly.graph_objects modules is a matter of control versus convenience. Network plots, nodes and edges for social and product networks, size by centrality. Tree maps, nested rectangles for hierarchical data, size and color intensity, encoding value and risk. Map charts, geographic background for many category location data. Summary, major visualizations and operations by machine learning goal. The chapter ends by consolidating its guidance into a ready reckoner organized by what the analyst is trying to do. Prediction, put the numerical outcome on the y-axis of box plots, bar charts, and scatter plots. Study it against categorical predictors with side-by-side box plots, bar charts, and panels, and against numerical predictors with scatter plots. Use distribution plots to decide on transformations. Add color, panels, or size to test for interaction terms. Aggregate and zoom to distinguish global from local pattern. Classification. Study the categorical outcome against categorical predictors with bar charts. Outcome on the y-axis against numerical predictors with side-by-side box plots. The most separable boxes flagging useful predictors against pairs of numerical predictors with color-coded scatter plots. Use color on a parallel coordinates plot. Use distribution plots and aggregation levels as for prediction. Time series forecasting. Create line charts at several temporal aggregations to determine pattern types. Zoom and pan to examine short periods. Aggregate to identify global and local patterns. Identify missing values. Overlay trend lines of different types to judge modeling choices. Unsupervised learning. Use scatterplot matrices for pairwise relationships and clustering of observations. Use heat maps to examine correlations. Use aggregation and zooming for different behavior regions. Generate parallel coordinates plots to identify clusters. 2 unsupervised recommenders. Association rules find generic co-purchase patterns. Collaborative filtering personalizes from user item combinations. Extend the discipline. Fine-tuning and RAG adapt general models. The promise is real, and so are the ethical stakes. Chapter 4. Dimension Reduction. Introduction. Dimensions are variables, and a dataset's dimension must often be reduced before machine learning algorithms operate efficiently. For large neural nets, the reduction is handled by the algorithm itself. For other methods, it is part of the pilot and prototype phase of supervised learning, done before deployment. Several approaches are on the table. Incorporating domain knowledge to remove or combine categories. Using data summaries to detect information overlap between variables. Converting categorical variables into numerical ones, and automated techniques such as principal component analysis, which creates a new set of uncorrelated variables, weighted averages of the originals, of which a small subset usually retains most of the combined information. Supervised methods like regression and classification and regression trees can also remove redundant variables and combine similar categories. The stakes are practical. Even when the initial variable count is small, new derived variables, dummies, new forms of existing ones, quickly expand the set, and correlated or irrelevant variables invite overfitting and hurt predictive accuracy and reliability. A large variable count also creates computational problems for some algorithms and raises deployment costs, since superfluous variables must still be collected and processed. Curse of dimensionality. The dimensionality of a model is the number of predictors it uses, and the curse of dimensionality is the affliction caused by adding variables to multivariate data models. As variables are added, the data space becomes increasingly sparse, and models fail because the available data cannot support a useful model across so many variables. The difficulty grows exponentially. A location on a chessboard has 2 dimensions and 64 choices. Expanding the board to a cube raises dimensions by 50%, but multiplies location options 8-fold, to 512. In statistical distance terms, the proliferation of variables means nothing is close to anything else anymore. Too much noise is added and patterns and structure are no longer discernible. The problem is acute in genomics, where an analysis may confront thousands of genes. In the AI literature, the reduction goes by other names: factor selection, feature selection, or feature extraction. Sparsity. Each added variable makes the data space drastically sparser. The chessboard to cube jump multiplies options 8-fold while adding 50% of the dimensions. Nothing is close anymore. In statistical distance terms, high dimension adds noise that obscures structure and model performance fails. Quote, "The difficulty posed by adding a variable increases exponentially with the addition of each variable. In statistical distance terms, the proliferation of variables means that nothing is close to anything else anymore. Too much noise has been added, and patterns and structure are no longer discernible." Practical considerations. Although machine learning prefers automated methods over domain knowledge, the first step is to make sure the measured variables are reasonable for the task, and talking with the data provider almost always yields better results. The practical questions: which variables are most important and which likely useless, which carry error, which will be measurable in the future and at what cost, and crucially, which can actually be measured before the outcome occurs. The number of bids on an ongoing auction cannot predict its closing price, because that number is not yet known. The Boston housing example, crime rate, pupil/teacher ratio, median home value per tract, and more, anchors the chapter and recurs in later ones. Domain knowledge first. Which variables matter, carry error, remain measurable, and are knowable before the outcome occurs. You cannot predict an auction's closing price with its own bid count. Data summaries. Getting familiar with the data through summaries and graphs is an initial step whose importance cannot be overstated. The better you understand the data, the better the modeling. The pandas methods describe mean, STD, min, max, median, and len reveal each variable's scale and type. Min and max flag extreme values that might be errors. A large gap between mean and median indicates skew. The standard deviation shows dispersion. ISNA.sum counts missing values. The Boston summary immediately shows wide differences in variable ranges, a warning that variation in scale can distort later analyses, and reveals right skew in crim, with no missing values and no obvious typing errors. Aggregation extends the summary. Value counts breaks a single categorical variable into counts. 471 of 506 Boston tracts do not bound the Charles River. Group B aggregates by one or more variables, often after binning a numerical variable. Pivot table reshapes the aggregation into a table of outcome means by two grouping variables. In classification tasks, producing summaries for each class is a good exploratory step, flagging predictors that separate the classes. Summary statistics. Mean/median gaps reveal skew. Min/max flag errors. Standard deviation measures dispersion. Missing counts inform cleaning. Aggregation and pivots. Value_counts. Group B, with binning, and pivot tables summarize combinations and class separating potential. Correlation analysis. With many potential predictors, information usually overlaps, and the correlation matrix, all pairwise correlations, finds the redundancies. Pairs with very strong positive or negative correlation carry overlapping information and are candidates for removal, which also avoids the multicollinearity problems that arise when two or more predictors share the same linear relationship with the outcome. Correlation analysis also detects accidental duplication, the same variable appearing twice under different names after a merge, or the same phenomenon measured in different units. The heat map from Chapter 3 makes the scan easier. Redundancy detection. Strongly correlated pairs overlap in information and are prime removal candidates, also avoiding multicollinearity. Duplication. Correlation flags the same variable accidentally re-entered under a different name after a merge, reducing the number of categories in categorical variables. A categorical variable with m categories transforms into m or m-1 dummy variables, depending on the method, so even a few categorical variables can inflate a dataset's dimension enormously. The remedy is to reduce categories by combining close or similar ones, work that requires expert knowledge and common sense. Pivot tables show each category size and how the outcome behaves in it. Categories with very few observations are prime candidates for merging, and the categories most relevant to the analysis can be kept while the rest are labeled other. In classification, a pivot table broken down by outcome class reveals categories that do not separate the classes, equally candidates for other. In the Boston data, the distribution of cat_MEDV is identical across ZIN values 17.5, 90, 95, and 100, all high-value tracks, so those four categories collapse into one. Other ZN values combine similarly. In a time series, a season variable can be reduced by examining the time plot. In the quarterly Toys R Us revenues, only quarter 4 stands out, so quarters 1 through 3 combine into a single category. Category collapsing. Categories with few records or that fail to separate outcome classes merge into other, guided by pivot tables and expert judgment. Time series seasons. Similar periods, e.g., 3 of 4 quarters, combine into one category, converting a categorical variable to a numerical variable. Sometimes the categories of a categorical variable represent intervals. Age group, income bracket. If the interval values are known, the categorical code, say, 2 for ages 20 to 30, can be replaced by its mid-interval value, 25, yielding a numerical variable that no longer needs multiple dummy variables. Interval recoding. Known interval categories become mid-interval numerics, removing the need for dummies. Principal component analysis. PCA is a useful method for dimension reduction. especially with many variables, and especially when subsets of measurements share a scale and are highly correlated. It provides a few variables, often as few as 3, that are weighted linear combinations of the originals and retain most of the information. PCA is intended for numerical variables. For categorical ones, correspondence analysis is more suitable. The chapter works through the mechanics on the breakfast cereals data. 77 cereals measured on 13 nutritional variables and a consumer healthiness rating, with servings based on a bowl, constant volume, not weight, as most people simply fill a bowl. Focusing first on 2 variables, calories and rating, the two are strongly negatively correlated. Roughly 69% of the total variation is covariation, duplicated in both. The idea of PCA is to find a linear combination that captures most of the variability, information in the sense of variance. The first principal component is the direction of greatest variability. Among all possible lines, the one onto which the data project with maximum variance, which is also the line minimizing the sum of squared perpendicular distances. The second component is the perpendicular direction carrying the next largest variance, uncorrelated with the first. Running PCA on calories and rating shows the first principal component accounting for 86% of the total variability, so dropping the second keeps 86%, with the two components' variances summing exactly to the original variable's variances, each component's mean 0 after subtracting. The formalization generalizes to p-variables. Seek new variables that are weighted averages of the originals, after centering, uncorrelated by construction, ordered by variance from largest to smallest. A further advantage, regression models built on principal components as predictors encounter none of the multicollinearity problems of the originals. On all 13 serial variables, the first 3 components capture over 96% of total variation, under a quarter of the original dimensions. But these results are influenced by scale. Normalization changes the picture. Examining the unnormalized weights shows the first component dominated by sodium and the second by potassium, both measured in milligrams while the other nutrients are in grams. So the scale, not the structure, is producing the result. Normalizing, dividing each variable by its standard deviation, giving each unit variance, equalizes importance. Whether to normalize depends on the data. When units are common and scale reflects importance, dollars. Jet fuel versus heating oil sales, leave the data alone. When units differ or scale does not reflect importance, normalize. With the normalized serial data, 7 components are now needed for 90% of the variability, and reading the weights becomes informative. The first component balances calories in cups against protein, fiber, potassium, and rating. High scores mean high calorie content and low nutrition, unsurprisingly associated with low ratings. The second mainly reflects serving weight. The third, carbohydrate content. Plotting the first 2 scores shows brand cereals on the right, giving way to less healthy cereals leftward, heavier cereals upward, and children's cereals clustering in the middle right. A structure genuinely useful for clustering. For classification and prediction, PCA is applied to the predictors on the training data to fix the number of components to retain. Holdout records are then scored using the training weights and treated as predictors. The honest caveat, a subset of principal components can lose nonlinear predictive information, since PCA captures only linear relationships among the original variables. Principal components, uncorrelated weighted averages of the original, centered variables ordered by variance. A few often retain most information. First, PC, the direction of maximum projection variance, equivalently the line minimizing squared perpendicular distance. Normalization, standardizing to unit variance equalizes variable importance, reversing the dominance of whichever variable has the largest scale, sodium and potassium over gram-scale nutrients. Trade-off, PCA captures only linear relationships, so a reduced component set can drop nonlinear predictive information. Dimension reduction using regression models. Summary statistics, plots, and PCA are exploratory. Some ignore the outcome entirely, PCA, while others informally use the outcome, predict a relationship, combining categories by their outcome behavior. A more direct approach fits a regression model, linear for prediction, logistic for classification, and uses subset selection procedures to choose a subset from the larger set. Fitted regression models also combine categories. Categories whose coefficients are statistically insignificant can merge with the reference category, and categories with similar same-sign coefficients can be combined because their effects on the outcome are similar. The delayed flights example in Chapter 10 illustrates this. Subset selection, regression, linear for prediction, logistic for classification, algorithmically chooses predictor subsets. Category combining, statistically insignificant or similar sign coefficients license, merging categories with the reference. Dimension reduction using classification and regression trees. Classification and regression trees offer another route, since the algorithm creates binary splits on the predictors that best classify or predict the outcome. The resulting tree reveals the important predictors. Predictors that do not appear in the tree can be removed, and categories that do not appear can be combined. Trees thus serve both to reduce the number of columns and to consolidate categories, awaiting full treatment in Chapter 9. Part 3. Performance Evaluation. Tree as selector. Predictors and categories absent from the tree are candidates for removal or combination. Chapter 5. Evaluating Predictive Performance. Introduction. This chapter answers the question that makes everything else in machine learning meaningful. How well will a model predict on new data? The answer begins with a warning against the danger of evaluating a model on the data that trained it, and it proceeds through the full menu of performance metrics. For prediction, there are average error, mean absolute percentage error, and root mean squared error, all computed on holdout data. For classification, there are the confusion matrix measures, overall accuracy, sensitivity, specificity, plus the metrics that account for misclassification costs. The relation between the chosen cutoff value and classification performance is made explicit, and the ROC curve is presented as the popular chart for assessing performance across cutoffs. When the goal is not to classify the whole sample correctly, but to single out the most interesting records, the 10% of customers most likely to respond, the 5% of claims most likely to be fraudulent, cumulative gains and lift charts take over. The chapter closes with oversampling rare classes and adjusting performance metrics to undo its effects, and with a reminder that comparing holdout to training metrics is how you detect overfitting. The machinery rests on distinguishing the three things a model can output: a predicted numerical value, a predicted class membership, and a propensity, the probability of membership in a class. Prediction methods produce numbers, classifiers produce propensities, and a cutoff on the propensities converts them into class memberships. Underlying the whole chapter is a quieter distinction between the two uses of a classifier: classification, predicting class membership for each new record, and ranking, detecting which of a set of new records are most likely to belong to the class of interest. Evaluating predictive performance. Predictive accuracy is not goodness of fit. Classical statistics measures how well a model fits the data on which it was trained. Machine learning cares about accuracy on new records. The art of the second and standard error of estimate of regression, and the residual analysis used to gauge fit, say little about predictive ability. The honest measures are therefore all computed on the holdout set, which is more similar to the future records to be predicted. It was not used to select predictors or estimate parameters. The benchmark criterion for prediction is the naive average. Predict each new record's value as the training set mean, ignoring all predictors. A good model must outperform this benchmark. The prediction error for record I is the difference between actual and predicted value, and the popular measures aggregate these errors in different ways. M&E gives the magnitude of the average absolute error. Mean error keeps the sign, so positive and negative errors cancel. It reveals whether predictions systematically over or underpredict. MPE and MAPE give percentage scores of deviation, MAPE without sign. RMSE takes the square root of the average squared error, giving the typical error in the outcome's own units, like a standard error of estimate computed on holdout data instead of training data. All these measures are influenced by outliers, so plotting the error distribution, A histogram or box plot is itself a diagnostic that reveals more than any single metric. The chapter's Toyota Corolla example, 600 training for 100 holdout cars, shows most holdout errors inside the plus or minus $2,000 range. Comparing training and holdout performance is diagnostic of overfitting. Training errors are expected to be smaller, and the more complex the model, the greater the gap. In the extreme, training error approaches zero, while holdout error stays substantial. Comparable training and holdout metrics, as in Table 5.1, are a good sign. Predictive accuracy is not equal to goodness of fit. R to the second and residual analysis describe fit. Holdout-based MFI, mean error, MPE/MAPE, and RMSE measure predictive ability. Naive benchmark. The training average is the baseline a good prediction model must beat. Gains and lift. Ordering records by predicted value and accumulating actuals shows how much better than random a ranking model is. Quote, errors that are based on the training set tell us about model fit, whereas those that are based on the holdout set, called prediction errors, measure the model's ability to predict new data, predictive performance. Cumulative gains and lift charts answer a different question. Among a set of new records, which subset yields the highest cumulative predicted values? They are relevant only when ranking. Searching for the top records is the goal, not when predicting each record's value. The car rental firm that disposes of its fleet and wants to pick from cars it must sell the ones that maximize revenue is the running illustration. The charts order the records by predicted value from high to low, accumulate actual values as gains, and compare the resulting curve with the diagonal benchmark line of naive prediction. The further the curve rises above the diagonal, the better the model separates high value from low value records. The same information becomes a decile-wise lift chart, grouping the ordered records into 10 deciles and plotting, per decile, the ratio of model gains to benchmark gains, the lift. Selecting the top 10% of Toyota cars yields 1.7 times the revenue of a random 10%, a lift read directly from the ratio of the gains curve value to the benchmark value. Judging classifier performance. The natural criterion for a classifier is the probability of misclassification, and the simplest benchmark is the naive rule. Classify every record into the majority class, ignoring all predictor information. A classifier that uses predictors should outperform this baseline, with important exceptions, as the rare class discussion will show. The plausibility of a model also depends on class separation. If the classes are well separated by the predictors, even a small dataset suffices. If they are not, no amount of data helps. The chapter contrasts 24 riding mower households that separate cleanly by income and lot size, with 5,000 loan acceptor records that overlap heavily. The confusion classification matrix summarizes correct and incorrect classifications. Rows and columns are predicted in actual classes. The diagonal cells count correct classifications, and the off-diagonal cells count each type of error. From it comes the estimated misclassification rate, the overall error rate, and its complement, overall accuracy. Estimates are reliable only with a large enough dataset and classes that are not too rare. Using the holdout data to build the confusion matrix is what gives an honest estimate of future error. A training data confusion matrix flatters the model in exactly the way overfitting predicts. Comparing the two matrices is itself a check for overfitting. Most classification algorithms first estimate propensities. The probability a record belongs to each class. With overall accuracy as the goal, the record is assigned to the class with the highest probability. When a single class is of special interest, the analyst compares its propensity to a cutoff. The default cutoff in two-class classifiers is 0.5. Above 0.5, class 1, below, class 0. Raising the cutoff classifies fewer records as the class of interest. Lowering it classifies more. Typically, either move raises the misclassification rate. The mower example starts at March 24th with cutoff 0.5, rises to 5 to 24 at 0.25, more non-owners misclassified as owners, into June 24th at 0.75, more owners missed. Plotting accuracy against the cutoff shows a stable plateau around 0.8, between 0.2 and 0.8. Why move the cutoff at all? Because misclassification costs are asymmetric. It may matter far more to catch owners or frauds or defaulters than to avoid bothering the rest, and a cutoff can be tuned to accept the cheaper kind of error. A triage variant uses two cutoffs and a cannot say category, sending only the gray area to human review, as in classifying legal discovery documents in a clearly relevant, clearly not, and needs review. Sensitivity and specificity measure the classifier from the standpoint of the classifying agency. Sensitivity, recall, the true positive rate, is the proportion of positive members correctly classified. Specificity, the true negative rate, is the proportion of negative members correctly classified. When one class matters much more than the other, detecting bankruptcy over solvency, overall accuracy is the wrong yardstick, and this pair takes over. The ROC curve plots sensitivity against 1 minus specificity, true positive rate against false positive rate, as the cutoff descends from 1 to 0. The closer the curve hugs the top left corner, the better the classifier, while the diagonal traces a guessing classifier with no information. The area under the curve, AUC, ranges from 1, perfect discrimination, to 0.5, random. Naive rule. Assign every record to the majority class. The baseline classifiers must beat, with exceptions. Confusion matrix, predicted by actual counts yield error rate, accuracy, sensitivity, recall, specificity, precision, F1, and per group differences. Propensity and cutoff, a cutoff on class. One probability converts propensities to classes. Higher cutoffs catch fewer, lower cutoffs over-identify. ROC and AUC. Sensitivity versus 1 specificity across cutoffs. Useful for comparison, but not a single selection metric. Asymmetric costs. Misclassification costs fold into the cells, so expected cost, depending only on cost ratios, drives the decision. Quote, "We therefore advocate not using AUC as a single performance metric for selecting a model." The authors are explicit about AUC's deficiencies. It weights all misclassifications equally, may include irrelevant regions of the curve, and can mislead when ROC curves of different algorithms cross. Precision and recall add the entity's perspective. Precision is the proportion of positive predictions that are actually positive, exactness. Recall the proportion of positives that were caught, completeness. For fraud detection, we want recall near 1. Find all true frauds, and can tolerate low precision if misclassifying legitimate transactions is cheap. The F1 score combines the two with equal weight. Plotting precision, recall, and F1 against the cutoff exposes the trade-off. In the mower example, F1 peaks at 0.88 at cutoff 0.5. The chapter also distinguishes the agency's view from the individual's. Sensitivity and specificity answer, how well does the classifier segregate the important class members? While the false discovery rate, the proportion of positive predictions that are wrong, and the false omission rate, the proportion of negative predictions that are wrong. Answer, given my predicted class, what is my chance of actually belonging to that class? Asymmetric costs are the reason the misclassification rate alone can mislead. The chapter sets out the payoff. Mailing an offer to 1,000 people with a 1% response rate, where a responder is worth $10 and the mailing costs $1. Classifying everyone as a non-responder gives a 1% error rate, but yields $0 profit, a classifier with a higher error rate. Missing 2% of buyers and wasting 20% of offers still yields $60 profit. The trick is to fold all cost and benefit into the misclassification cells, recording the cost of failing to catch a responder rather than the benefit of catching one, so that minimizing expected cost becomes the criterion. The average misclassification cost depends on the costs only through their ratio, which is far easier to estimate than the absolute values. When the sample is oversampled, the true class proportions enter through the ratio as well. This is why software often prompts for ratios rather than actual costs and priors. Generalizing to more than two classes multiplies the misclassification types combinatorially, making the full cost matrix prohibitively complicated. Judging ranking performance. Ranking performance answers the marketing question: how effectively can we skim the cream, select a relatively small number of records, and capture a relatively large portion of the responders? The input is a scored validation set, each record carrying its propensity for the class of interest. We sort by propensity in descending order and accumulate the actual members of the class. The gain at each point is the cumulative count, or cumulative sensitivity. The cumulative gains chart plots these cumulative gains against the number of records. Interpretation runs against two reference lines. The ideal classifier would place all the ones first, a curve that rises with slope 1 until every positive is accumulated, then runs flat. A useless model shuffles propensities randomly, accumulating positives at their average rate, the diagonal reference line from origin to the total. A good model sits well above that diagonal. Targeting the top 10 of 24 MOA records captures about 9 actual owners versus the 5 expected at random, a lift of 1.8. Lift is not constant. It is highest when acting on the few most promising records and decays as more records are included. The decile-wise lift chart condenses the gains information into 10 buckets, each bar showing the factor by which the model outperforms random selection in that decile. Widely used in direct marketing, it shows, for example, that the top 10% of flights by delay probability yield twice as many delays as random selection, and that even the top 40% still performs twice as well as random, after which the lift dissolves to 1. A lift chart cannot be used with a multi-class classifier unless a single important class is defined and the rest reduced to its complement. Gains and lift charts survive the introduction of costs and benefits. The procedure: sort by propensity, record the cost or benefit of each record's actual outcome, accumulate these values into a gains curve, and draw the reference line from the origin to the total net value. If mailing costs $0.65 each against a $25 responder value at a 2% response rate, the net value of the whole list is negative and the reference line slopes downward. The optimal stopping point is where the gains curve is at its maximum, mailing to about 3,000 of 10,000 people. Gains can also be plotted against the cutoff rather than the number of records. The first suits a budget constraint, the second the search for a cutoff that separates the classes. Ranking goal: skim the cream. Identify the members of a rare, valuable class among new records. Cumulative gains and lift. Sort by propensity. Accumulate class members and compare against the ideal and the random benchmarks. The decile-wise lift chart condenses this to per decile multipliers. Costs and benefits form. Accumulate dollar gains by propensity, with the optimum where the curve peaks. The reference line may slope down when net value is negative. Oversampling. Rare classes, responders, frauds, defaulters are the interesting ones, and simple random sampling may yield too few of them to build a model. Stratified sampling that oversamples the rare class, equivalently, undersamples the plentiful one, improves classifier performance. Oversampling is one way to fold asymmetric costs into training. If missing a responder costs 5 times missing a non-responder, replicating each responder fourfold lets the algorithm find the classification line automatically. Oversampling without replacement in proportion to the costs is optimal in principle, but often impractical, since responders may be too scarce. Practitioners often simply sample equal numbers of responders and non-responders. The imbalanced learn package supplies random oversampler, random undersampler, and SMOTE, which synthesizes new minority class records by combining a randomly chosen rare record with one of its k-nearest neighbors. Whatever the oversampling method, performance must be adjusted for it in one of two ways. Score the model on a holdout set selected without oversampling, the simpler route, or reweight an oversampled holdout set to undo the distortion. For the confusion matrix, each responder in the sample represents the ratio of the sample response rate to the population rate. With a 2% population response oversampled to 50%, each sampled responder stands for 25 population responders, and each non-responder for about 0.51. Dividing each cell by its oversampling weight restores the population scale matrix and the honest misclassification rate. The cumulative gain chart is adjusted the same way, dividing each record's cost or benefit by its oversampling weight, so the marketing decision is made against the real response distribution. Part 4. Prediction and classification methods. Oversampling rare classes. Weighting the rare class when sampling gives models enough events and folds asymmetric costs into training. Adjustment. Evaluate on an unweighted holdout or reweight an oversampled holdout by the oversampling weights to restore true proportions. SMOTE. Synthetically generate minority records by combining a rare record with its nearest neighbors. Chapter 6. Multiple Linear Regression. Introduction. The most popular model for making predictions is the multiple linear regression model of the Introductory Statistics course. It fits a relationship between numerical outcome variable y, the response, target, or dependent variable, and a set of predictors, independent variables, input variables, regressors, or covariates, under the assumption that y equals beta sub 0 plus beta sub 1x sub 1 plus dots. C plus beta sub px sub p plus epsilon, where the beta are coefficients and epsilon is the noise or unexplained part. Regression modeling is more than estimating coefficients. It also means choosing which predictors to include and in what form. A numerical predictor may enter as itself, in logarithmic form, or bend into groups, a choice guided by domain knowledge, data availability, and needed predictive power. The applications are as broad as business itself, predicting credit card activity from demographics, vacation travel, spending from frequent flyer history, help desk staffing from product and sales information, cross-sell revenue, and the impact of discounts on retail sales. Explanatory versus predictive modeling. Two different objectives hide inside the same procedure, and the distinction often escapes those who first met regression in a statistics course. The explanatory or descriptive objective is to explain or quantify the average effect of inputs on an outcome. The data are a random sample from a population. The estimated model captures the average relationship in that population, and the coefficient statements are of the form: a unit increase in service speed is associated with an average increase of 5 points in customer satisfaction, all other factors being equal. Where causality is known, such statements are actionable policy, explanatory modeling. Where it is not, they quantify association, descriptive modeling. The predictive objective is entirely different. Predict the outcome value for new individual records, where the analyst cares not about the coefficients or the average record, but about the predictions used for micro-decision-making at the record level. The choice of model follows the goal. An explanatory model is judged by how closely it fits the data and uses the whole data set to learn the population relationship. A predictive model is judged by predictive accuracy on a holdout set and splits the data into training and holdout. Where the explanatory model focuses on the coefficients, the predictive model focuses on the predictions themselves. A good predictive model can fit its training data loosely. A good explanatory model can predict poorly. Explanatory modeling uses the whole data set to estimate an average population relationship, judged by fit and coefficient meaning. Predictive modeling splits data into training and holdout, judged by predictive accuracy on new records, with coefficients secondary. The pair diverge. A good predictive model can fit loosely. A good explanatory model can predict poorly. Quote, a good predictive model can have a looser fit to the data on which it is based, and a good explanatory model can have low prediction accuracy. Estimating the regression equation and prediction. Once the predictors in their form are fixed, the coefficients are estimated by ordinary least squares, minimizing the sum of squared deviations between actual and predicted outcome values. Under the classical assumptions, normal noise, correct linear specification, independent records, homoscedasticity, these estimates are unbiased and have the smallest mean squared error of any unbiased estimates. But the chapter's key insight for prediction is that even if normality is dropped entirely, the least squares model remains best among linear models in mean squared error. Normality matters for confidence intervals and tests, which belong to explanatory modeling. Violations of the other assumptions may still leave predictions accurate enough for their purpose. Evaluate predictive performance, treat assumptions as secondary, and let residual analysis point toward better models. The Toyota Corolla example carries the chapter. A dealership needs to predict the resale price of used cars so it can price a trade-in promotion profitably. Data on 1,000 cars, age, kilometers, fuel type, horsepower, metallic paint, automatic transmission, engine size, doors, road tax, weight, are partitioned 60-40 into training and holdout. The fuel type variables' three categories require two dummy variables. The third, CNG, is redundant, a perfect linear combination of the other two, and including it would make the regression fail. The fitted model's coefficients are interpretable. Each month of age lowers price by roughly $131, each kilometer by about $0.02. Diesel cars carry a premium of roughly $3,876 over CNG. On the holdout set, RMSE is $1,355 and MA $1,028, with most errors inside plus or minus $2,000 and a noticeable tail of large underpredictions, a judgment call about whether that matters for the application. Cross-validation improves on the single random split, which can be sensitive to which records landed where. Applying 5-fold cross-validation to the entire dataset yields an average RMSE of $1,515 and MA of $1,053, a more stable estimate of predicted performance than one partition, and it dispenses with a separate holdout entirely. The scoring metrics are reported negative because scikit-learn convention makes higher scores better. Variable selection in linear regression. With many candidate predictors, the kitchen sink temptation, throw them all in and let the regression sort out, is strong, and the hope of surfacing a hidden relationship is real. But caution is warranted. Some predictors are expensive or infeasible to collect in the future. Fewer predictors can be measured more accurately. More predictors multiply missing values and the records deleted or imputed. Parsimony yields more insight, and coefficient estimates become unstable under multicollinearity, two or more predictors sharing the same linear relationship with the outcome, with a rough rule of thumb of more than 10 records per predictor. Finally, predictors uncorrelated with the outcome inflate prediction variance. These considerations trade off. Accepting some bias can reduce variance, and this variance trade-off, basic to most machine learning, is why predictor reduction is so often worthwhile. The first step in reduction is always domain knowledge, understanding what the predictors measure and why they should matter, then dropping the expensive, the inaccurate, the collinear, the missing, and the irrelevant, aided by frequency and correlation tables, summary statistics, and missing value counts. The computational step, then, follows one of two routes. Exhaustive search fits every subset of predictors and examines the most promising by criteria, such as the adjusted R to the second, which, unlike R to the second, penalizes the number of predictors and is equivalent in subset choice to minimizing training RMSE, and the information theoretic AIC and BC, which balance fit against parameter count, preferring smaller values. For subsets of the same size, AIC and BIC agree. Comparing different sizes is where they diverge. These criteria were designed for explanatory modeling and use training data. The out-of-sample alternative is cross-validation, general and model-independent, but computationally expensive. On the 11 predictors of the Corolla data, exhaustive search with 5-fold cross-validation finds the 5-predictor model, age, kilometers, horsepower, doors, weight, with RMSE $1,479. The iterative algorithms, forward selection, backward elimination, stepwise regression, are computationally cheaper but risk missing good combinations. Forward selection adds the predictor with the largest marginal contribution at each step, but a pair that performs well together yet poorly alone is missed, like job candidates who are excellent colleagues and poor solo interviews. Backward elimination starts with all predictors and drops the least useful one at each step, but the initial all-predictor fit can be unstable and slow. Stepwise regression combines the two, dropping predictors that are no longer useful after additions. On the Corolla data, forward and stepwise reproduce the exhaustive 5-predictor model, RMSE 1479. Backward elimination stops at 9 predictors with RMSE 1482 and a 4-predictor model. Age, kilometers, horsepower, weight performs only slightly worse, preferable on parsimony grounds. Principal components, Chapter 4, and regression trees, Chapter 9, offer further reduction routes. Regularization, or shrinkage, is the more flexible alternative to subset selection, where subset selection sets coefficients to 0 and produces interpretable results. Shrinkage pulls coefficients towards 0 via a penalty on their aggregated magnitude, not on their count, with predictors typically standardized first. The logic: highly correlated predictors produce coefficients with high standard errors, as small training data shifts radically reallocate emphasis among them. And this instability hurts prediction. Constraining the combined magnitude reduces that variance. Ridge regression uses the L2 penalty, sum of squared coefficients, shrinking coefficients but keeping all predictors. Lasso uses the L1 penalty, sum of absolute coefficients, which effectively shrinks some coefficients to 0 and thereby selects a subset. The tuning parameter lambda controls the strength of the penalty. Lambda equals 0 is ordinary regression. Elastic net combines the two penalties with a mixing parameter between 0 and 1. In scikit-learn, the penalty is set via alpha and lasso CV, ridge CV, and Bayesian ridge selected automatically. Lasso CV and ridge CV by cross-validation, Bayesian ridge iteratively from the training set. Since none normalizes the data, they're combined with a standard scaler in a pipeline. On the Corolla data, Lasso reduces the predictors to 5. Ridge keeps all 11 with coefficients close to the unregularized ones, and both holdout performances are comparable to the full model. While in terms of computational intensity and predictor count, the selection methods differ markedly: 11 predictors for full and ridge, 6 for exhaustive/forward/stepwise, 5 for backward and lasso. The choice among them is therefore as much about parsimony, interpretability, and compute as about a few RMSE dollars. The stats models appendix is a note for the genuinely explanatory analyst. Small ols gives the full inferential output. Standard errors, p-values, are to the second. AIC, BeachC, Durbin-Watson. More than predictive modeling needs, and OLS.FTregularized applies the same ridge/lasso distinction through the L1WT argument. Kitchen sink caution. Many predictors add collection cost, missing values, instability, and multicollinearity. Parsimony wins. Exhaustive search and criteria, adjusted are to the second. AIC and BIC balance fit against parameter count. Cross-validation estimates out of sample error. Iterative algorithms. Forward selection, backward elimination, and stepwise search are cheaper but can miss good predictor combinations. Regularization. Ridge, L2, shrinks coefficients towards 0. Lasso, L1, shrinks some to 0, selecting a subset. A tuning parameter lambda controls strength. Elastic net mixes the two. Validation-guided search. Try fewer or interaction-bearing predictors. Prefers simpler models when performance ties, and reserve a holdout for final assessment. Regularization. Stepwise/forward/backward heuristics and L1/L2 penalties select predictors, mirroring Chapter 6. Chapter 7. Nearest neighbors, KNN. The KNN classifier, categorical outcome. The K, nearest neighbors idea, is disarmingly simple. To classify or predict a new record, find the K records in the training data that are most similar to it, its neighbors, and let those neighbors decide. For classification, the new record is assigned to the predominant class among the neighbors by vote. For prediction, the prediction is the average of the neighbors' outcome values. The method makes no assumptions about the form of the relationship between class membership and the predictors. It is non-parametric, drawing its information from similarities in predictor values rather than from parameters in an assumed functional form like the linear equation of regression. Similarity is measured by distance in predictor space. The most popular measure is the Euclidean distance, which is computationally cheap, a decisive advantage, since N computes a distance between every record to be predicted and every record in the training set. Before computing distances, predictors should in most cases be standardized because a variable measured in large units would otherwise dominate the distance. The standardization uses the training data's means and standard deviations, and neither new nor holdout records are included in their calculation. The classification rule is a majority vote. Find the nearest K neighbors and classify the record as a member of the majority class among them. Even the simplest case, K equals 1, is surprisingly powerful with a large training set. The misclassification error of one nearest neighbor is no more than twice the error achievable when the probability density functions of each class are known exactly. The riding mower's example carries the method. A manufacturer wants to classify families as likely or unlikely to buy a riding mower on the basis of income and lot size, working from 24 households, 12 owners, 12 non-owners, partitioned into 14 training and 10 holdout. The authors note openly that the data set is far too small for partitioning and will yield unstable results, but it serves illustration. For a new household with $60,000 income and a 20,000 square foot lot, the closest training household is household 4, $61,500, $20,800, so 1 classifies the newcomer as an owner. With K equals 3, the nearest neighbors are households 4, 14, and 1, 2 owners and 1 non-owner, and the majority vote again says owner. In practice, the model is a scikit-learn pipeline that first standardizes the data and then applies the classifier, ensuring the same pre-processing handles both training and new data. Choosing K is the central tuning decision. Higher values of K provide smoothing that reduces the risk of overfitting to noise. Too low, a K fits noise. Too high, a K misses the local structure that is the method's main advantage. In the extreme, K equal to the number of training records assigns everyone to the majority class. The naive rule, pure over-smoothing. The balanced choice depends on the data. The more complex and irregular the structure, the lower the optimum K. Values typically fall in the range 1 to 20, with odd numbers preferred to avoid ties. The empirical method is to choose the K with the best estimated classification performance. Classify the validation records for various K and compare error rates. In the mower example, K equals 5 or 7 maximizes leave one out cross-validation accuracy at 0.79. Leave one out chosen because of the tiny sample, impractical for large data. The honest caveat, because the training data were used to select K, the cross-validation accuracy is optimistic. A separate holdout set must evaluate the final choice on data it has never seen. Once K is chosen, the algorithm is rerun on the combined training and holdout sets to classify new records. The new household's 5 nearest neighbors are 4 owners, giving a propensity of 0.8 that it is an owner. Weighted K, NN sharpens the majority vote with a simple, powerful idea. The closer the neighbor, the heavier its weight. Each neighbor's weight is the inverse of its distance. Normalized, so the weights sum to 1, and class probabilities are the sums of the weights of the neighbors in that class. In the worked example, with K equals 3, 2 nearby non-owners and 1 farther owner produce weights that yield a 0.59 owner probability, crossing the 0.5 threshold for owner even though the unweighted majority is non-owner. Scikit-learn needs the weights equals distance argument to enable this. The cutoff value is how majority rule and class probability connect. The proportion of class 1 members among a record's neighbors estimates its propensity for class 1, and a simple unweighted majority rule is exactly a cutoff of 0.5. Changing the cutoff, lower to catch a rare class of interest at the cost of over-identifying it, higher to demand stronger evidence, changes the confusion matrix and error rates exactly as Chapter 5 describes. The classifier extends to more than 2 classes with the same majority rule or where one class is of special interest, by estimating the proportion of neighbors in that class as a propensity and comparing it to a user set cutoff. Categorical predictors must be converted to binary dummies before k. In n, since Euclidean distance between categories is meaningless. Here the rule inverts the regression rule. All m dummies are used, one-hot encoding, rather than m-1, because the redundancy causes none of the multicollinearity problems it does in linear models, and dropping a dummy would skew the category's contributions to the distance. Scikit-learn's column transformer applies column-specific pre-processing, one-hot encoding for categoricals, standardizing for numerics, pass-through for variables to leave alone. Non-parametric neighbor vote. A new record takes the majority class of its k nearest training records. No assumed functional form. Distance and standardization. Euclidean distance is cheap and standard. Predictors should be standardized using training means and standard deviations. Choosing k. Low k risks fitting noise. High k oversmooths toward the naive rule. Typically 1 to 20. Chosen by cross-validated accuracy. Weighted k and n. Closer neighbors get heavier votes, inverse distance weights, so a near majority can outvote a farther one. K and n for a numerical outcome. The extension to a continuous outcome leaves the first step unchanged, determine the neighbors by distance, and modifies the second. Instead of a majority vote, average the outcome values of the k nearest neighbors, usually a weighted average, so closer neighbors count more. K-neighbors regressor does this in scikit-learn. The other modification is the error metric. Rather than the classification error rate, choose the best k using RMSE or another prediction error metric. Neighbor averaging. The prediction is the usually distance-weighted average outcome of the k nearest neighbors. RMSE picks the best k. Advantages and shortcomings of k and n algorithms. The main advantage of k and n is its simplicity and lack of parametric assumptions. With a large enough training set, it performs surprisingly well, especially when each class is characterized by multiple combinations of predictor values. As in real estate, where many different combinations of home type, rooms, neighborhood, and price characterize homes that sell quickly versus those that linger. 3 difficulties limit its practical power. First, although no time is spent estimating parameters from the training data, the time to find nearest neighbors in a large training set can be prohibitive. 2 remedies. Reduce the dimension, principal components analysis, and use search tree data structures that settle for an almost nearest neighbor for speed, as in bucketing, where records are grouped into close-knit buckets. The buckets are ordered by distance to the record to be predicted, and the search stops when the distance to a bucket exceeds the closest record found so far. Second, the number of records needed to make the training set large grows exponentially with a number of predictors, because the expected distance to the nearest neighbor rises sharply with dimension. The curse of dimensionality, fundamental to all classification, prediction, and clustering. Third, k and n is a lazy learner. The time-consuming computation is deferred to prediction time, when every new record must be compared against the whole training set, which rules out real-time prediction of a large number of records simultaneously. The Pandora box in the chapter shows the idea in practice. The Music Genome Project rated hundreds of song attributes on a 0 to 5 scale using paid human musicians, then matched users' chosen songs to nearby songs in that space, merging liked songs into clusters and storing disliked ones, until each user's taste was captured by several stations. The human labeling at the heart of the method was also its Achilles heel, costly and a bottleneck on new songs, and later services replaced it with collaborative filtering and deep learning that learned from user behavior and raw sound waves without the human step. Advantage: simple, assumption-free, and strong with large data sets when classes have multiple predictor value signatures. Costs: slow neighbor search, bucketing, and dimension reduction help. The curse of dimensionality on the needed sample size and lazy prediction time computation. Quote, "It is a remarkable fact that this simple, intuitive idea of using a single nearest neighbor to classify records can be very powerful when we have a large number of records in our training set. It turns out that the misclassification error of the one nearest neighbor scheme has a misclassification rate that is no more than twice the error when we know exactly the probability density functions for each class. Chapter 8. The Naive Bayes Classifier. Introduction. The naive Bayes method, and indeed an entire branch of statistics, is named after the Reverend Thomas Bayes, 1702 to 1761, and the chapter builds up to it through the complete or exact Bayesian classifier. The basic principle could hardly be simpler. To classify a new record, find all training records with the same predictor profile, determine which class is most prevalent among them, assign that class. A cutoff probability variant answers a different question. What is the propensity of belonging to the class of interest? By establishing a cutoff, finding the matching records, computing the proportion in the class of interest, and classifying the record if that proportion clears the cutoff. Both procedures rest on conditional probability. The probability of event B given event A, written P of B given A, for a response with G classes and predictor values X sub 1 dots. See X sub P. We want P of class given predictors. The classifier works only with categorical predictors. With numerical predictors, it is unlikely that records will share identical values. So the alternatives are binning the numericals or the Gaussian naive Bayes variant to come. The chapter's first example is an accounting firm that must judge each customer's financial report fraudulent or truthful and wants to know whether prior legal trouble predicts fraud. Of the 1,500 investigated companies, 1,000 training, 500 holdout, 230 had prior legal trouble, and 50 of those were fraudulent. Applying the full, exact Bayesian classifier. For a new company that had prior legal trouble, the conditional probability of fraud is P of fraudulent given prior legal equals 50 over 230. The probability of truthfulness is the remainder, 180 over 230. Under assigned to the most probable class, every record lands in the truthful class, the same result as the naive majority rule. But the auditor's real concern is catching fraud, and for that the cutoff method serves better. If the cutoff is set at 0.20, a prior legal trouble record is classified as fraudulent because its fraud probability of 0.22 clears it. The cutoff is a slider the user adjusts like any model parameter. The exact procedure has a profound practical limitation. It amounts to finding records exactly like the new one across all predictor values. Easy with one predictor, impossible with many. Predicting voting from demographics. Even a sizable sample may contain no record matching a male Hispanic with high income from the U.S. Midwest, a voter in the last election who skipped the one before, 3 daughters, 1 son, divorced, 8 variables, a small number by machine learning standards. Adding a single new variable with 5 equally frequent categories cuts the probability of a match by a factor of 5. Exact matching collapses. With many predictors, almost no record gets an exact profile match. One new 5-category variable cuts match probability 5-fold. Solution: naive Bayes. Naive Bayes breaks the exact matching deadlock by using the entire dataset. For each class, estimate the individual conditional probability of each predictor value within that class. Multiply those probabilities together and by the class's overall proportion. Do the same for every class. Divide each class's value by the sum of all classes' values to obtain the class probability. Assign the record to the class with the highest probability. All the pieces come from pivot tables of the outcome against each categorical predictor. The price is a simplifying assumption of conditional independence. The exact conditional probability of seeing a record with predictor profile X sub 1 dots. Cx sub P within a class is approximated by the product of the individual conditional probabilities. Where the predictors are independent within a class, the two quantities are identical. The assumption avoids hunting for records that combine, say, prior legal trouble and lost money last year, and instead multiplies the probabilities of the two alone. Complete independence is unlikely in practice, yet the procedure works quite well. Because what is usually needed is not an accurate propensity in absolute terms, but a reasonably accurate rank ordering of propensities, and rank ordering typically survives the assumptions violation. Where only ranking matters, and the denominator is constant across classes, the numerator alone suffices, though the resulting propensities, correctly ordered, are not on the scale the user expects. The two-predictor worked example shows how close the naive calculation comes to the exact one. On 10 companies, the naive probability of fraud, given prior legal trouble and small size, is 0.53 against the exact 0.5, and the naive and exact methods agree on the classification for a cutoff of 0.5 and many others. The rank orderings are closer still than the probabilities themselves. And for classification, it is rank ordering that matters. The flight delay example scales it up. Delays on Washington to New York flights in January 2004. 19.5% delayed, 5 categorical predictors. Day of week, departure time and hourly bins, origin, destination, carrier, are classified with a naive Bayes pipeline in scikit-learn. Scoring a Delta flight from DCA to LGA departing 10 to 11 a.m. on a Sunday, a combination that does not exist in the training data, yields propensities of 0.06 delayed and 0.94 on time, exactly what the product of conditional probabilities calculation gives by hand. Evaluated on holdout data, naive Bayes reaches about 80% accuracy in both training and holdout, no better than the naive rule that calls every flight on time at the same 80%. Yet the cumulative gains chart shows the method's real strength lies in ranking, capturing the delayed flights effectively. The spam filtering box is the canonical illustration. Human-labeled spam and non-spam emails provide per-word frequencies. The word free in 500 of 1,000 spam and 100 of 1,000 non-spam yield a 5-6 posterior that a message containing only that word is spam. The word probabilities are multiplied together, and the spam/non-spam ratio is treated as a score against a cutoff the operator can move. The chapter notes the enormous computational burden and the spammer's countermove, poisoning the vocabulary with random irrelevant words that dilute key terms, which is why sophisticated filters add structural signals. Link counts, subject line vocabulary, real originating from addresses, HTML, and images, dynamic versus static IP origins. Independence assumption. The exact profile probability is approximated by multiplying per predictor conditional probabilities within each class. Why it works anyway. Even when independence fails, the rank ordering of propensities, what classification needs, is typically preserved. Cutoff variant. For a rare class of interest, compute the class numerator, divide by the sum across all classes, and compare to a slider cutoff. Advantages and shortcomings of the naive Bayes classifier. The beauty of the classifier is its simplicity, computational efficiency, good classification performance, and ability to handle categorical variables directly. It often outperforms more sophisticated classifiers even when the independence assumption is far from true, an advantage especially pronounced with very large numbers of predictors. 3 issues temper the praise. It requires a very large number of records for good results. More seriously, a predictor category absent from the training data makes naive Bayes assign 0 probability to any new record carrying it. If no training company owns a yacht-owning prospect receives probability 0 of buying high-value life insurance. The absent predictor actively outvotes all the favorable evidence. Large training sets and judicious binning mitigate this. Laplace smoothing replaces the zeros with small non-zero values, the alpha argument, and scikit-learn's default smoothing of 1 already does this. Finally, although the method ranks well, its absolute propensities are biased, which is why it is rarely used in credit scoring. Strengths: simple, fast, handles categoricals directly, often beats stronger models even when independence is violated, especially with many predictors. Weaknesses: needs many records, and absent training category zeros out a record. Laplace smoothing helps. Absolute propensities are biased, so it is avoided in credit scoring. Quote, in practice, despite the assumption violation, the procedure works quite well, primarily because what is usually needed is not a propensity for each record that is accurate in absolute terms, but just a reasonably accurate rank ordering of propensities. Even when the assumption is violated, the rank ordering of the record's propensities is typically preserved. Chapter 9. Classification and Regression Trees. Introduction. If one had to choose a classification technique that performs well across a wide range of situations, requires little effort from the analyst, and remains readily understandable to the consumer of the analysis, a strong contender is the tree methodology developed by Bryman et al. 1984, implemented as CART, classification and regression trees, with the related C 4.5. A classification tree separates records into subgroups by splitting on predictors, creating transparent logical rules. If age less than or equal to 55 and education greater than or equal to 12, then class equals 1. So the resulting subgroups are homogeneous in the outcome and yield useful classification rules. A tree has two kinds of nodes. Decision, splitting. Nodes have successors. A new record is dropped down the tree, taking the appropriate branch at each decision node. Terminal nodes, leaves, have none and represent the final partitioning of the data. Binary CART trees satisfy a tidy identity. The number of terminal nodes is exactly one more than the number of decision nodes. In scikit-learn's plot_tree, each node box shows the number of records, samples, the class distribution, and the majority class. The split condition, predictor, and value sits at the top, the left child meeting the condition and the right child not. Trees are popular because they produce easily understandable decision rules, at least when they're not too large. Each terminal node is a rule, with the majority class deciding, and the class proportions convertible to a propensity compared against a user cutoff, a lower cutoff to catch rare successes at the cost of lumping in more failures. Classifying a new record is simply a matter of dropping it down the tree and taking a vote, or an average for a numerical outcome, of the training records that reach the same terminal node. Classification trees. The key idea underlying tree construction is recursive partitioning of the predictor space. The p-dimensional space is divided into non-overlapping rectangles. Choose a predictor and a split value. Split the space into two parts. Then recursively divide one of the parts again, and so on, until each rectangle is as homogeneous, pure, as possible, meaning it contains records of a single class, impossible when records from different classes share identical predictor values. The riding mower's illustration is illuminating. With 24 households, 12 owners, 12 non-owners, the algorithm first splits on income at 59.7, producing a left rectangle of mostly non-owners, 7 of 8, and a right rectangle of mostly owners, 11 of 16. How is that split chosen? The algorithm examines every predictor and every possible split value, the midpoints between consecutive values, and ranks the splits by how much they reduce impurity, defined as overall impurity before the split minus the sum of the impurities of the two resulting rectangles. The next split, on lot size at 21.4, then purifies the left region further until rectangles become pure. Categorical predictors complicate this. With M categories, the split choices are all ways to divide the set into two subsets, 7 ways for 4 categories, growing rapidly, and scikit-learn currently requires converting them to dummies first. The full set of M, as with K, nearest neighbors. Whether predictors are standardized makes no difference to a tree. Impurity is measured by one of two popular indexes. The Gini index for a rectangle A is a function of the proportions of records in each class, ranging from 0, all one class, to its maximum when the classes are equal. In the two-class case, it peaks at 0.5 when a rectangle holds 50% of each class. The entropy measure takes the same peak at the balance point and is computed with base 2 logarithms. Working the mower split. The unsplit data has maximum impurity, Gini 0.5. After the first split, the left rectangle, 7 non-owners, 1 owner, has Gini 0.219 and entropy 0.544. The right, 11 owners, 5 non-owners, has Gini 0.430 and entropy 0.896. And the combined weighted impurity drops to Gini 0.359 and entropy 0.779. The tree picks whichever predictor and split maximizes this reduction. Recursive partitioning. Repeatedly split the predictor space into rectangles, each as pure, single class, as possible. Impurity measures, the Gini index, and entropy both maximize at balanced classes and guide which split reduces impurity most. Evaluating the performance of a classification tree. Modeling is not finished with a fitted tree. Out-of-sample data are needed for two reasons peculiar to trees. First, tree structure is unstable. Partition the data into two samples and build a tree from each, and when several predictors have roughly equal power, the top-level splits can easily differ, and a different top split cascades into completely different rules. Second, a fully fitted tree invariably overfits. The Universal Bank personal loan example, 5,000 customers, 9.6% acceptors, partitioned into 3,000 training and 2,000 holdout, shows both. The default decision tree classifier grows an unrestricted, fully grown tree with pure leaves, 42 terminal nodes, of which 23 classify as non-acceptor and 19 as acceptor. Its training accuracy is a perfect 1.0, but holdout accuracy is 0.98, and, in fact, the whole exercise is a demonstration of overfitting to perfection. Cross-validating the full tree across 5 folds shows holdout accuracy swinging from 0.973 to 0.993. The instability in visible form. Instability. Slightly different samples can produce very different top splits and cascading rule changes. Overfitting. Fully grown trees fit training perfectly. Accuracy 1.0, yet generalize worse. Holdout and cross-validation expose the gap. Avoiding overfitting. For training data, overall error falls to 0 at maximum tree size. For holdout data, it falls to a minimum, and then rises as the tree starts modeling noise. Hence the classic U-shaped overfitting curve. The intuition. The final splits of a large tree rest on very small numbers of records, so perceived class differences are likely noise rather than signal. Growth can be stopped by rules of thumb. Maximum depth, minimum records in a terminal node, minimum impurity reduction. But knowing a good stopping point is genuinely hard. The lone example compares a full-grown tree with a smaller one restricted by depth, minimum split size, and minimum impurity decrease. The smaller tree has 4 terminal nodes. Its training accuracy, 0.9823, is lower than the full tree's perfect 1.0, yet its holdout performance, 0.9770, essentially matches the full tree's 0.9790, and, crucially, the training versus holdout gap is far smaller. The full tree's gap is the overfitting signature. Fine-tuning replaces hand-set stopping rules with grid search over parameter combinations, evaluated with cross-validation on the training set, never on the holdout set, which must remain untouched until final evaluation. Searching on holdout would overfit the holdout. Grid search CV on the loan data drives the parameters to max depth 5, min impurity decrease 0.0003, min samples that are score split 20, lifting validation accuracy from 0.9877 to 0.9883. The fine-tuned tree reaches 0.9907 training and 0.9825 holdout accuracy. Exhaustive grid search grows expensive quickly. Randomized search CV samples combinations, including from distributions, rather than enumerating all of them. Other size-limiting methods predate and complement these. CHAID, chi-squared automatic interaction detection, uses a chi-squared test of independence at each node, splitting on the predictor with the strongest significant association and terminating when no split improves purity significantly. The ancestor of conditional inference trees. Pruning recognizes that the smallest, farthest from the trunk branches are the most likely to be fitting noise and lops them off. C4.5 grows and prunes with the training data. CART's innovation is pruning with a separate validation set, guided by a cost complexity function that balances misclassification error against a penalty for size. As the complexity parameter alpha rises from 0, the full-grown tree, toward very large values, a single node, the method produces a sequence of trees and either a validation partition or K Fold cross-validation chooses among them. Scikit-learn exposes this through ccp_alpha. Stopping growth, depth, minimum terminal size, and minimum impurity decrease limit size. But good stopping points are hard to guess. Fine-tuning, grid and randomized search over parameters with cross-validation on training, never the holdout. CHAID and pruning. Significance-based split termination or cost complexity pruning of a full-grown tree with validation. ccp_alpha. Classification rules from trees. Each terminal node is a rule, and redundancies can often be removed. If income less than or equal to 110.5 and education greater than or equal to 1.5 and income greater than or equal to 116.5, then class equals 1 collapses to if income greater than or equal to 116.5 and education greater than or equal to 1.5. Transparency matters in settings where the final classification is not the only thing of interest. In health insurance underwriting, showing the rules that led to a coverage denial. Income below a cutoff and low credit history lets the insured demonstrate the denial was not discriminatory. Tree rules are far more easily explained to managers and operating staff than discriminate functions, and certainly more transparent than the weights of a neural network. Rule redundancy. Terminal node rules simplify by dropping redundant conditions. Transparency that matters for regulatory and managerial acceptance. Classification trees for more than 2 classes. Classification trees extend to outcomes with more than 2 classes with no change. The Gini and entropy measures are defined for any number of classes, and the tree's terminal nodes simply carry one of the G-class labels. Generalization. Gini and entropy are defined for any class count, so the tree structure is unchanged. Regression trees. Regression trees adapt the same machinery to a numerical outcome. Many splits are attempted. Impurity is measured in each branch, and the split minimizing the sum measure is chosen. On the Toyota Corolla prices, 1,000 cars, 600 training, the fine-tuned regression tree's top levels are dominated by age, weight, and mileage, with individual details like powered windows making smaller adjustments lower down. 3 details differ from classification trees. Prediction. The terminal node's value is the average outcome of the training records that landed there. A car aged 60 months with 160,000 kilometers and 100 horsepower lands in the node worth 8,392.857, the average of the 7 training cars in that bucket. Impurity, where classification uses the Gini index or entropy, functions of class proportions. Regression uses the sum of squared deviations from the node mean, the sum of squared errors, since the mean is the prediction. Evaluation. Predictions are means, errors are the usual residuals, and performance is measured with RMSE and friends, just as for linear regression. Node mean prediction. A terminal node predicts the average outcome of its training records, e.g., €8,392.90 for 7 old, high-mileage cars. Impurity as SSE. Regression uses the sum of squared deviations from the node mean. Performance uses RMSE like any predictor. Advantages and weaknesses of a tree. Trees are good off-the-shelf classifiers and predictors, and they double as variable selection tools, with the most important predictors typically surfacing near the top. The small lone tree used just 3 of 14 predictors, the fine-tuned 1.5. Users are spared effort in 2 ways. No variable transformation is needed. Any monotone transformation yields the same tree, and variable subset selection is automatic. Trees are intrinsically robust to outliers because splits depend on the ordering of values, not their magnitudes. Yet they are sensitive to changes in the data, where even a slight change can produce very different splits. They are nonlinear and non-parametric, accommodating a wide range of relationships. But because splits consider one predictor at a time rather than combinations, trees miss relationships between predictors, especially linear structures. When 2 classes separate best along a diagonal line, a tree of horizontal and vertical splits performs worse than discriminate analysis. They need large data sets for good classifiers and are computationally expensive to grow, with overfitting avoidance methods adding more. They favor predictors with many split points, categorical variables with many categories, and numerics with many distinct values. A bias that binning and category combining mitigate, in which the two-step conditional inference and quest algorithms avoid by testing predictors before picking split points. They handle missing data without imputation, and their transparent rules are a practical advantage in managerial settings, an advantage lost in the ensemble versions. Advantages: off-the-shelf strength, automatic variable selection, transformation robustness, outlier robustness, missing data handling, transparent rules. Weaknesses: instability, one predictor at a time splits that miss diagonal, joint, structure, large data need, slow growth, and a bias toward many split-point predictors. Strengths: interpretable per predictor contributions, simple, parsimonious, robust to minor violations, strong on small samples. Weaknesses: normality and equal covariance assumptions, outlier sensitivity, mitigated by transformation and variable choices. Improving prediction: random forests and boosted trees. In a pure prediction application, the transparency of a single tree matters less than raw performance, and both come from combining many trees, ensembles. Random forests, introduced by Bryman and Cutler as a special case of bagging, draw multiple bootstrap samples with replacement from the data, fit a tree to each sample using a random subset of predictors at each split, and combine by voting, classification, or averaging prediction. On the lone data, a forest of 500 trees achieves holdout accuracy 0.982, matching the fine-tuned single tree. The forest cannot be drawn as a single transparent diagram, but produces variable importance scores, the sum Gini decrease attributable to each predictor across all trees, showing income and education dominant, CC average third, and the rest far behind. Boosted trees take a different route. Each successive tree concentrates on the records the previous tree misclassified by sampling with higher probabilities those misclassified records, then voting with heavier weight on the later trees. On the lone data, the boosted tree, XGB classifier, reaches holdout accuracy 0.9830, and its special talent is the rare class, where one class dominates, over 90% here. Basic classifiers are tempted to call everything the majority class, and the ones become most of the misclassifications. Boosting concentrates exactly there, cutting misclassified ones from 43, single small tree, to 27 in the holdout. The ROC curves confirm it. The boosted model has the highest sensitivity at high specificity, and tuning with the scale-plus weight argument focuses training on the rare class and improves the curve further. Random forests. Bag trees on bootstrap samples with random predictor subsets, combined by vote/average. Variable importance, sums Gini decrease. Boosted trees. Sequential trees re-weight the misclassified records, sharpening the rare class of interest, 4327 missed acceptors. Quote, one of the reasons that tree classifiers are very popular is that they provide easily understandable decision rules, at least if the trees are not too large. Chapter 10. Logistic Regression. Introduction. Logistic regression extends linear regression to a categorical outcome, where the aim of multiple linear regression is to predict a continuous value. Logistic regression's goal is to predict which class a new record belongs to, or to compute its propensity, the probability of membership in each class, so records can be ranked and acted on. It serves both classification and profiling, classifying customers as returning or non-returning, or predicting loan approval from credit scores, or, where the class is known, finding which predictors distinguish classes, such as what differentiates male from female top executives. The model demands that the user specify the predictors in their form, which means even small datasets can support it, and, once estimated, it classifies large samples of new records cheaply and fast. An obvious shortcut, the linear probability model, linear regression on a zero-first outcome, fails. Its predictions are not proper probabilities, useful only for comparison with a cutoff. Logistic regression proceeds in two steps. First, estimate the propensity for a binary outcome, p equals p of y equals 1, which also gives P of y equals 0. Then apply a cutoff, a default 0.5, but a lower cutoff when class 1 is a low probability but important event like a fraudulent transaction. The logistic regression model. The idea is to model the logit, a function of the probability, as a linear function of the predictors, then map the predicted logit back to a probability. Starting from P, the probability of class 1, a linear function of the predictors would not guarantee values in the interval 0, 1. So the logistic response function wraps it in a nonlinear form that always stays inside the unit interval. Related to the probability is the odds, the ratio of the probability of class 1 to the probability of class 0, a metric familiar from horse racing and epidemiology. Given the odds, the probability is recovered by inversion. The relationship between odds and predictors is multiplicative. A unit increase in a predictor is associated with a multiplicative change in the odds, interpretable in percentage terms. Taking the natural logarithm of the odds yields the logit, which ranges from very low values, low odds, to very high values, high odds, with a logit of 0 corresponding to even odds, probability 0.5. The logit is what is modeled linearly. Logit, the log odds, modeled linearly in the predictors and mapped back to a probability via the logistic response function. Odds, the probability ratio of class 1 to class 0, multiplicative in predictors, so coefficients read as odds multipliers. Example, acceptance of personal loan. The universal bank example returns 5,000 customers, 9.6% accepting a loan offer, with the goal of identifying who is most likely to accept in future mailings. A single predictor model with income yields the familiar S-shaped probability curve, and the customer is classified as an acceptor if the estimated probability clears the cutoff. The parameters are estimated not by least squares, but by maximum likelihood, finding the estimates that maximize the chance of obtaining the data we have, requiring iteration. Estimation is less robust than for linear regression. It is reliable for well-behaved datasets where both outcome classes are well represented. Their ratio is not extreme, and the number of coefficients stays small relative to the sample, no more than about 10%. Collinearity among predictors causes computational difficulty, as it does in linear regression. Pre-processing for the full model converts education, 3 levels, into 2 dummies. 3 would create multicollinearity, and with 6 numerical predictors and the other 4 categorical predictors, yields 12 predictors total. The fitted model's signs tell the story. Positive dummy coefficients for graduate and professional education, CD account, and online banking raise acceptance probability. A securities account and a universal bank credit card lower it. Among continuous predictors, higher income raises it and older age lowers it. AIC gives a compact fit summary. For profiling, odds are the right currency. Because odds are multiplicative in the predictors, a 1-unit increase in a predictor, holding others constant, multiplies the odds by e to the beta. For a dummy, this is the odds ratio relative to the reference category. A customer who holds a CD account has odds of acceptance multiplied by e to the 3.65 approximate 38 relative to one who does not, everything else constant. The advantage of odds over probabilities. These statements hold for any predictor value, whereas a 1-unit change in a predictor changes the probability by an amount that depends on the current probability. Increasing income from 3 to 4 shifts P differently than from 30 to 31. Probabilities are therefore only discussed for specific records, while odds support general coefficient interpretation. Maximum likelihood. Parameters are found by maximizing the chance of the observed data, needing iteration. Reliability requires balanced classes and few coefficients. Odds interpretation. A CD account multiplies acceptance odds by roughly e to the 3.65. Odd statements hold for any predictor value. Probability statements do not. Evaluating classification performance. The measures of Chapter 5 apply directly. Predictions come from the estimated equation. Predict each holdout record's logit, convert to a probability, and classify by the cutoff. The worked example shows 4 holdout customers, 2 correctly classified, a non-acceptor at 0.02 probability, an acceptor at 0.97. 2 misclassified, a non-acceptor wrongly given a 0.67 propensity, an acceptor wrongly given a 0.011, illustrating both error directions. The cumulative gains and decile-wise lift charts for the holdout set quantify the ranking value. The 10% of records ranked most likely to accept yield 7.8 times as many acceptors as a random 10%. Confusion matrix and lift assessment. Holdout propensities plus cutoff give classifications. Gains and lift charts quantify ranking value. Top decile is almost equal to 7.8 times random. Variable selection. Model search proceeds by trying simpler models, fewer predictors, or richer ones. Interaction terms such as income by family. The choice is guided primarily by performance on the validation data, for which simpler models are preferred when performance is roughly equal, and the honest caveat that validation selected performance is optimistic because the validation data have entered the model selection process. A reserve holdout set measures the final choice on unseen data, or variable selection runs on the training set with cross-validation. The same heuristics as linear regression apply, stepwise, forward, backward, optionally minimizing AIC, and regularization with L1 or L2 penalties. An L2 penalty with an enormous C reproduces ordinary logistic regression. Logistic regression for multi-class classification. The binary model extends to more than 2 classes. With G classes, each record has G probabilities that sum to 1, so only G minus 1 need estimation. For ordinal classes, those with a meaningful order, like buy, hold, sell, the proportional odds or cumulative logit, method models the cumulative probabilities, the probability of buy, then the probability of buy or hold. Each is a linear function of the predictors sharing the same slope but different intercepts. Class membership probabilities are recovered from the cumulative ones, and the record is assigned to the class with the highest probability. For nominal classes, unordered, like brands of cereal, one class serves as reference and G minus 1 pseudologid equations are formed, each modeled linearly with its own coefficients. The two models differ, as the accidents data, severity as no injury, non-fatal, fatal, show. The ordinal fit has 2 intercepts and 1 coefficient set for the predictors. The nominal fit has 3 intercepts and 3 separate coefficient sets, and the predicted probabilities differ, so the analyst must judge which coding suits the outcome and validate accordingly. Ordinal cumulative logit 1 slope, class-specific intercepts on cumulative probabilities, e.g., buy or hold. Nominal, a reference class plus G minus 1 pseudologits, each with its own coefficients. The 2 codings yield different probabilities and fits. Example of complete analysis, predicting delayed flights. The full worked example predicts delays, more than 15 minutes late. On the 22:01 Washington-New York flights of January 2004, 19.5% delayed from 6 predictors. Day of week, departure time and hourly bins, origin, destination, carrier, and whether there was weather-related delay. 34 dummies after pre-processing with reference categories set. ID, LGA, U.S. Airways, Wednesday. The coefficient table is read through odds. Flights to EWR are more likely delayed than to JFK. Among carriers, U.S. Airways has the lowest odds of delay and MQ the highest. Monday has the highest odds across days. Delays climb through the day, most noticeably at 7 to 8 p.m., and weather carries the largest coefficient, marking the huge gap between weather-affected and clear flights. The authors deliberately skip statistical significance. The goal is prediction, so predictive performance governs. Evaluation uses the holdout confusion matrix and gains chart. The full model reaches 83.09% accuracy, classifying on-time flights far better than delayed ones, and the same pattern in training data, so it is no surprise. The real use of the model is ranking flights by delay probability under limited resources, controllers opening routes, airlines activating standby crews, hotels freeing space for stranded travelers. The gains curve shows the model beats random selection. Variable selection then exploits the data. Most carriers fly from a single airport and delay rates match across airports. So origin dummies are dropped without hurting fit. Destination is dropped for a practical reason. Not all carriers fly to all airports, so the model would be asked to predict impossible combinations. Days group in as Sunday plus Monday versus the rest. Carriers and hours condense into a few dummies. The reduced 7-predictor model, sun_mon, weather, a carrier group, and 4 time-of-day dummies, matches the full model's accuracy, 83.43%, and gains at a fraction of the information, and Lasso with L1 penalty produces 19 non-zero variables. The chapter closes with a critical flag. The weather variable records actual weather at flight time, not a forecast, so a model that truly predicts delays in advance must drop it, while a profiling model may keep it to evaluate the other factors with weather held constant. The bottom line from January 2004. The highest chance of an on-time flight is Tuesday through Saturday around noon on Delta, Comair, United or U.S. Airways, and of course, good weather is advantageous. The stats model's appendix is the mirror of chapter success. Small GLM with the binomial family gives the full inferential output for genuinely explanatory purposes, and logic fit and regularized applies the same L1 penalty. Coefficients as odds. EWR more delayed than JFK. U.S. Airways lowest delay odds. MQ highest, whether the largest coefficient. Reduction. Dropping origin and destination dummies and condensing days/hours/carriers preserves accuracy, 83.4%, with a fraction of the predictors. Weather caveat. The weather predictor is actual at flight time, so a genuinely predictive, in advance, model must drop it. Quote, the advantage of reporting results in odds as opposed to probabilities is that statements such as those above are true for any value of xj. Unless xj is a dummy variable, we cannot apply such statements about the effect of increasing xj by a single unit to probabilities. This is because the result depends on the actual value of xj. The change in the probability, p, for a unit increase in a particular predictor variable, while holding all other predictors constant, is not a constant. It depends on the specific values of the predictor variables. Chapter 11. Neural Nets. Introduction. Neural networks, also called artificial neural networks, are models for classification and prediction, loosely inspired by the interconnected, experience-learning neurons of the brain. They mimic the way human experts learn and have a capacity to generalize from particulars. They began to be applied successfully in the late 1990s in bankruptcy trading and fraud detection, and took off in the early 2000s as networks grew more complex and computers more powerful. What the public calls artificial intelligence is, at its heart, deep multi-layer neural networks. The lineage runs further back than most realize. An autonomous vehicle application from the 1980s, Alvin, steer a highway car from a 30 by 32 grid of camera pixel intensities, outputting one of 30 steering classes from sharp left to bare right. The main strength of the network is high predictive performance. Its structure captures very complex predictor, outcome relationships that other predictive models cannot. Concept and structure of a neural network. The idea is to combine predictor information flexibly enough to capture complicated relationships. In linear regression, the form of the relationship is specified directly by the user, and no amount of transformations and interactions escapes the assumption of linearity. In a neural network, the user specifies no form at all. The network learns the relationship from the data. Linear and logistic regression can themselves be seen as special cases of very simple networks with input, output, and no hidden layers. The most successful architecture is the multi-layer feed-forward network, an input layer of nodes, neurons, that simply accept the predictor values, successive layers of nodes that receive input from the previous layer, and a final output layer. The layers in between are hidden layers. Feed-forward means fully connected, one-way flow, no cycles. A classification problem with G classes uses G output nodes. Multi-layer feed-forward, input, hidden, and output layers of nodes. Fully connected, one-way flow, no cycles. Linear and logistic regression are zero hidden layer special cases, fitting a network to data. The tiny cheese tasting example: 6 consumers, 2 predictors, fat and salt scores, and a like/dislike outcome, makes every computation visible. Nodes N1 and N2 input the predictors. Hidden nodes N3, N5 each take a weighted sum of the inputs plus a bias term, a constant controlling the node's level of contribution. Then apply an activation function. The output node N6 does the same on the hidden node's outputs, producing the propensity of like. The activation function matters. Examples of the linear function, an exponential function, and the logistic/sigmoidal function. The most popular because it squashes very small and very large values while staying nearly linear between 0.1 and 0.9. Deep learning mostly uses the rectified linear unit, ReLU, or its variants, identical to the linear function but 0 below 0. Weights and biases start as small random numbers, a state of known knowledge, like a model with no predictors, and the first record's actual arithmetic is shown, with initial weights and bias. The hidden nodes weighted some feeds through the logistic function to an output. With additional hidden layers, the inputs to each layer are simply the outputs of the preceding one. For classification with more than 2 classes, the output node with the largest value wins. 2 striking equivalences close the mechanics. A network with a single output node, no hidden layers, and the identity activation function is exactly multiple linear regression. With the logistic activation function on a binary outcome, it is exactly logistic regression. The formulations coincide, but the estimates differ because the neural network learns by a different estimation method. Because sigmoidal activations work best on a bounded scale, all variables are rescaled to 0, 1, or -1, 1 before training, subtracting the minimum and dividing by the range, with the option of a log transform for the many right-skewed business variables like income before rescaling. Binary variables need only dummies. Ordinal categories map to fractions reflecting their ordering. Nominal categories become dummies. Training means estimating the weights and biases that give the best predictions. The forward pass computes predictions for each training record. The errors feed backward, and each hidden node is assigned responsibility for part of the error, which then updates its weights. This is backpropagation. Each weight updates by an amount controlled by the learning rate or weight decay, typically between 0 and 1. Case updating adjusts weights after each record, a trial. Batch updating after the whole training set. Case updating is more accurate but slower, and hundreds or thousands of sweeps, epochs, through the training data are routine. The process is an example of gradient descent. Repeatedly take small steps downhill on the error surface, and if a step improves, continue. The procedure can trap the network in a local minimum and stochastic gradient descent, shuffling the data so random noise jiggles the search, helps escape. Updating stops when the new weights change only incrementally, when a misclassification rate hits a threshold or stops improving across epochs, early stopping, or when the iteration limit is reached. Scikit-learn provides the basic networks, Keras, PyTorch, and TensorFlow the deep ones. The accidents example, 3,840 records, severity classes no injury/injury/fatality, 7 predictor dummies, shows the architecture decision in action. A single hidden layer, with 2 hidden nodes giving the best balance between training improvement and validation performance. More nodes performed no better and added complexity. The 2-node network classifies classes 0 and 1 perfectly in training and validation, but misclassifies class 2 heavily. A familiar note that rare classes remain hard. Overfitting is a genuine weakness. Networks can fit the training data so well that holdout and new data air balloons. The antidote is to limit training iterations and detect overfitting by monitoring validation, or cross-validation. Error, which falls in the early epochs, and then begins to rise as training error still improves. The minimum validation error marks the best stopping point. For numerical outcomes, the output is back-transformed from its scaled range, transform target regressor with a min-max scaler. For binary outcomes, propensities in a network tend to cluster around 0.5. So the validation set rather than a hard 0.5 is a better place to choose the cutoff. For G classes, the largest output wins. And when classes are not mutually exclusive like race, the outputs need not sum to 1. Activation functions. The logistic sigmoid squashes inputs and stays near linear mid-range. ReLU dominates deep learning. Backpropagation. Errors from the output layer update hidden weights, scaled by a learning rate. Case or batch updating over many epochs. Preprocessing. Scale inputs to 0, 1, or -1, 1. Dummy categoricals. Log transform right skew predictors. Overfitting control. Limit iterations. The minimum validation error marks the best stopping epoch. Binary propensities cluster near 0.5, so validate the cutoff rather than assuming 0.5. Required user input. Architecture choice. The number of hidden layers and nodes remains trial and error guided by past experience, with no clearly superior automatic method. The guidelines are concrete. One hidden layer is usually sufficient, even for very complex relationships. The number of hidden nodes sets the complexity of the relationship, trading underfitting against overfitting, with a rule of thumb of starting with P, the number of predictors, and adjusting while checking for overfitting. Output nodes number G for G classes or 1 for numerical outcome. Predictor choice deserves careful attention because networks depend on the quality of their input. Domain knowledge, feature selection, and dimension reduction should precede the network. The learning rate, weight decay, is the key user-tunable parameter, used primarily to avoid overfitting by downweighting new information, toning down outliers, and avoiding local optima. The practical advice is to start large, learning quickly from the data, and decay it through the iterations, with the rule of thumb of setting it to 1 over the current iteration number. Architecture. One hidden layer usually suffices. Node count trades under, against overfitting, starting around P predictors. G output nodes for G classes. Learning rate. Weight decay downweights new information to avoid overfitting and local optima. Start large and decay. Exploring the relationship between predictors and outcome. Networks are black boxes. Their output sheds no light on the patterns they model, and that opacity is the biggest criticism of the method. But a sensitivity analysis on the holdout set can reveal the capture relationships. Set all predictors to their means and record the prediction. Then repeat with each predictor at its minimum and then its maximum. Comparing the predictions across levels shows which predictors move the output and how. Sensitivity analysis. Vary each predictor from minimum to maximum, others at their mean, and observe how predictions move. The black box's only native window. Deep learning. Deep learning arrived with Geoffrey Hinton's 2006 paper and the realization that complex multilayer networks could perform dimension reduction and feature discovery on their own. For structured business data, the predictive features already exist. For voice and image recognition, they do not. All theirs are low-level sound wave amplitudes or pixel intensities. Deep learning learns the higher-level features itself. The key innovation examined is convolution. In a standard network, each predictor gets its own weight at each layer. A convolution selects a subset of pixels and applies the same operation to the whole subset. This grouping is what fosters automated feature discovery. On a line drawing of a man's chin, a small 3 by 3 filter of pixel values applied to a 3 by 3 image section, combining with a filter matrix good at detecting vertical lines, produces a high sum. Evidence the filter has found a vertical line, which consolidates 9 pixel values into one number. The filter then slides across and down the image. Stride determines how far, producing a smaller feature map that answers, is there a vertical line in this section? Different local filters find horizontal lines, diagonals, curves, boundaries. Further convolution layers take these feature maps as inputs and successively build corners, rectangles, circles, and ever higher features, progressively compressing the information into tensors of abstract high-level features, so abstract that one cannot peer into a deep network and point at an eye. The net learns which convolutions to retain, simply those that lead to successful classification. Faces, for example, are found by keeping the hierarchies, edges to circles to eyes, that classify labeled face images correctly and dropping the rest. Sometimes a single node's output becomes an effective classifier by itself. Most strikingly, deep learning also identifies features and objects unsupervised. Autoencoder networks are trained to reproduce their own input. They compress the data to a low-dimensional bottleneck of learned features, expand those features back into an image, and compare the reconstruction with the input, working with backpropagation until the reconstructions match, all without labeled data. The bottlenecks learned features, a low-dimensional representation analogous to principal components, are then useful for supervised prediction or unsupervised clustering. The fashionist example, 60,000 grayscale 28 by 28 clothing images, 10 classes, shows a full convolutional architecture in Keras. 2NV2D layers with 32 and 64 filters and ReLU activation, max pooling, dropout layers to resist overfitting, a flattened, 2 dense layers, and a softmax output, over 1 million parameters. Trained with the Atom Optimizer on categorical cross-entropy, the network reaches 92.5% validation accuracy, with shirts, class 6, the hardest confused with t-shirts, pullovers, dresses, and coats. The companion box on double descent explains why such parameter-heavy models work at all. As parameters approach the number of records, holdout error peaks, but beyond that point it falls again because the model automates feature reduction and consolidation even when parameters outnumber records. Deep learning's other families, the recurrent networks of LSTM and GRU for time series, text, speech, and clickstreams, where order matters, are summarized, and the closing counsel is practical. Weigh performance against other methods and their data and computing requirements. Convolution. A shared filter slides over a pixel grid, consolidating local patches into feature maps that build ever higher features, line shapes eyes. Autoencoders compress data to a bottleneck and reconstruct it, learning features unsupervised, a principal components like representation. Double descent. Error peaks near the parameter record boundary, then falls again. Deep nets cope even when parameters exceed records. Advantages and weaknesses of neural networks. The prominent advantage is predictive performance, high tolerance to noisy data, and the ability to capture highly complicated relationships between predictors and outcome. The weak point is insight, the black box reputation. 3 dangers deserve attention. Extrapolation beyond the scene predictor range produces completely invalid predictions. The flexibility demands sufficient data for training and sufficient minority class records, obtained by oversampling. And computation time, which grows sharply with the number of predictors, must be measured wherever real-time prediction is required, so it does not delay decision-making. Strengths. High predictive power, tolerance of noise, capture of very complex relationships. Weaknesses. Black box opacity, dangerous extrapolation, heavy data and minority class needs, and computation time that grows with predictors. Quote, neural networks mimic the way the human experts learn. The learning and memory properties of neural networks resemble the properties of human learning and memory, and they also have a capacity to generalize from particulars. Chapter 12. Discriminate Analysis. Introduction. Discriminate analysis is a classical statistical classification method, used like logistic regression for both classification and profiling. Its applications are remarkably broad, classifying organisms into species, loan and credit card applications into risk categories, customers into early adopters, bonds into rating categories, skulls by fossil type, disputed authorship, college admission, alcoholics versus non-alcoholics in medical studies, and fingerprints. The chapter returns to the riding mowers and personal loan examples and closes with a 3-class accident example. The motivating intuition. A linear classification rule is a line separating owners from non-owners, and the question is whether a better line than the ad hoc one, for misclassifications out of 24 in the mower data, can be found. In today's applications, the classes rarely separate cleanly. The universal bank acceptors and non-acceptors overlap heavily on income and spending, even across all 5,000 records. Distance of a record from a class. The general idea is to classify a record to the closest class, measured by distance from the record to the class mean. Loan acceptors average $144.75 thousand income. Non-acceptors $66.24 thousand. So a customer with income X is classified by which class mean is nearer. With several predictors, the class mean becomes the centroid, the vector of means, and distance is the Euclidean distance from the record to the centroid. But Euclidean distance has three flaws. It depends on the units of measurement. Dollars versus thousands of dollars change the answer. It ignores variability. Acceptor's income is less variable, $31.6 thousand standard deviation versus $40.6 thousand for non-acceptors. So if a customer nearer the acceptor's mean in dollars may just as likely be a non-acceptor once that spread is considered. Distance should be measured in standard deviations, in effect z-scores. And it ignores correlation between predictors. So variables that are individually good discriminators but redundant in the presence of others still count fully. The statistical distance, or Mahalanobis distance, fixes all three. It is the Euclidean form re-weighted by the inverse of the covariance matrix, so it accounts for each variable's spread and for the correlations among predictors. With a single predictor, it reduces to a squared z-score. Discriminant analysis uses statistical distance to find a separating line or hyperplane equally distant from the class means, measuring each record's statistical distance to every class and allocating it to the nearest. Classify to nearest. Distance from centroid, class mean vector, decides. Euclidean distance is scale dash, variance dash, and correlation blind. Statistical, Mahalanobis, distance, inverse covariance weighted, folding in spread and correlation, reduces to a z-score for one predictor. Fisher's linear classification functions. R.A. Fisher's 1936 linear classification functions find linear functions of the measurements that maximize the ratio of between-class to within-class variability, classes that are very homogeneous and differ the most from each other. For each record, the functions yield scores measuring its proximity to each class, and the record is assigned to the class with the highest score, equivalently, the smallest statistical distance. In scikit-learn's two-class output, one decision function, the difference of the two classification functions, is returned and the sign decides, positive to class 1, negative to class 0. In multi-class problems, each class gets its own function and the highest score wins. On the mower data, the decision function's weights give the first household income $60,000, lot 18.4, a negative score, misclassified as a non-owner. The full table shows three misclassifications against the ad hoc lines 4. Alternatively, the classification scores convert to class propensities via the standard formula, and a cutoff of 0.5 is equivalent to picking the highest score, with the bonus that propensities support ranking and lift curves. Scikit-learn exposes all three: decision scores, predictions, and propensities. Fisher's functions, linear combinations maximizing between to within-class variability. The highest classification score, or decision function sign, assigns the class. Propensity conversion, scores convert to class probabilities. A 0.5 cutoff equals picking the highest score, and propensities enable ranking and lift. Classification performance of discriminant analysis. The method rests on two assumptions. First, the predictors come from a multivariate normal distribution within every class. And when this holds, discriminant analysis is a more powerful tool than logistic regression. Efron, 1975, showed it 30% more efficient, needing 30% fewer records for the same results. In practice, it is robust to departures from normality. Even dummy variables are tolerable as long as the smallest class exceeds roughly 20 records, but it is sensitive to outliers, so exploratory analysis should locate and possibly eliminate extreme cases. Second, the correlation structure among predictors is the same across classes. This can be checked by comparing per-class correlation matrices. If the correlations differ substantially, the classifier tends to shunt records into the class with the largest variability. With a large dataset, quadratic discriminant analysis becomes the alternative. The predictive mindset reminder applies. The ultimate test is empirical. Explore, train, evaluate, and circle back on outliers and predictors as accuracy suggests. Evaluation uses the Chapter 5 machinery, confusion matrix with or without costs, lift and gains for ranking, always on a holdout set. The Mower model's 12.5% error rate on the data used to fit it is optimistic because the same records fitted the classification functions and estimated the error. Normality assumption, multivariate normal predictors per class, then 30% more efficient than logistic regression, 30% fewer records. Equal covariances, correlations should match across classes, outliers need handling, evaluation still on holdout. Prior probabilities. So far the objective is minimum classification error, assuming future records arise at the training set class proportions. When the future proportions differ, say mower owners are 15% of the population but 50% of the oversampled training set, the model should classify fewer records as owners. Setting the priors argument adjusts the functions so that family 13, misclassified as an owner under equal priors, is correctly classified as a non-owner under population priors. Priors argument. When future class proportions differ from the sample, e.g., 15% owners versus 50% sampled, resetting priors reclassifies borderline records. Unequal misclassification costs. When misclassifying a Class 1 record, costs vary differently from misclassifying a Class 2 record. The goal shifts to minimizing expected misclassification cost rather than error rate. In the two-class case, the classification functions are modified by the pairwise products of prior probabilities and misclassification costs. In practice, the absolute costs are hard to estimate, but their ratio is not. The classification functions depend only on the ratio of costs, and, when needed, the ratio of priors, which is why software so often prompt for ratios. Cost-modified functions. Prior times cost products feed the classification functions. Only the cost ratio matters, so software asks for ratios. Classifying more than two classes. The medical dispatch example classifies accidents into no injury, non-fatal, and fatal from initial call information, useful for deciding which units to send under ambiguous, resource-strapped conditions. With three classes, there are three classification functions rather than one decision function, and the 3x3 confusion matrix tracks all correct and incorrect combinations. The rule is unchanged. Compute each class score from its coefficients and assign to the highest. The first accident, with no injury score -0.46, beating non-fatal -0.96, and fatal -5.94, is correctly classified as no injury. Propensities come from the same scores to probabilities relation as the two-class case, and again the highest probability decides. The overall accuracy, 0.5283, is modest, reflecting the inherent difficulty of the task. Three classes, three functions. Each class gets a score and a propensity. The highest score/class wins. The 3x3 confusion matrix tracks all error types. Advantages and weaknesses. Discriminate analysis straddles the boundary between statistics and machine learning. Often absent or barely mentioned in machine learning resources, yet very popular in the social sciences and effective in practice. It shares the character of linear regression. It searches for the optimal weighting of predictors, here for separating classes rather than predicting a numerical outcome, uses least squares, and is robust to local optima. Its underlying assumption is approximate multivariate normality, and though violated often, binary predictors, it is surprisingly robust because, as Hasty et al. Suggest, data usually support only simple linear separation boundaries. Skewed continuous variables can be log transformed and outliers removed. As a classifier, it yields per predictor importance for ranking and variable selection. Finally, it is computationally simple, parsimonious, and especially strong on small datasets. Its parametric form makes the most of limited data. Quote, when this assumption is reasonably met, discriminate analysis is a more powerful tool than other classification methods, such as logistic regression. In fact, Efron, 1975, showed that discriminant analysis is 30% more efficient than logistic regression if the data are multivariate normal, in the sense that we require 30% less records to arrive at the same results. Chapter 13. Generating, comparing, and combining multiple models. Ensembles. Ensembles made their public debut in the $1 Million Netflix Prize Contest of 2006. Netflix offered its anonymous movie rating data and a prize for a recommendation algorithm beating its own Cinematch by 10%, and an active leaderboard soon revealed an odd behavior. Teams joined forces and combined. Ensemble. Predictions proved more accurate than any individuals. The winning team, Belcour's Pragmatic Chaos, described the lesson directly. If two prediction sets achieved similar RMSEs, it was quicker to average the two than to build a new model, and even a plainly worse set had some linear combination that improved the better one. The underlying logic is the wisdom of crowds. Francis Galton watched a county fair contest to guess an ox's weight. Individual guesses varied wildly, but the mean of all guesses was within 1% of the true weight. The errors canceled. In modeling, risk is variation in prediction error. If two models each have errors averaging 0, the average of their predictions still has 0 mean error, but its variance can be much smaller than either alone. Smaller still when the errors are negatively correlated. Averaging several models, therefore, tends to improve predictive power, most of the time, if not always. The simplest ensemble is plain averaging or voting. For numerical outcome, average the predictions of, say, a linear regression, a regression tree, and AK, an in-model, or 3 regressions using different predictor sets. The median is less affected by extreme predictions, and a weighted average can weight by model accuracy or data quality. Forecasts combine the same way. The weather app Dark Sky aggregated many data sources to provide the most accurate forecast possible. For classification, vote. The most popular class among the classifiers wins, with a weighted majority rule possible. Propensities average like predictions, with the caveat that algorithms like naive Bayes produce biased propensities and should not be simply averaged with others. Bagging, bootstrap aggregating. Averages across random data samples. Draw multiple bootstrap samples with replacement, run the algorithm on each, and combine the results. It stabilizes performance and resists overfitting by modeling different data samples separately, so it suits unstable, flexible methods like trees and neural networks. Boosting takes the opposite tack, sequential rather than parallel. Fit a model, draw a sample that overweights the misclassified or high error, records, refit, and repeat, so each new model is forced to attend to where the previous one failed. Both work on any method, but are most effective and most commonly applied to trees. On the personal loan data, both the bagged and boosted trees beat the single decision tree on holdout accuracy and ROC, and random forest and XGBoost do likewise. Stacking stack generalization is the heterogeneous variant. Fit different base learner algorithms, build a new dataset whose predictors are just their predictions, plus the target, and fit a meta-learner, the stacking model learner, on that. Scikit-learn's stacking classifier and stacking regressor, MulkStend, and H2O's AutoML all implement it. Federated learning adapts the ensemble idea to privacy. A central model is shared with client organizations. Each retrains it on its own data without sharing the data, and the model parameters, not the predictions, are combined centrally. The accuracy falls somewhat short of training on all data together, but the gain over siloed clients is substantial and essential where confidentiality rules. The ensemble approach is most useful when the combined model's prediction errors are negatively associated, though it helps even with low correlation. Sample-based ensembles resist overfitting, yet one can still overfit an ensemble by tuning it, choosing best weights on the same data that evaluated it. The costs are resources, computation, software, analyst time, and a black box outcome. Combining models usually makes the predictor-outcome relationship non-transparent. Why ensembling works. Averaging prediction errors of 0 mean reduces error variance, all the more when errors are negatively correlated. The wisdom of crowds. Simple models. Average predictions or medians. Vote on classes, average propensities, with caveats. Naive-based propensities are biased. Bagging versus boosting. Bagging averages bootstrap samples to stabilize. Boosting reweights misclassified records to sharpen them. Stacking and federated learning. Base learner predictions feed a metamodel. Privacy-preserving model parameter sharing across clients. Automated machine learning, AutoML. AutoML automates the whole workflow, from data loading to a rank-ordered list of candidate models with automatic parameter tuning. Scikit-learn's consistent interface already makes it easy to train and compare many models by hand, but packages like H2O provide a complete implementation. The steps mirror the Chapter 2 process. Data exploration and cleaning remain largely manual, since they rightly require domain knowledge. H2O runs data processing and model building on a separate cluster server, which permits specialized hardware. The task is chosen by the outcomes type, converting the outcome to a factor signals classification, leaving it numeric signals regression, and imbalanced data can be handled with class balancing. Here, 90% no versus 10% yes. So models are built with and without balancing. Feature choice still must respect data quality and regulatory ethical limits. Gender is a forbidden predictor in U.S. loan applications, and algorithm choice must weigh runtime and suitability. H2O AutoML then trains up to a fixed number of models, here 20, excluding deep learning for reproducibility, adding stacked ensembles, and reports cross-validated performance on a leaderboard. On the loan data, a gradient boosting model led the imbalanced run and a random forest the balanced one, with the imbalanced model performing better on holdout, showing how inevitably the balance choice matters. Deployment entails engineering. Fix package versions, add tests comparing predictions against the expected outcome after environment changes, apply the same pre-processing to new data, pipeline. Read large datasets from databases via Sclalchemy or SQLite 3, and consider parallelization or clusters for heavy workloads, or wrap the model in a web application with Django's framework or FastAPI. The advantages of AutoML are real. Beginners get a fast starting point. Advanced users save time on common workflows, and by analyzing the finally chosen model, the data scientist can redirect effort toward data understanding, preparation, and feature generation. The disadvantage is its deceptive ease. Because results come quickly, analysts may skimp on the data understanding that guards against garbage in, garbage out, producing thoughtless models. AutoML automates loading, feature selection, model training, tuning, and a ranked leaderboard. H2O trains up to a budget of models plus stacked ensembles. Trade-off: saves time and gives beginners a start, but can hide the data understanding that prevents garbage in, garbage out. Explaining model predictions. Explainability matters most where predicted scores must be justified, loan and judicial decisions. And it answers two questions: how the predicted score is affected by the predictor values, descriptive, and how changing those values would change the score, causal. LIME, local interpretable model-agnostic explanations, explains individual records by generating synthetic neighbors. Copy the record. Randomly perturb each variable. Predict each neighbor, then fit a linear regression on those neighbors and their predictions. The resulting local correlations show how much each predictor contributed to that record's prediction. Useful even when the global relationship is nonlinear, because locally the relationship is approximately linear and the information genuinely differs from record to record. Thinking of the model as a black box, you poke the inputs, watch the output, and learn which inputs correlate with it. On the lone random forest, LIME shows that for high-propensity predictions, income, education, and average credit card spending carry the decision. For borderline cases, propensity near 0.6, a small change flips the classification. Raising one customer's income from $81K to $90K turns a no into a yes. Lowering another's from $125K to $114 turns a yes into a no. Such granular explanations build stakeholder trust in black box models and matter most where a predictor like a CD account is decisive for some customers, but irrelevant to others. At the opposite end from global feature importance measures, which summarize a predictor's overall contribution over a holdout set. Lime, perturb a record's neighbors, predict them, and fit a local linear model. Local correlations attribute each prediction's drivers, record by record. Summary. The methods of the book are building blocks used in an analytic process whose goal is to inform and provide insight. This chapter shows 3 ways the blocks combine. Ensembles, where multiple models are weighted and combined into improved predictions. Automated machine learning, which accelerates selecting, applying, and tuning many models while the analyst concentrates on evaluating and comparing results. And explanation tools like Lime, which restore the transparency that complex models give up. The through line is that as models grow more complex, the machinery for choosing, combining, and understanding them must grow too. Quote, an early lesson of the competition was the value of combining sets of predictions from multiple models or algorithms. If 2 prediction sets achieved similar RMSEs, it was quicker and more effective to simply average the 2 sets than to try to develop a new model that incorporated the best of each method. Even if the RMSE for one set was much worse than the other, there was almost certainly a linear combination that improved on the better set. Chapter 14. Interventions, Experiments, Uplift Models, and Reinforcement Learning. A/B testing. Supervised and unsupervised learning work on observational data, passively collected about customers, households, transactions, flights. This chapter introduces a third paradigm. Experimental data, produced by applying interventions to the entities of interest and measuring the outcomes. The simplest intervention is the A/B test, a randomized experiment testing the causal effect of a treatment on an outcome, routinely used by Google, Microsoft, and Uber to test new features. A treatment is whatever is tested: a drug, an email, an ad, a web page, and random allocation is the essence. Because subjects are assigned randomly, any difference between groups can be attributed to the treatment rather than to pre-existing differences. A magazine display ad would not qualify unless a call to action lets the marketer trace a purchase to the ad and the magazine copies were randomly split. The power of the randomized experiment is matched by its economy. Only 2 measurements per subject, which treatment and what outcome. And for a binary outcome, only the proportion in each group is needed. The Photo2 example, 2,000 users, half seeing a new disappearing photo feature, shows the question. The feature raises both photo uploads and conversion to paid users, but is the difference a signal or a fluke sample? The t-test answers it, comparing an observed difference against what chance would produce. If a chance model produces a result at least as unusual only 5% of the time, the difference is statistically significant. If it happens 35% of the time by chance, stick with the standard. For Photo2, uploads give a p-value of 0.0024 and conversion 0.0044, small enough to generalize. A critical footnote accompanies the machinery. Statistical significance is hostage to sample size, so on huge A/B test samples, even a practically meaningless 5.000001% versus 5% difference will appear significant. The magnitude and business meaning must be weighed separately. A/B/N testing extends the design to several groups, replacing the t-test with ANOVA, numerical outcome, or a chi-square test, proportions. The deeper hazard is multiple testing. Many A/B tests run in parallel, across metrics, subgroups, or repeated peaks, dramatically inflate overall false discoveries. Kahavi's Optimizely case is a cautionary tale. Early versions let testers peak at p-values before the experiment ended, effectively running the test many times and manufacturing apparent effects. Remedies are both technical, adjusting thresholds or p-values for the number of tests, and practical, choose essential tests, fix the experimental period, forbid peaking, justify treatments. Randomized experiment. Random assignment lets a difference be attributed to treatment, not pre-existing differences. T-test discipline. Compare against what chance would produce, but statistical significance is hostage to sample size, so weigh magnitude too. Multiple testing. Many tests, subgroups, or peaks inflate false discoveries. Fix periods, Forbid peaking. Adjust thresholds. Uplift persuasion modeling. An A/B test says which treatment does better on average. Nothing about which treatment does better for which individual. The political campaign example makes the gap vivid. Calling a Democrat who is not yet an activist may win a vote. Calling an already supportive Democrat wastes the call. Calling a Republican may be harmful. Campaigns grew data-rich, and since 2008 the recognition took hold that data should model whether a voter responds to outreach, not expert rule of thumb. The data come from public voter files, party poll watchers' records of who voted, appended census neighborhood data, and purchased demographic data. The experiment. Survey 10,000 voters' Democratic inclination. Randomly mail a pro-candidate message to half and resurvey. The control group is essential. 34.4% of those who received no message moved toward the Democrat anyway, reflecting election dynamics, while 40.2% of those message did, a lift of 5.8%. What the campaign really needs is the uplift for each voter. How much the message changes that voter's propensity, so limited resources reach the most persuadable. The method. Build a predictive model of the outcome that includes the treatment as a predictor. Score each record under its actual treatment. Then reverse the treatment and res score and estimate uplift as the difference in propensities between being treated and not treated. In data-driven methods like trees and random forests, the treatment's effect varies across records automatically. In logistic regression, interaction terms are added explicitly. A machine learning process that misclassifies some voters still easily beats the naive majority class rule. A random forest on the plaintext prediction achieves 96.3% accuracy. The outputs are striking in their detail. Some voters have positive uplift. The message helps. Some effectively zero. They were going to move anyway. And some negative. The message actually backfires. The campaign orders by uplift and contacts those with positive uplift or under budget constraints, the highest uplift subset. Everyone is eager to avoid both wasting effort on those who would act anyway and antagonizing those the message turns off. Uplift modeling's two purposes, whether to message at all and which of several messages to send, are technically the same problem, since no message is simply another treatment arm. Uplift. The per-record difference in outcome propensity between treated and untreated. Score under both and subtract. Control group essential. Baseline movement, 34.4%, must be netted out of the treated rate, 40.2%, to find a true 5.8% lift. Targeting use. Contact those with positive uplift, and never those the message would antagonize. Reinforcement learning. Reinforcement learning is the family of computational agents that learn by interacting with experimental units through dynamic treatment assignment. The distinction from supervised learning is fundamental. Supervised learning trains on pre-existing data. Reinforcement learning starts without data, and the algorithm decides which treatment to deploy so as to generate the outcome data most useful for learning the optimal treatment outcome mapping. In a recommendation system, you cannot know what a user would have done until you actually serve a recommendation and observe the reaction. Multi-arm bandits get their name from a gambler facing several slot machines with unknown payoff rates. An A/B test deploys the winner and abandons the rest. A bandit updates treatment assignment sequentially, increasing the share given to whichever treatment currently performs best while continuing to test the others. Because with a 100% commitment, there would be no chance to learn that a rival is actually superior. This is the explore-exploit tension. Exploit the winning treatment to improve outcomes, but keep exploring to evaluate the others. Strategies differ in how they schedule the two. Epsilon first explores randomly for a period, then commits. Epsilon greedy explores a fixed fraction of the time and exploits otherwise, with variants that decay exploration over time. Contextual bandits recognize that the best intervention may depend on a changing context. The same user wants different music in the morning than at night, on the phone than on the TV, so they combine the trial and error search with estimating how context variables moderate the treatment effect. The movie lens simulation shows the payoff. a lin-UCB policy that models each movie arm's expected reward as a linear function of a user's genre profile handily beats random recommendations. Markov decision processes generalize bandits to longer horizons. A bandit is a special case of a multi-stage process in which the allocation at one stage may depend on what happened before, and an MDP lets the algorithm learn the longer-term relationship between interventions and outcomes. A recommendation with low immediate reward but high future payoff, or a high profit item despite a low purchase probability. The MDP works through states. All the information about the user, context, and item. Actions, what is recommended or displayed. Rewards, user feedback like playing a song for 30 seconds. And a value function assigning each state the expected long-term reward under a given policy. Markov means the future depends only on the most recent state, reward, and action. The agent ignores everything older. The generic loop. Predict what the user would select next, recommend accordingly, collect feedback, update the model linking outcomes to current state and action, then recompute values and repeat. Two cautions close the chapter. First, the agent is only as good as the goals specified. Stuart Russell's Echo Smart Home Controller, designed to reduce energy use by learning from household behavior, eventually left inhabitants sitting in the dark when visitors stayed past bedtime. The objective was narrow, and the agent found an acceptable to it solution that was not acceptable to anyone else. In games like Go and chess, the ends and rules are fully specifiable, and the agent's creative solutions are legitimate. In human environments, they are not. Second, the standard methods were designed for fully observable tasks with short horizons, few states, and simple, predictable rules. Russell's warning. Relaxing any of these conditions means that the standard methods will fail. Learning by interaction. The agent deploys treatments to generate the outcome data most useful for learning, unlike supervised pre-existing data training. Multi-armed bandits. Balance exploiting the current best arm against exploring others. Epsilon first, epsilon greedy, contextual variance. Markov decision processes, states, actions, rewards, and a value function optimize long-run outcomes. With Russell's warning, relax full observability, short horizons, or simple rules and the standard methods fail. Summary. The chapter's methods all use randomized experiments and user feedback to determine the best intervention, and all involve interaction with the units of interest. A/B testing compares an intervention group with a control to estimate a treatment's effect. A/B/and extends it to several treatments. Uplift modeling folds A/B test results into a predictive model as a treatment predictor, guiding not only whether to send an offer, but to whom, by estimating each record's individual uplift. Reinforcement learning uses computational agents that learn the best intervention policy through trial and error, balancing exploration against exploitation. The two popular formulations are multi-armed bandits and Markov decision processes. Part 5. Mining relationships among records. Quote, reinforcement learning algorithms were designed for tasks that are fully observable, involve short time horizons, and have a small number of states and simple, predictable rules. Russell, 2019, concludes, relaxing any of these conditions means that the standard methods will fail. Chapter 15. Association rules and collaborative filtering. Association rules. Association rules, or affinity analysis, are the study of what goes with what, called market basket analysis because the method began with customer transaction databases to learn which items are bought together. Barcode data from supermarkets give a natural setting. Each record lists all items in a single purchase transaction, and managers want to know which groups of items are consistently purchased together to place products, cross-sell, run promotions, design catalogs, and segment customers. The rules are probabilistic if-then statements. If orange juice and flu medication are purchased, then soup is purchased on the same trip, and they power the frequently bought-together recommendations we see online, where a shopper browsing a phone is shown the case and screen protector often bought with it. The faceplate example. A store's promotion on 6 colors of cellular phone faceplates with 10 transactions carries all the mechanics. A rule has an antecedent, the if part, and a consequent, the then part, both item sets and disjoint. Ideally, we would examine every combination of items, but the count grows exponentially. 602 rules for 6 items, 1932 for 7. So the practical route is to consider only frequent item sets. Support is the measure of frequency, the number of transactions containing both the antecedent and consequent item sets, sometimes expressed as a percentage. A frequent item set is one whose support exceeds a user-selected minimum. The a priori algorithm of Agrawal et al., 1993, generates them efficiently. Count the 1 item supports, drop those below the minimum, then build 2 item sets from the survivors, because any item set containing a rare item cannot be frequent, and so on up the sizes, with each step a single pass through the database. This makes a priori fast, even with thousands of distinct items. From the abundance of candidate rules, selection picks out the strong dependencies. Confidence is the ratio of the support to the number of transactions containing the antecedent, the conditional probability that the consequent is purchased given that the antecedent is. In the supermarket example, 800 of the 2,000 transactions with juice plus medication also bought soup, so the rule has support 800 0.8% and confidence 40%. But confidence can deceive. If nearly everyone buys bananas and ice cream, then if bananas then ice cream, we'll have high confidence whether or not the items are truly associated. Lyft fixes this by comparing the confidence with what it would be under independence. The ratio of the rule's confidence to the benchmark confidence, where a lift above 1 indicates an association stronger than chance, and a larger lift a stronger one. The Mulxtend library adds leverage, deviation from independence, 0 when independent, and conviction, 1 when independent, infinite when the rule always holds. The 2 formats for transaction data are the transactions database and the binary incidence matrix. The faceplate data, with a minimum support of 20% and minimum confidence of 50%, yield a rule table whose interpretation requires all 3 lenses. Support tells how many transactions are affected, confidence the rate at which consequence will be found, and lift how efficient the rule is relative to random selection. Rule selection runs in 2 stages. Find a frequent item sets, then keep those whose confidence clears the bar. Rules and chance is a caution that every practitioner should internalize. On a database of 50 transactions where the 9 items were assigned to transactions completely at random, the algorithm still produces rules with confidence 1.0 and lift 4.55, because with enough rules examined, some will look strong by chance. 2 principles govern. Rules based on more records are more solid, and the more distinct rules we take seriously, the more likely some are chance artifacts. 1 person tossing 10 heads is surprising. 1,000 people doing so is not. The practical discipline is to consider rules top-down by business applicability and not to attempt more than human decision-making can absorb. The book purchase example, 4,000 transactions, 11 book types, shows both the reward and the need for judgment. The 25 highest lift rules cluster around child BKS, appearing in nearly every rule. But children's book purchases likely reflect the customer's children rather than personal preference, so child BKS may be meaningless noise to filter out. The rule, Ital cook, equals cook BKS has high confidence, but is probably trivial. Italian cooking books are simply a subset of cookbooks. And many rules, 70 to 73, 56 to 58, 22 to 25, involve the same few book types with only the antecedent consequent roles permuted, discernible at a glance by rows sharing the same support, and useful for consolidating actions even when they add no new information. A priori, frequent item sets build up from single items. Any superset of a rare item is rare. Each level 1 pass, fast at scale. Support, confidence, lift, frequency, conditional probability, and ratio to independence judge rule strength. Leverage and conviction add more. Chance rules. With many rules, some look strong by luck. Weigh support and keep the count human reviewable. Data format. Transactions database or binary incidence matrix drive the 2-stage generate then select process. Collaborative filtering. Recommendation systems are critical to sites with a huge variety of offerings. Amazon's millions of products, Netflix's movies, Google's web index, Spotify and Pandora's catalogs, travel and social sites, and they convert browsers into buyers, increase cross-selling, and build loyalty. Collaborative filtering identifies relevant items for a user. Filtering, by considering the preferences of many users. Collaboration. Amazon's item-to-item collaborative filtering draws on what user bought, rated, and liked, plus what similar customers viewed and purchased, to customize even the browsing experience. The data are a user-by-item matrix of preferences, numerical ratings, or binary behaviors like purchase, like, or click, typically sparse, since no one consumes everything, and the many missing values sometimes convey uninterested. With large user and item counts, the matrix is stored as triples: user ID, item ID, preference. The Netflix prize is the canonical application, millions of anonymous 1 to 5-star ratings, a $1 million prize for a 10% improvement over Cinematch, and the winning team's insight that which movies a user chose to rate at all. The binary view, regardless of rating value, was more informative than the ratings themselves, because a user's choices are deliberate, not a random sample. User-based collaborative filtering answers people like you. Find a user's most similar to the target user, the neighbors, then recommend items they prefer that the target has not yet consumed. Similarity is the crux. Euclidean distance performs poorly here. The Pearson correlation between two users' ratings, computed, crucially, only over the items both rated, is the popular measure, and cosine similarity, which omits the mean subtraction, is a common variant. Subtracting the mean and the correlation adjusts for users who rate everything high versus everything low. The cold start limitation follows directly. A user or item with a single rating cannot anchor a similarity. Correlation denominators collapse to zero, so new users and new items fall outside the method's reach. Selecting the best item among the neighbors' holdings means, for binary data, the most purchased, for ratings, highest rated, most rated, or awaiting. With a huge user base, computing all pairwise similarities is expensive. Clustering users into homogeneous groups moves the computation offline and compares the new user to clusters in real time, at the cost of somewhat less precise recommendations. Item-based collaborative filtering inverts the perspective. When a user expresses interest in an item, find the items co-purchased or co-rated with it and recommend the most popular or most correlated among them. Because the number of items is usually far smaller than the number of users, the item-item correlations can be computed offline and recommendations become fast at scale. The reason item-based approaches have largely displaced user-based ones where speed matters. Their weakness is less diversity. Recommendations built from co-purchase patterns are often obvious. Both approaches are implemented in Python with the surprise package. The Movie Lens example, 100,836 ratings from 610 users on 9,742 movies, builds user-based and item-based cosine models whose top 4 recommendations for sample users differ markedly. The Usual Suspects, Fargo, and Star Wars from user-based. A Bug's Life. The Exorcist, and A Fish Called Wanda from item-based, with only one movie in common across the top 10 lists. Evaluation of a recommender treats the user's actual behavior as the answer to a hidden recommendation. Hide some user item entries as the holdout, generate recommendations, and compare against the revealed truth. Predictive performance uses the familiar holdout metrics, RMSE and MAE for ratings, though distorted by long-tail items that a single miss can mask, and confusion matrix accuracy, recall precision, ROC for clicks/no-click. Ranking performance focuses on the top end, set the user actually sees. Spearman correlation for rating orderings, top-end precision and recall for categorical ones, plus specialized metrics for novelty, trust, coverage, and serendipity. Partitioning differs from supervised learning. The sampling unit is the user item entry, not the user. On Movie Lens, user-based filtering, RMSE 0.973, edges out item-based, 0.978, and both crush a random recommender, 2.008. A crucial caveat: Collaborative filtering is unsupervised at heart. The predictions come without true outcomes, so evaluation treats the user's behavior as if it responded to a recommendation, and real performance is best judged by online learning, where actual user feedback and business-relevant metrics like conversion rate are measured against the presented recommendations. User versus item-based. Find similar users and recommend what they liked, or find co-purchased items for what the user wants. Similarity. Pearson correlation over co-rated items, and cosine similarity. Cold start blocks new users and items. Evaluation. Hide user item entries as holdout. Predictive. RMSE/MNE. Accuracy. And ranking. Top-end precision/recall. Metrics. Partition by entries, not users. Summary. Association rules and collaborative filtering are unsupervised methods for deducing associations among purchases. Association rules discover generic if-then rules about items bought together, transparent and easy to understand, through a two-stage process of generating candidate rules from frequent item sets, a priori, and selecting the strong ones by support and confidence, with LIF comparing efficiency against random association. Their shortcomings are the profusion of generated rules, demanding human winnowing of the trivial and redundant, and the blindness to rare combinations that fail the minimum support bar. A reason to prefer items of roughly equal frequency, for instance book types rather than individual titles. Collaborative filtering provides personalized recommendations from user item combinations. User-based filtering finds similar users and recommends what they favored. Item-based filtering finds items co-purchased with what the user wants. Its requirements are sufficient per user neighbors and per item ratings. Its limits are the cold start for new users and items and computational strain at scale. Item-based methods and SVD dimension reduction relieve it. And its power is that it captures each user's individual taste rather than generic co-purchase patterns. Quote, at root, the retail giant's recommendation system is based on a number of simple elements. What a user has bought in the past, which items they have in their virtual shopping cart, items they've rated and liked, and what other customers have viewed and purchased. Amazon calls this homegrown math, item-to-item collaborative filtering, and it's used this algorithm to heavily customize the browsing experience for returning customers. Chapter 16. Cluster Analysis. Introduction. Cluster analysis forms groups, or clusters, of similar records from measurements on those records, with the goal of characterizing the clusters in ways useful for the analysis. The idea has powered astronomy, archaeology, medicine, chemistry, education, and biology. Mendeleev's periodic table is a spectacular clustering success. In marketing, clustering drives market segmentation. Customers grouped by demographics and transaction history each receive a tailored strategy, sometimes at the store level in location-sensitive markets like India, microsegmentation. Cluster analysis also identifies groups of similar products, market structure, groups neighborhoods by lifestyle. Claritas famously turned postal zip codes into 40 clusters with evocative names like Bohemian Mix, Furs and Station Wagons, and Money and Brains, and it pervades finance, where balanced portfolios are built by picking securities across clusters and industry analysis groups, firms by growth, profitability, and market size, to reveal who competes with whom. Even the design of U.S. Army women's uniforms was a clustering problem, yielding 20 sizes defined by 5 measurements, each fitting a different body type. The public utilities example carries the chapter. 22 utilities, each measured on 8 variables: fixed charge ratio, rate of return, cost, load factor, demand growth, sales, percent nuclear, fuel cost, where clustering similar utilities would let economists build a detailed cost model for one typical utility per cluster and scale up. Even plotting just sales against fuel cost shows the I3 loose groups: high fuel cost, low fuel cost with low sales, low fuel cost with high sales. 2 families of algorithms form such clusters. Hierarchical methods are agglomerative, start with n singleton clusters and merge the nearest, or divisive, split one cluster down to singletons, and suit data with a natural hierarchy. Non-hierarchical methods like K-means pre-specify the number of clusters and assign each record to 1, generally cheaper and preferred for very large datasets. Measuring distance between two records. Everything rests on distance. A distance metric between two records must be non-negative, 0 from a record to itself, symmetric, and satisfy the triangle inequality. The Euclidean distance, the square root of the sum of square differences, is the most popular, but it has 3 flaws. It is highly scale-dependent. With sales measured in the thousands and fuel cost in the tens, sales dominates the distance. So continuous measurements are routinely normalized to z-scores first. The Arizona Utilities normalized sales, for instance, is computed from its deviation from a mean divided by the standard deviation. It ignores relationships among variables, so strongly correlated variables double count, and it is sensitive to outliers. Other measures address specific needs. Correlation-based similarity, the squared Pearson correlation, works when similarity of shape matters. Any similarity converts to a distance. The statistical Mahalanobis distance uses the covariance matrix to downweight variables that are highly correlated with others. Variables that are practically redundant contribute less. The Manhattan or city block distance uses absolute rather than square differences and is robust to outliers. The maximum coordinate distance looks only at the variable on which the two records differ most. For categorical data, similarity measures are more natural. The matching coefficient counts agreements, including zeros, while Jacob's coefficient ignores zero matches. Desirable when a shared absence, like both not owning a Corvette, should carry no similarity weight. For mixed continuous and binary data, Gower similarity is a weighted average of per variable similarities, each variable scaled to 0, 1. Euclidean distance, the default but scale-dependent, correlation-blind, and outlier-sensitive, normalize first. Alternatives, statistical, Mahalanobis, distance downweights correlated variables. Manhattan is outlier robust. Correlation similarity and Gower's measure handle shapes and mixed data. Categorical measures, matching and Jacket similarity. Jacket ignores shared absences, which is usually what you want. Measuring distance between two clusters. Once clusters contain several records, cluster-to-cluster distance must be defined. Minimum distance, single linkage, takes the closest pair across the clusters. Maximum distance, complete linkage, the farthest pair. Average distance, the average over all pairs. And centroid distance, the distance between the two cluster mean vectors. Domain knowledge guides the choice. Minimum distance suits elongated, chain-like clusters, crops along a river, disease along waterways, minefields, and is more robust to small deviations, though sensitive to added or removed data. Maximum and average distance suit the roughly spherical clusters that most real data form, and are good defaults. Linkage choices, minimum, single, suits chain-like clusters. Maximum, complete, and average suit roughly spherical ones. Centroid distances group means. Hierarchical, agglomerative, clustering. Hierarchical agglomerative clustering starts with every record as its own cluster and repeatedly merges the two nearest clusters until one remains. The linkage method determines what nearest means. Single linkage, minimum distance, tends to chain distant records together into elongated shapes. Complete linkage, maximum distance, produces tight, roughly spherical clusters. Average linkage, UPGMA, averages all pairwise distances. Centroid linkage, UPGMC, takes the distance between group means. Ward's method takes a different tack, measuring the loss of information. The error sum of squares around each cluster mean, and merging so as to add the least. Ward's method tends to produce convex clusters of roughly equal size, valuable for meaningful customer segments. The dendrogram is the tree-like diagram of the whole process. Records along one axis, and for each merge a line whose vertical length reflects the merging distance. Cutting the tree at a chosen height yields a set of clusters. Records joined below the cut belong together. On the 22 utilities, normalized, 8 variables. Single linkage with a cutoff of 2.7 gives 6 clusters, and average linkage with 3.5 gives a slightly different 6. Both isolate New York and San Diego as singletons, and both suggest 4 as a reasonable number. clusters obtained from fewer cuts nest within those from more, a property essential for taxonomy of organisms applications. The average linkage 6 clusters are geometrically suggestive: a southern group, a northern group, an east/west seaboard group, and a west group. Validation asks whether the clusters generate insight. Interpretability. Examine each cluster's summary statistics, check separation on a variable not used in the clustering, and label each cluster. Stability. Do the assignments survive small input changes, or do clusters built on one partition still predict membership on another? Separation. Examine the ratio of between cluster to within cluster variation. Statistical F-ratio tests are controversial. Number of clusters. Must serve the purpose. A marketing department that can sustain only 3 presentations should not be handed 5 segments. Characterizing the 6 utility clusters by a heat map of their measurements shows 1 cluster of high nuclear utilities, 1 of high fixed charge and rate of return, 1 of high fuel costs, profiles that turn anonymous company names into descriptive groups. Hierarchical clustering's appeal is that it needs no pre-specified cluster count and renders the whole process as an interpretable dendrogram. Its limitations. It stores and computes an NXN distance matrix, expensive for very large data. It makes a single pass, so a record allocated incorrectly early cannot be reallocated. It has low stability. Reordering or dropping a few records changes the solution. Average linkage is sensitive to the choice of distance metric, while single and complete linkage depend only on the ordering of distances. And it is sensitive to outliers. Merging loop. Start with singletons and repeatedly merge the nearest clusters. Single, complete, average, centroid, or wards. Least loss of information. Dendrogram. Cut the tree at a height to read clusters. Clusters nest as cuts increase. Essential for taxonomy-style questions. Validation. Interpretability, summary stats, labels, stability across partitions, separation, and a purpose-appropriate cluster count. Limitations. NXN distance matrix, single pass with no reallocation. Low stability, metric sensitivity, average linkage, outlier sensitivity. Non-hierarchical clustering. The k-means algorithm. K-means pre-specifies a number of clusters K and assigns each record to one of them, so as to minimize within-cluster dispersion. Typically the sum of squared Euclidean distances from each record to its cluster centroid. The optimization is an integer program, expensive to solve exactly, so K means uses a fast heuristic. Start with K initial clusters. Reassign each record to the cluster with the closest centroid. Recompute the centroids of clusters that gained or lost records. Repeat until moving records no longer reduces dispersion. The worked 5 utility, 2 variable example shows 1 full reassignment cycle. Records migrate, centroids recompute, and the process stops when everyone sits in the closest cluster. Choosing K is driven by external considerations, prior knowledge, practical limits, or by trying values and comparing the resulting sum of distances. With no external information, the algorithm is rerun from several random starting partitions to dodge poor local solutions. A striking visual aid for choosing K is the elbow chart of within-cluster distance against K. On the utilities data, dispersion falls steeply through K equals 4, then improvements flatten. The elbow at 4. Notably, K means clusters are not nested across different K the way hierarchical ones are. With K equals 6 on the 22 utilities, K means reproduces much of the hierarchical picture. New York, a singleton, and 2 clusters nearly identical to the average linkage groups: Arizona, Central, Florida, Kentucky, Oklahoma, Texas, and Virginia, Northern Commonwealth, Madison, Wisconsin. Characterizing comes from the cluster centroids. Read numerically or as a profile plot, showing that one cluster has very low fixed charge and rate of return with high demand growth and sales, and that sales and fixed charge spread the clusters most. Within cluster dispersion and the distances between centroids round out the description, and the ratio of within cluster to total square distance measures how well the clustering separates the data. Part 6, Forecasting Time Series. K-means loop. reassign each record to the nearest centroid, recompute centroids, repeat until dispersion stops shrinking. Choosing K, external constraints or the elbow in within cluster distance. Utilities. 4. Clusters are not nested across K. Characterization. Read centroids and profile plots. Within cluster and between centroid distances validate separation. Quote, cluster analysis can be applied to huge amounts of data. For instance, internet search engines use clustering techniques to cluster queries that users submit. These can then be used for improving search algorithms. Chapter 17. Handling Time Series. Introduction. Time series forecasting is performed in nearly every organization that works with quantifiable data. Retailers forecast sales, energy companies forecast reserves, production, and demand, institutions forecast enrollment, governments forecast tax receipts and spending, the World Bank and IMF forecast inflation, transportation companies forecast travel, banks forecast home purchases, sometimes badly, and venture capital firms forecast market potential. All of it treats time differently from the cross-sectional data of the earlier chapters. With today's technology, many series are recorded at very fine scales. Ticker-level stock data, real-time purchases, a torrent of Internet of Things sensor feeds. Yet for forecasting, the finest scale is not always best. Minute-by-minute grocery sales carry so much peak hour noise that they forecast next-day sales worse than daily aggregates, where the noise averages out. The choice of time scale must weigh the scale of the required forecasts against the noise in the data. The focus here is forecasting a single series. Multivariate models exist, but are restrictive, expertise-hungry, and rarely worth the trouble, while simple heuristics like Estee Lauder's leading lipstick indicator capture external associations plainly. Descriptive versus predictive modeling. Modeling a time series serves two purposes. Descriptive modeling, time series analysis, determines the series components, seasonal patterns, trends, relations to external factors for decision-making and policy. Predictive modeling, time series forecasting, uses the series to forecast its own future values. The goals drive different choices. Describing prefers understandable, sometimes causal models, and can legitimately use future information, averaging yesterday, today, and tomorrow to smooth today's value. Forecasting is prospective and can only use what would have been known then. Analysis versus forecasting. Describing a series can use future information to smooth. Forecasting may only use what would have been known. Popular forecasting methods in business. Two families dominate business forecasting. Multiple linear regression, where the user specifies a model and estimates it from the series, and data-driven methods. Smoothing and deep learning, where the method learns patterns from the data. Machine learning methods built for cross-sectional data are sometimes pressed into forecasting service, mainly to fold external information into the predictions. Combining methods improves accuracy, as with cross-sectional ensembles. Either two-level, multi-level forecasters, where a first method forecasts the series and a second forecasts the first model's residuals, correcting its forecasts, or ensembles that average several methods' forecasts into a more robust, higher precision result. Two families, regression, user-specified model, and data-driven smoothing/deep learning that learns patterns. Combining methods improves precision. Time series components. It is customary to dissect a series into four components. Level, the average value. Trend, the change from one period to the next. Seasonality, short-term cyclical behavior repeated several times within the series. Any repeating time period, not just the calendar seasons. And noise, random variation from measurement error and unmodeled causes, always present to some degree. The first three characterize the unseen underlying series that we observe only with added noise. The time plot, the series values against calendar time, is where the components first surface. The Amtrak ridership series, monthly, January 1991 through March 2004, shows an overall level near 1,800,000 riders, a slight U-shaped trend, and pronounced annual seasonality, peaking in July and August. A few manipulations sharpen what the eye sees. Zooming into a short period reveals patterns hidden in the whole. The Bareg Tunnel's daily traffic shows a strong day-of-week rhythm only when a few months are examined. Changing scale tests hypotheses. A log-scale axis that straightens a trend reveals exponential growth. Overlaying trend lines reveals whether the trend is linear, exponential, or quadratic. Suppressing seasonality. Aggregating to a coarser scale, plotting one line per season, or using moving averages, exposes the trend beneath. Methods divide by how they treat the components. Some assume structure, a linear or exponential trend, normal noise. When the assumptions hold, forecasts are more robust and models more understandable. Data-adaptive methods estimate the components from the data with fewer assumptions, advantageous when assumptions break or the structure changes over time, and many are simple and computationally cheap. The decisive criterion is global versus local pattern. A global pattern, a constant linear trend throughout, is well served by model-driven methods that use all the data. A local pattern, a slope that shifts slowly, defeats a model-driven approach, which would have to specify when patterns change, and prefers data-driven methods whose memory length can be set to match the rate of change. Short memory for quickly changing patterns, long for slowly changing ones. The time plot should reveal not only the components, but their global or local nature. 4 components: level, trend, seasonality, and noise. The first 3 observed only through added noise. Time plot reading. Zoom, risk scale, add trend lines, and suppress seasonality to expose components and their global or local character. Global versus local. Model-driven methods fit global patterns. Data-driven ones adapt to changing local ones, with memory length matched to the rate of change. Data partitioning and performance evaluation. Partitioning a time series differs from cross-sectional data in an essential way. Random partitioning would punch holes into the series, and standard forecasting methods cannot handle missing values. Instead, the series is trimmed. The earlier period becomes training, the later period holdout, which also mimics deployment, training on the past to forecast the future. Evaluation reuses the cross-sectional metrics, with MA, MAPE, and RMSE the most popular, and adds visualization. Overlaying actual and predicted series reveals performance and hints at improvements. The benchmark is the naive forecast, the most recent value of the series, projected forward. Sometimes surprisingly hard to beat, it is the essential yardstick. A seasonal naive forecast, the value at the most recent similar season, handles seasonal series, forecasting April 2001 ridership from April 2000. On Amtrak's monthly seasonality, the seasonal naive forecast is the clear winner over plain naive on both training and holdout on every measure, and holdout accuracy, not training, is what guides the choice. One more difference closes the chapter. When generating real future forecasts, the training and holdout sets are recombined and the model refit on the complete series. The holdout period, being most recent, is closest in time to the forecast and thus most valuable. More data estimates some models more accurately, and forecasting from the training set alone would require forecasting far ahead. Chronological trim. Random time series partitioning would punch holes. Train on the earlier period, test on the later, mirroring deployment. Naive benchmarks. The most recent value, or recent similar season, is surprisingly hard to beat. Seasonal naive wins on seasonal series. Recombine to forecast. Refit on the full series before real forecasting. The holdout is the most recent, most valuable data. Quote, while simple, naive forecasts are sometimes surprisingly difficult to outperform with more sophisticated models. It is therefore important to benchmark against results from a naive forecasting approach. Chapter 18. Regression-based forecasting. A model with trend. Regression-based forecasting captures trend and seasonality in a multiple linear regression model, then generates forecasts by plugging fresh predictors into the estimated equation. A linear trend is modeled by setting the outcome, y to the series values, and the predictor x to a time index, estimating y sub t equals alpha plus beta t plus epsilon sub t, capturing level, trend, and noise, but not seasonality. Even where the trend is not linear, Amtrak's is visibly U-shaped. The exercise is instructive. The linear trend's intercept is 1,662.17 and slope 0.351, yet the trailing RMSE of 158.9 versus holdout RMSE of 239.5 signals an inadequate trend shape, most plainly seen in the residual plot, which arcs in the U the model missed. A statistically insignificant trend coefficient does not mean no trend. The plot may reveal a trend the linear form cannot represent. The gap between training and holdout error, in other words, is itself the diagnostic. An exponential trend implies a multiplicative change over time. Y sub t equals alpha, e to the beta t fit a linear regression of the log of y on the time index. Popular for sales data, reflecting percentage growth. Schim's pipeline of log transformer plus trend forecaster handles the transform and back transforms forecasts automatically, so comparisons stay on the original scale. A polynomial, quadratic, trend adds the squared time index as a second predictor. A quadratic trajectory correctly captures Amtrak's U-shape within the training period, leaving residuals that show only seasonality. Yet the forecasts overshoot in the holdout, a reminder that a shape fitting the training data well need not extend into the future. The general rule: any trend with a mathematical form can be fit, but the assumption is that the shape holds over both the observed and the forecast periods. Do not choose an overly complex shape, which will overfit. Always check the holdout performance. Linear trend. Regress the series on a time index. Here it misses Amtrak's U-shape, training RMSE 158.9 versus holdout 239.5. Exponential and polynomial trends. Log the outcome for percentage growth. Add t to the second for curvature, but don't let a complex shape overfit. Check holdout. A model with seasonality. Seasonality means some seasons consistently run higher or lower than others. Day of week, monthly, quarterly patterns, Amtrak summer peak. The regression captures it by creating a categorical season variable, converting it to dummies, 11 for 12 months, and including them as predictors. The ARDL model, autoregressive distributed lag, fits this. A seasonality-only model captures the seasonal pattern well. The August dummy of 396.66 says Amtrak's average August ridership runs 396,660 passengers above January's, but leaves the trend to show up in the residuals because no trend term was included. This is additive seasonality. Each season sits a fixed amount above or below the reference. Multiplicative seasonality, where seasons differ by a percentage, is fit the same way, but with the log of y as the outcome, which also pairs naturally with an exponential trend when both are present. Season dummies. A categorical season variable becomes m-1 dummies. Additive seasonality adds a constant per season. Multiplicative uses the log outcome. A model with trend and seasonality. Combining both sets of predictors captures both patterns. For Amtrak, a quadratic trend and monthly seasonality are both warranted, giving 13 predictors, 11-month dummies plus t and t to the second. The quadratic term added as an exogenous variable, since ARDL does not support a quadratic trend directly. The fitted model's residuals reveal what remains. The seasonal cycle no longer dominates, but a strong positive lag. One autocorrelation shows neighboring residuals are related, information the next section exploits. Even so, the holdout forecasts miss the mark, suggesting the identified trend may not be so global after all. The next chapter's local trend methods will allow for change. When satisfied, the model is refit on the entire series and used for step-ahead forecasts, inserting the appropriate month and index terms. Combine both. Month dummies plus trend terms capture both. Residuals then reveal any remaining trend or autocorrelation. Refit before forecasting. Once satisfied, refit the whole series and forecast by inserting month and index terms. Autocorrelation and ARIMA models. Something more than trend and seasonality connects neighboring values. Autocorrelation. the correlation between the series and a lagged copy of itself. The lag. One autocorrelation is the correlation between the series and its one-step forward copy based on n-1 pairs. Lag. 2. The two-step copy, and so on. The autocorrelation function, ACF, plots these across lags with confidence bands. Typical behaviors carry meaning. Strong autocorrelation at a lag greater than 1, and its multiples signals a cycle, positive lag. 12 in monthly data, annual seasonality. Positive lag, 1 stickiness, a series that moves generally in one direction, as under a strong linear trend. Negative lag, 1, a swinging series. The first 24 months of Amtrak ridership show the strongest negative autocorrelation at lag. 6, a biannual high summer, low winter pattern. The residual series is where autocorrelation pays. If a model has adequately captured the seasonal pattern, the residuals should show no autocorrelation at the season's lag, and after the trend and seasonality model, the 6 and 12-month cycles no longer dominate. But a strong positive lag, 1 autocorrelation remains in the residuals. Neighboring forecast errors are related, and that information can improve the forecasts. The tool is an autoregressive AR model of the residuals. For the Amtrak errors, an AR1 with coefficient 0.5998, close to the lag, 1 autocorrelation. Its forecast for the next residual, plug the most recent residual, 12.108, into the AR1, says the regression forecast for April 2001 is too low by about 7,316 riders. The two-stage regression plus AR1 forecast of 2,011,587 lands far closer to the actual 2,023,792 than the plane regression's 2,004,271. The residuals of residuals show no remaining autocorrelation. The AR1 absorbed it. The honest caveat: the AR layer improves short-term forecasts only. An AR model of order K provides useful forecasts for about K periods ahead, after which it leans on its own earlier forecasts rather than actual data. Predictability deserves a check before forecasting at all. A random walk is a series whose period-to-period changes are random. The special case of an AR1, with slope 1, making forecasts equal to the most recent value, the naive forecast. Testing whether a series is a random walk is testing whether it's lag. One different series behaves like random noise. If the difference autocorrelations are all near 0, the original is likely a random walk. The S&P 500 monthly closing prices, May 1995 to August 2003, illustrate all lag 1 difference autocorrelations are practically 0, and the AR1 slope is 0.9834, about 1 standard error from 1. A random walk, so forecasting it beyond the naive approach is futile, in line with the efficient market hypothesis. Autocorrelation, the correlation of a series with lagged copies. Cycles, stickiness, and swings each have characteristic ACF signatures. AR correction, regress the residuals on their own lag. AR1 coefficient is almost equal to lag, 1 autocorrelation, and add the forecast error correction, short horizon only. Random walk test, near 0 differenced autocorrelations, or an AR1. Slope is almost equal to 1, S&P 500, 0.983. Mean the naive forecast is the best available. Quote, ordinary regression models do not account for dependence between values in different periods, which in cross-sectional data is assumed to be absent. Yet in the time series context, values in neighboring periods tend to be correlated. Such correlation, called autocorrelation, is informative and can help in improving forecasts. Chapter 19. Smoothing and Deep Learning Methods for Forecasting. Smoothing Methods. Introduction. Smoothing methods are the data-driven counterpart to regression-based forecasting, where regression assumes a theoretical structure for the components, a linear or quadratic trend. Smoothing estimates the components directly from the data, smoothing out the noise to uncover the patterns. These methods are especially useful when patterns change over time, and they differ in how many periods are averaged, how the average is computed, and how many times the averaging is repeated. Two popular families are the moving average and exponential smoothing. Moving average. The moving average averages values across a window of consecutive periods. The window has two placements with opposite purposes. A centered moving average, which centers the window on each time point and averages the surrounding values, is a powerful visualization tool because the averaging suppresses seasonality and noise and makes the trend visible. A trailing moving average, which averages the most recent K values, is the forecasting version, since forecasting cannot use the future. For a seasonal series, the natural window width is the length of the seasonal cycle. For Amtrak's annual pattern, 12. Applied as a centered 12-period average, the series smooths into a global U-shape that still deviates from a strict parabola, a slight dip in the last year. The trailing version visibly lags the series. The trailing moving average as a forecaster exposes its limits, forecasting every holdout month as the same value. 1938.481, the last 12-month average, under forecast high seasons and over forecast low ones, and it lags trends. Under forecasting in an increasing trend, over forecasting in a decreasing one. In general, the moving average should be used only on series without trend or seasonality, which sounds impractical until one remembers that regression models can detrend and deseasonalize a series first. Apply the moving average to the residuals, assumed free of both. Forecast the next forecast error, and add the correction back. For Amtrak, the regression forecast for April 2001, 2015.572, is corrected by the 12-month moving average of the residuals, about 30.66 thousand riders, because the positive residual forecast signals the regression is too low. The only user choice is the window width K, and it is the same trade-off as in any smoothing. Wide windows expose global trends, narrow ones local. The forecasting window should reflect domain knowledge about how relevant past values are and how fast the series changes, and empirical comparison across values is fair game, with a standing caution not to overfit the choice. Centered versus trailing. Centered averages reveal the trend. Trailing averages forecast using only past values. Window width. Match the seasonal cycle, 12 for annual. Wider equals global trend. Narrower equals local. The moving average lags trends and misses seasons, so use it on residuals. Simple exponential smoothing. Simple exponential smoothing is the moving average's sophisticated cousin. Instead of a simple average of the most recent K values, it takes a weighted average of all past values with weights decaying exponentially into the past. Recent information counts most, older information is not discarded. It also belongs only on series without trend or seasonality, hence its typical use on regression residuals. The smoothing parameter alpha, between 0 and 1, sets the learning rate. The recursive formulation is the revealing one. The next forecast is the previous forecast plus alpha times the previous forecast error. The forecaster is an active learner correcting its miss. If the last forecast was too high, the next is adjusted down, and it needs to store only the most recent forecast and error, a decisive savings for real-time or mini-series forecasting. Because the series is assumed to lack trend and seasonality, all horizons share one forecast. The choice of alpha trades learning speed against smoothing. Near 1, and only the recent past matters. Near 0, and the whole history governs. Well-tested defaults hover around chapter 0, verse 1 to 0.2, and the urge to pick the best alpha by optimizing holdout accuracy runs the usual risk of overfitting. The two simple smoothers are approximately equivalent when a moving average window equals 2 over alpha minus 1. Exponentially weighted average. All past values, weights decaying into the past. The naive version corrects the last forecast by alpha times the forecast error. Smoothing parameter. Near 1 learns fast. Near 0 smooths heavily. Default chapter 0, verse 1 to 0.2. Optimize on holdout, not training. Equivalence. The moving average and exponential smoothing align when the window is about 2 over alpha minus 1. Advanced exponential smoothing. For series with trend, Holt's exponential smoothing double exponential smoothing. Estimates both a level and a local trend, updated as data arrive, so the trend need not be global as in regression. The step-ahead forecast combines the level and the trend times the horizon, which makes different horizons differ. Two smoothing parameters, one for level and one for trend, govern the learning rates. For series with both trend and seasonality, Holt, Winter's exponential smoothing adds a seasonal index with three updating equations: level, seasonally adjusted, trend, and seasonal index, each a weighted average of the previous estimate and recent information. The formulation shown is multiplicative seasonality. Seasons differ by percentage. An additive version handles constant differences. On raw Amtrak ridership, Holt, Winters reaches holdout RMSE 79.0 and MAPE 3.01%. A strong result on the unmodified series. A trend-free variant deletes the trend term for seasonality-only series. In time, these are all exponential smoothing, with trend and seasonal arguments and the season length SP. Leaving smoothing parameters unset optimizes them. Holt, double a level and a local trend updated as data arrive. Trend need not be global. Holt, Winters, adds seasonal indices with three updating equations: multiplicative for percentages, additive for constants, trend-free variant for seasonality alone. Deep learning for forecasting. The data-driven toolkit has been extended by deep learning for sequential data. Recurrent neural networks, RNN, add to each hidden layer a feedback arrow that lets information flow from one pass to the next, a looping memory. Training partitions the series into rolling windows of width k, each window a predictor series with the next value as label, fed sequentially so the hidden nodes carry memory forward. A simple RNN, however, has short-term memory. The vanishing gradient problem shrinks the gradient updates over time. The earliest layers stop learning and distant information is forgotten. Long short-term memory, LSTM, networks fix this with gates in each hidden node that learn what to keep and what to discard, relaying relevant information along the chain. The Amtrak illustration: normalize the series to 0 to 1, build 111 subseries of 12 values with their one-step ahead labels, and define an LSTM with two 50-node LSTM layers, a flattened and a dense output. Train for 400 epochs on mean squared error. Forecasting the holdout requires a rolling window. The last 12 training months forecast the first holdout month, which then joins the window as the earliest value drops out, and so on. The results are honest. Training RMSE is 88.8 and holdout 154.0, the gap signaling overfitting, and the holdout RMSE is worse than Holt, Winters 79. Yet the plot shows the LSTM performs well on the near-term holdout months and degrades on longer horizons. A reminder that such models suit applications updated month by month rather than long-range forecasting. Part 7. Data Analytics. RNN and LSTM. Recurrent loops give memory. LSTM's gates fix the vanishing gradient short-term memory of plain RNNs. Rolling windows. Vertically slice the series into windows as predictors with next value labels. Forecast by sliding the window forward. Honest results. On Amtrak, the LSTM's holdout, RMSE 154, trails Holt, Winters 79, and shows overfitting, strong short horizon, weak long horizon. Quote, in both smoothing methods, the user must specify a single parameter. In moving averages, the window width k must be set. In exponential smoothing, the smoothing parameter, alpha, must be set. In both cases, the parameter determines the importance of fresh information over older information. Chapter 20. Social Network Analytics. Introduction. Social media took off in the early 2000s with Friendster and MySpace, then Facebook in 2004, followed by LinkedIn, X, formerly Twitter, Tumblr, Instagram, Yelp, and others. And these information-based companies immediately began generating a deluge of data, especially data about links among people. For Facebook, X, and LinkedIn, nearly the entire value of the company lies in the analytic and predictive value of that network data. As of June 2024, Facebook was worth more than 10 times General Motors and Ford combined. Others, like Amazon and Spotify, use social network data as components of predictive engines for selling products and services. The methods themselves long predate the internet. They began with the study of whom people are connected to, but the explosion of social media brought them to the center of analytics. A social network is simply entities, people, and the connections among them. Nodes, vertices, and edges, links. Directed versus undirected networks. The tiny hypothetical LinkedIn network, 6 members, edges between some pairs, is undirected. If John is connected to Peter, Peter is connected to John. The same members on X form a directed network. Dave may follow Peter without Peter following Dave, so edges carry arrows. Edges can also be weighted, with thickness representing the strength of a connection, email traffic, bandwidth, and length representing attributes like physical distance. Direction and weight. Undirected for mutual ties, directed for follows. Edge weight and length encode strength and distance. Visualizing and analyzing networks. Network plots are everywhere in the news. The San Antonio Express News drug laundering visualization maps the connections behind a money laundering operation. With a well-connected central node, the address of an expensive home in a gated community owned by the accused launderers, alongside smaller segments and a singleton. Node size encodes centrality. A crucial subtlety. The XY coordinates in a network plot carry no meaning. The message is carried by node size, edge width, labels, and arrows, so the same network can look entirely different under different layouts. Layout choices are governed by readability principles. Every node visible, every node's degree countable, every link traceable from source to destination, clusters and outliers identifiable, and layout algorithms combine fixed structures, random tweaking, physical analogies like springs, and iteration toward these metrics. Every network plot is anchored to a data structure. The edge list, or adjacency list, is the table whose rows are links between nodes. The drug network's edge list pairs entities like Q and MLLC with 10 Kings Heath. The adjacency matrix is the matrix equivalent. Cells indicate an edge, with the originating node down the side and the destination across the top. Dave following Peter, Jenny, and John reads directly off his row. Network data often arrive unstructured. X's public feed was the original research goldmine, and the analytic task is to convert them into structured metrics usable in ordinary machine learning. Readability principles. Every node visible, degree countable, links traceable, cluster/outliers identifiable. Layout carries no inherent coordinate meaning. Data structures. Edge lists and adjacency matrices anchor every network plot. Social data metrics and taxonomy. The vocabulary of network analysis matters before any metric. Edge weight, strength of a connection, path and path length, the route and number of edges between nodes, with the shortest path in a weighted network the least cost path, not necessarily the fewest edges. Connected network. Every node reachable from every other, possibly in separate connected segments. Clique. Every node connected to every other by direct edge. And singleton. An unconnected node, someone who joined a read. Reviews and never participated. Centrality answers who matters. Degree. The most basic measure. Count a node's edges. Albert has degree 1, Sam 2, Jenny 3. In a directed network, in degree and out degree separately count incoming and outgoing connections. Closeness measures how near a node is to everyone else. The reciprocal of the average shortest path to all others. Betweenness quantifies how often a node sits on the shortest paths between other pairs. Peter, appearing on 6 of the paired shortest paths in the tiny network, has normalized betweenness 0.6, making him the intermediary. The classic aphorism gets an upgrade. It is not what you know, but who you know and who they know. Eigenvector centrality captures exactly that, factoring in both a node's links and the onward connections of those links. Its value runs 0 to 1, and it is what size the drug network's nodes. The egocentric network looks outward from one individual. The degree. One ego network is the node's own connections. The degree 2 network adds their connections. vital for recruiters interested in a job title and whomever its holders know. Whole network measures round this out. The degree distribution tabulates how many nodes have each number of connections. Density is the ratio of actual edges to the maximum possible for directed and undirected networks alike, ranging from near zero, sparse, to 1, as dense as possible. Terminology: edge weight, path/path length, connected network, clique, singleton. Centrality: degree, closeness, betweenness, and eigenvector centrality. Answer: who matters? Sized as node diameters. Network measures: degree distribution and edge density summarize the whole network. Egocentric networks zoom to an individual. Using network metrics in prediction and classification. Network metrics plug directly into standard classification and prediction. Link prediction: Facebook's and LinkedIn's people you may know restates the business goal as an analytics problem. If presented with a network, predict the next link to form. Algorithms score every possible node pair by similarity, and the closest pair that is not yet linked is the predicted next edge. The similarity measures span both ordinary variables, education, age, location, and network-specific ones, shortest path, number of common neighbors, edge weight. The same machinery underpins intelligent surveillance, where collecting everything is infeasible and link prediction prioritizes a small set of targets from known ones. Entity resolution asks whether the same person appears in multiple records, whether individual A, cited by French surveillance, is the same as AA, seen by Israeli intelligence, and AAA by American. Profile distances with domain-weighted variables. A street address match counts far more than a zip code match. Can be combined with network similarity. ANAA, embedded in nearly identical connection sets, are almost certainly the same person, while AAA's network differs. The method is used far beyond counterterrorism. Customer record management must flag later contacts as the same returning customer, and a telecom used link resolution to catch debtors who disappeared and reappeared under new accounts. They're called networks with a stable fingerprint. Collaborative filtering, too, can combine network metrics with ordinary distances. The illustration is elegant. User A's nearest neighbor by normalized demographics is user C, but when shortest path distances in the social graph are folded in with equal weight, user B becomes the closest, and the weights, chosen by business judgment rather than science, decide who gets the recommendation. Beyond recommendations, network analysis identifies clusters of similar individuals, finds influential people to target with promotions, and, sometimes, helps control the spread of disease and information. Link prediction: score potential pairs by similarity, shortest path, common neighbors, edge weight, and predict the closest unlinked pair. Entity resolution: match records across sources by weighted profiles plus network similarity. Customer deduplication, fraud, surveillance. Collaborative filtering: blend network distances with standard distances to drive recommendations. Business uses of social network analysis. The key value of social network data is what connections reveal about individuals' needs, desires, and tastes. Capturable without measuring them directly, and often user-provided rather than actively collected. The social media giants built enormous value on exactly this: real-time, individual-level information for targeted advertising, the holy grail of the business. The most famous demonstration was the 2016 presidential campaign, whose digital director credited Facebook as the method: 50,000 to 60,000 differently targeted ads a day, finding 15 persuadable people in the Florida Panhandle that a TV buy could never reach. Traditional businesses use their own networks, mapping internal relationships to find influential employees and optimize teams, analyzing supply chains for risk, tracking disease spread and referral patterns, tailoring social interventions. Law enforcement is a heavy user. Network analysis handled drug money laundering, 2 to 5% of world GDP, per the UN, well, because the event of interest is rare and the visualizations communicate, and the FBI's Anim operation, distributing over 12,000 encrypted phones whose traffic flowed straight to law enforcement, generated far too much data to review manually. needing network methods at minimum for triage. The chapter closes with the hazards. The trend is toward less public access to social data. The EU's Digital Services Act and privacy concerns pressures. Rapid sharing plus powerful recommender systems can magnify malignant social movements. And engagement with social media, however valuable, is distinct from the analytics this chapter teaches. Every organization should know what it is actually doing. Value: targeted advertising from connections without direct measurement. Internal team and supply chain insight. Law enforcement triage. Hazards: declining data access, privacy scrutiny, and recommender-driven amplification of harmful content. Quote, network analysis can take this unstructured data and turn it into structured data with usable metrics. These metrics can be used not only to describe the attributes of networks, but also as inputs to more traditional machine learning methods. Chapter 21. Text Mining. Introduction. Until now, the data have been numerical, binary, or multi-category. But in many predictive applications, the predictors arrive embedded as text. An internet service provider wants an algorithm to separate urgent support tickets from routine ones. A law firm in discovery wants document classified as relevant or irrelevant. Text mining methods have grown on the back of social media and web text, blogs, forums, reviews, news, and are increasingly applied to contact center notes and transcripts. The tabular representation of text, term document matrix, and bag of words. The foundation is the term document matrix. In the three-sentence example, this is the first sentence. This is a second sentence. The third sentence is here. Each word, term, becomes a row, and each sentence, document, a column. The cells count the term's frequency in that document. This is the bag of words approach. The document is a collection of words, and order, grammar, and syntax do not matter. What was unstructured text is now a data frame like any other, ready for clustering, classification, or prediction once an outcome is appended. The simplicity ends there. Real text needs considerable pre-processing before the matrix is usable, and human review is often indispensable. Term document matrix. Terms as rows, documents as columns, cells as counts. The bag of words ignores order, grammar, syntax. Bag of words versus meaning extraction at document level. Text mining can aim at two distinct goals. Labeling or clustering documents requires a sizable corpus, extractable predictors, and for classification, many pre-labeled documents, and it uses the standard predictive models already covered. Extracting the meaning of a single document is far more ambitious. It requires the computer to master grammar, syntax, and punctuation, to track word order. San Francisco beat Boston is not Boston beat San Francisco, and to resolve ambiguity. Hitchcock shot the birds in Bodega Bay might read as bird hunting to someone unfamiliar with the film. The book stays with the easier goal, probabilistically labeling or clustering documents. Meaning extraction is the province of natural language processing, NLP. Text mining versus NLP. Probabilistically labeling many documents uses standard models. Extracting meaning from one document requires comprehension, the harder natural language processing goal. Pre-processing the text. Real documents are messy. Extra spaces, emoji, incorrect capitalization, misspellings, and the pre-processing rules must match. Tokenization divides the text into tokens, the basic unit of analysis. A word separated by spaces, 23 as one token, but 2 plus 3 as 3, punctuation as its own token. The tokenizer's delimiter rules shape everything. Scikit-learn's count vectorizer by default discards numbers and punctuation, and a custom token pattern can keep an emoji or the doubled exclamation marks as meaningful tokens. For a large corpus, the token count explodes. The English language has over 1 million words, so vocabulary reduction is essential. Stop-word lists automatically remove the frequent, mostly meaningless terms. Scikit-learn ships 318, an application-specific boilerplate, a law firm signature block, can join them. Further reduction. Stemming collapses word variants to a common core, sentence, sentences, sentencing to sentenc, Frequency filters drop terms that appear nearly everywhere or almost nowhere. Synonyms consolidate. Lettercase is ignored, and normalization replaces classes of specifics with a category token. Email addresses become email token, numbers number token. After tokenization, stop word removal, and stemming, the four-sentence example collapses from a dozen terms to just 3 unique ones. The bag of words can be expressed as frequency or presence/absence. Frequency suits a support ticket where IP address matters only if repeated. Presence/absence suits a forensic model where a vendor name is decisive however often it appears. Binary equals true. Term frequency, inverse document frequency, TF-IDF, blends both. It multiplies a term's frequency in a document by a corpus-wide inverse document frequency, so it rewards terms frequent in a document yet rare overall. This, which appears nearly everywhere, scores low, while first appearing once in one document scores high. It identifies documents with frequent occurrences of rare terms. Latent semantic indexing, LSA, is principal components for text. It reduces the vast term document matrix to a small number of concepts, linear combinations of correlated terms. The worked intuition. If alternator always appears with battery and headlights, and brake with pads and squeaky, the 4 terms collapse into 2 concepts, brake failure and alternator failure. The penalty is interpretability. Beyond such toy examples, the concepts are opaque, and the model becomes a black box for prediction. Word 2 vec and glove go further, representing each word as a high-dimensional vector learned from context so that semantically related words sit close together. Word 2 vex train vectors famously make vector, Paris, minus vector, France, plus vector, Italy, is almost equal to vector, Rome. Tokenization. Delimiters divide text into tokens. The tokenizer's rules decide what counts. Numbers, punctuation, emoji. Vocabulary reduction. Stop word lists, stemming, frequency filters, synonym consolidation, case folding, and normalization, category tokens. TF-IDF. Rewards terms frequent in a document yet rare corpus-wide. Latent semantic indexing reduces terms to concepts at the cost of interpretability. Word embeddings. Word 2 vec and glove map words to dense vectors so similar meaning words sit close. Vector arithmetic can track analogies. Paris minus France plus Italy is almost equal to Rome. Implementing machine learning methods. After pre-processing, the text is a numeric matrix ready for the standard machine learning methods. Clustering to group documents, prediction for outcomes like time to resolve on support tickets, and above all classification, labeling. Standard models on text. Once in matrix form, clustering, prediction, and above all classification, labeling, apply as usual. Example, online discussions on autos and electronics. The classification example classifies 2,000 internet discussion posts, 1,000 auto-related, 1,000 electronics-related from pre-labeled groups. The pipeline, import and label records by file path, pre-process, tokenize, stem, remove stop words, compute the TF-IDF matrix, and reduce what will be 13,515 predictors to 20 concepts via latent semantic indexing, truncated SVD plus normalization. A logistic regression on the 20 concepts reaches 95.63% holdout accuracy, and the decile-wise lift chart shows the ranking power. Lift just under the maximum of 2 for the top half of records, near 0 for the last 40%, meaning the middle rank 20% is where human review should concentrate. The same flow handles prediction simply by replacing the class label with a numeric value. Pipeline, label, pre-process, TF-IDF, LSA to 20 concepts, then logistic regression, 95.6% holdout accuracy, with lift concentrated at the top of the ranking. Deep learning approaches. Deep learning sequence handling models, RNN and LSTM from Chapter 19. Suit text because word order carries meaning. Text is represented by embeddings like word 2 vec, and these models grew into today's large language models, LLMs, for classification, summarization, question answering, and translation. The early landmark was BERT, a transformer built on self-attention. The model weights each token by its importance and position, reads bidirectionally, both preceding and following words, and masks words to predict from context. Attention's independent parallel tasks are a huge speed advantage, enabling the specialized chips built for video games. Where word2 vec and glove give each word a static vector, BERT's embeddings are context-dependent. Bank is represented differently in picnic on the bank of the river than in deposit money at the bank. LLMs also learn their embeddings during training rather than from a pre-trained table at the cost of enormous pre-training data and compute, which is why they outclass simple word2 vec plus supervised pipelines, and why the newest generation, GPT, adds text generation on top. BERT and transformers. Self-attention weights each token by relevance. Bidirectional context produces embeddings that vary with context, bank by the river versus the money bank. Scale. LLMs need enormous pre-training data and compute, which is why they outclass simple word2 vec plus classifier pipelines. Example: sentiment analysis of movie reviews. The sentiment example classifies 10,000 IMDb reviews, 5,000 positive, 5,000 negative. Two embedding routes are compared on the same logistic regression. Glove embeddings, 400,000 words, 100-dimensional vectors. Replace each word with its vector, average them into a sentence vector, and feed the 100 predictors to logistic regression, reaching 78.65% accuracy. A pre-trained transformer, all mini-LM L6 V2, produces sentence embeddings directly. The AUC improved from 0.8624 to 0.9072 and accuracy to 82.55%. The lesson is concrete. Richer, contextual embeddings outperform static averaged ones on the same classifier. Glove versus transformer. Averaged 100 D-word vectors reach 78.7% accuracy. A pre-trained transformer, mini-LM, reaches 82.6% with AUC up from 0.862 to 0.907. Summary. The chapter distinguishes extracting meaning from a single document, NLP, from probabilistically labeling many documents, text mining, and concentrates on the latter. Pre-processing, more involved than numerical data preparation, produces a term document matrix. Vocabulary reduction tames the excess of terms, and dimension reduction to concepts makes the matrix tractable. Documents then classify with the standard methods, and modern LLMs with contextual embedding outperform simpler approaches on many text mining tasks. Quote, "The general idea of TF-IDF is that it identifies documents with frequent occurrences of rare terms. TF-IDF yields high values for documents with a relatively high frequency for terms that are relatively rare overall and near zero values for terms that are absent from a document or present in most documents." Chapter 22, Responsible Data Science. Introduction. Machine learning promises seemingly unlimited good, but conversations about the benefits too often ignore the harms the models can cause. The chapter's focus is deliberately on the unintentional kind, models built with good intentions that nevertheless exhibit bias or unfairness. The Compass recidivism algorithm is the motivating example. Northpoint's proprietary system, with more than 170 predictors, informs sentencing by predicting which defendants will reoffend. Its advocates point to good overall performance and similar accuracy, measured by ROC area, for African American and white defendants. Its critics charge bias. The two claims are simultaneously true and the source of the harm. The errors are quite different. African American defendants are overpredicted to reoffend, drawing tougher sentences. White defendants are underpredicted, drawing lighter ones. The two error types balance out to the same overall rate, so a single-minded focus on overall accuracy obscures the bias. The whole chapter will rebuild this example under a responsible data science lens. Unintentional harm. Compass did not set out to penalize African Americans. Its intent was more consistent, more scientific sentencing, yet the bias was real and unwanted. The Optum healthcare algorithm shows the same pattern by a different mechanism. Impact Pro predicted patients' future need for follow-up care from prior healthcare spending. Better care timing, better resource management, and better insurance rates were the intent. Obermeyer's research found that at any given risk score, African American patients had more chronic conditions than white patients. Because African American spending on healthcare ran lower, driven not by better health, but by lower incomes and less access to insurance and costly facilities. The algorithm predicted less need for follow-up care for a black individual with the same health as a white one. The bias was an artifact of a proxy variable. Well-intentioned social algorithms likewise build communities and also nurture hatred and false news. Intended harm is a separate, darker catalog. Fake reviews weaponized by bad actors, facial recognition that tracks down suspects, good, but also enables immigration sweeps, bad. Surveillance of Uyghur and Tibetan communities, worse, and turning a blind eye. Executives knowing their algorithms harm teenagers and foster discord, yet leaving profitable platforms unchanged. A framework cannot stop the determined malefactor, but can make developers anticipate how their work might be misused. Proxies encode bias. Optum used prior spending to predict care need. Spending is lower for African Americans for access reasons, not health, so care was underpredicted. Legal considerations. Legal compliance is ultimately for attorneys. Data scientists contribute best by pursuing a framework. Two legal foundations frame the discussion. The EU's GDPR 2018 gives those in the EU sweeping protections: the right to be forgotten, data portability, the right to object to automated decision-making and profiling, and as the first comprehensive big data regulation, set the pattern for California's CCPA and Canada's PIPEDA, becoming in effect a global regime. Its focus is individual privacy, so the 2024 AI Act targets societal harms, dividing AI risk into unacceptable, high, limited, and minimal categories, with obligations escalating accordingly and full implementation expected by 2026. On discrimination, the guiding principle is that laws restricting behavior do not vanish because decisions are algorithmic. What is illegal for a human, lending discrimination by gender or age, is illegal for an algorithm. Protected groups by race, gender, age, sexual orientation, disability, and more carry long-standing legal protections, and fairness metrics are computed relative to a designated privileged group, a technical base for comparison, not a moral claim. GDPR and AI Act, individual privacy rights, and a four-tier risk regime. Anti-discrimination law does not vanish because decisions are algorithmic. Protected and privileged groups, race, gender, age, and more carry protections. Fairness metrics need a base, privileged, group for comparison. Principles of responsible data science. Legal compliance alone does not prevent harm, and reputational harm can match legal jeopardy. Facebook's reputational reviews exist precisely to anticipate how algorithms might be criticized. 5 principles recur across responsible data science frameworks. Non-maleficence, avoiding harm, is the hardest to guarantee. A model can be fair, transparent, accountable, and private yet still harm. A triage algorithm necessarily pushes some people to the back of the queue. A credit score makes life difficult for low scorers. It is a goal to strive toward, considered in context, more than a box to check. Fairness covers equal representation, non-discrimination, and just outcomes, evaluated primarily by whether outcomes are fair. Input details matter less. It is genuinely hard to define. Fair taxation has no unique universal meaning. Yet because it centers on outcomes, it is more implementable than the other principles, though fairness-improving methods remain underused, and its relevance extends beyond people, to making a spam filter equally accurate across topics. Transparency records the modeling decisions and communicates them via documentation. But what satisfies the modeling team, regulators, users, and clients may diverge. Closely related is interpretability. Black box models, neural nets, random forests, boosted trees offer little insight into which predictors drive biased outcomes. Classical models like linear and logistic regression are intrinsically interpretable. The two-pronged strategy. Keep an interpretable model among the finalists as a benchmark. Learn how much performance a black box buys, and apply interpretability methods ex post to any black box that wins. Accountability means legal compliance, integrity, responding to affected individuals, and recourse. A lonial should come with an explanation, an appeal, and what would have changed the decision, though in practice it rarely exceeds legal compliance. Privacy means gathering only necessary data, storing it securely, de-identifying before use, and preventing model results from leaking other user data. Differential privacy, adding randomization, is the robust safeguard but is not yet built into popular packages. 5 principles: non-maleficence, fairness, transparency, accountability, privacy. Interpretability. Black box models hide, which predictors drive bias. Keep an intrinsically interpretable baseline and apply ex post methods to black boxes. A responsible data science framework. The framework turns principles into practice across the phases of a project. Justification starts with the business context and asks whether similar projects hit ethical problems, what harms might ensue, and whether the team can assess them. Assembly gathers the raw data, the software, data sheets, and the protected group identification, and here privacy rules must be honored. Clearview AI's scraping of social media for facial recognition and the Cambridge Analytica FAIR, a quiz app that harvested 87 million users' data through friends, showed data acquisition ethics and failure. The test for gray areas are the project's importance, the explicitness of the rules, and the news story test. Data preparation must not distort raw data toward bias and may be iterative. An audit finding a poorly represented group sends the team back to oversample it. Modeling adds interpretability to predictive performance. Auditing, the key stage, reviews explanations, checks for bias against protected groups, and mitigates. Oversample underrepresented groups, deepen interpretability, and, where needed, adjust predictions themselves. Proxies complicate everything. Excluding race as a predictor is not enough when membership in an African American fraternity or the women's chess club stands in for it. The Amazon resume model picked up an implicit preference for men from training data and derived gender proxy features. Race may, however, be legitimately included in a second, diagnostic model whose only purpose is to investigate whether some other feature is correlated with race and whose business necessity must then be justified. Phases: justification, assembly, preparation, modeling, auditing, with oversampling, proxy detection, and threshold adjustment as the audit's mitigations. Documentation tools. Several tools structure the documentation. Impact statements, required by NeurIPS for 2020 and adopted by the AI giants. Answer 5 questions. The project's goal, expected benefits, relevant ethical concerns, prior similar attempts and their outcomes, and anticipated future uses. Model cards standardize a model's performance and non-technical characteristics, purpose, version, owner, references, use case, limitations, ethical considerations, performance plots, adopted by IBM, fact sheet, Microsoft, Azure Transparency Notes, and OpenAI, with Google's Model Card Toolkit automating generation. Data sheets are the nutrition labels for data sets. They standardize data dictionaries and add the collection process, intended uses, sensitive features, transformations, sampling, license, and copyright. Yet, because data preparation is often treated as tedious, model cards have caught on faster than data sheets. Audit reports capture what cards and sheets cannot. The process of verification and fixing. A general performance summary and detailed per sensitivity group pages comparing candidate models, showing interpretability outputs, and describing findings. They may feel burdensome, and most real projects skip most of them, largely why so many ethical failures happen. But as a superstructure, they invite selecting the elements that matter for a given project. Unstructured data deserve a special warning. Image and text models are almost always black box neural nets, so no interpretable benchmark exists. An interpretation must come from ex post methods aimed at individual cases, never reaching the simplicity of a regression coefficient. Impact statements. Goal: benefits, ethical concerns, prior attempts, future uses. Made famous by Nur IPS 2020. Model cards and data sheets. Nutrition labels for models and datasets. Audit reports capture the verification process the snapshots miss. Example: applying the RDS framework to the Compass example. The Compass story is rebuilt under the framework. Unanticipated uses to flag. The system could migrate down the justice process to affect whether someone is even identified as a criminal, and it could be exported to authoritarian systems predicting a broad range of criminality. Ethical concerns are historical and specific. Since the post-Civil War era, African Americans have been burdened with criminal histories used to coerce labor, and their over-policing is a documented legacy, so discrimination against them warrants special alertness. Protected groups are formally identified, all racial categories, plus gender and age, though those may stay as predictors here since the concern is race. Data issues are real. ProPublica obtained Broward County records via a public records request, yielding 7,214 defendants, 51% African American, 34% white. Cleaned to 5,304 by dropping misdated charges and traffic offenses and applying a 2-year recidivism definition, a definitional choice that can shift conclusions. Fitted on age group, charge degree, sex, and prior count. The models differ in transparency. The logistic regressions coefficients read plainly. Being male multiplies recidivism odds by 1.62. Being over 45 versus under 25 divides them by 4.3. Each prior crime raises them by a factor of 1.18, while the random forest awaits ex post interpretation. Their accuracy, 71 to 72%, modestly beats the naive 64%, and both use a handful of predictors to outperform the proprietary 170-plus predictor Compass, itself a red flag in an audit. Disaggregating by race exposes the story overall metrics hid. Accuracy ranges 6.3 points and AUC over 9 points across groups, and the false positive rate for African Americans is nearly double that of any other group, while their false negative rate is lowest. Harmful errors for individuals come at the top of the list for Black defendants. Interpretability methods illuminate what drives the outcome. Permutation feature importance shows prior convictions dominant, age second. Partial dependence plots show recidivism probability rising with prior count. The plausible, expected finding. Reducing dimensionality finds only 2 strong predictors, ruling out recombinations. Oversampling cannot help because African Americans are already plentiful. An 85% bootstrap augmentation leaves false positive rates above 15% versus 11% for whites. So the model itself cannot be sufficiently corrected with the existing data, and the research question remains. Perhaps a prior conviction is not as meaningful for African Americans, who are over-policed yet less prone to future crime than their records suggest. The practical path is threshold adjustment. Classify at 0.625 for African Americans and 0.45 for whites. Separate thresholds that balance the false positive rates and quantify the bias the model encodes. Audit findings. A few predictor logistic model equals the 170 predictor Compass. Per race FPR for African Americans is nearly double. The bias overall accuracy hides. What works? Recombinations don't, few strong predictors, and oversampling doesn't. Group already plentiful. Separate thresholds, 0.625 versus Chapter 0, verse 45, bring false positives into balance. Summary. Machine learning models can aid authoritarian governments, amplify autocracy even in democracies, and, with the best intentions, encode and amplify the biases built into their training data. The responsible data science framework of justification, assembly, preparation, modeling, and auditing minimizes the probability of such harm, though it cannot guarantee against it. The ever-present danger is that a framework decays into a rote checklist. Building a good model takes domain knowledge and full understanding of the business context. Protecting against harm takes the same judgment extended to the broader context. the ability to step back from a model that performs a little better than its competitors and ask what, beyond accuracy, it is really doing. Quote, building a good technical model requires domain knowledge and full understanding of the business context. Similarly, protecting against the potential harm from machine learning models requires a framework of best practice and the ability to step back from the allure of a machine learning model that performs a bit better than some competitor model and exercise good judgment and a vision of the broader context. Chapter 23, Generative AI. The transformative power of generative AI. No machine learning technology has generated as much fanfare. The public availability of tools like OpenAI's ChatGPT, where anyone types a prompt and gets impressive results, drives constant press coverage and speculation about artificial general intelligence, AGI, capabilities similar to human intelligence. OpenAI states its mission as building safe and beneficial AGI. AGI remains in the future. What is more tractable to imagine is machine learning graduating from very specific tasks, predict air travel demand, through more general ones, make airline operational decisions, to high-level strategic recommendations. Awe is warranted, but a closer look reveals two dimensions to language generation. The models have comprehensively learned the structure of language, grammar, vocabulary, syntax, style, and they have learned role and voice, the subset of language options appropriate to a given situation. Both are remarkable. Both require enormous training data and time, and both have mimicry at their heart, not independent creation. The surrounding debate is loud. Pichai calling generative AI more profound than fire or electricity. Polls of experts assigning it a 12% chance of decimating humanity by 2100. A Japanese corporate manifesto warning of democracy's collapse, and Musk calling AI a potential existential threat. AGI speculation. Public models plus the promise of AGI drive the frenzy. The sober view is that the models have learned language structure and role/voice. Mimicry, not independent creation. What is generative AI? Generative AI is a class of models that produce text, images, audio, or video from a user-supplied prompt, an extension of the supervised learning and deep neural nets of earlier chapters. Large language models, LLMs, like ChatGPT and Gemini, are trained on a huge volume of online content. They're cagey about specifics. At heart, they perform the old, familiar task of predicting the next word, the engine behind search and autocomplete for decades, but with the crucial addition of context. Each generated word depends on a long, sometimes page-long, sequence of prior words in the prompt, and must follow grammar, syntax, and the prompted style. The answer draws only on training data. The model cannot know what happened after it was trained. The machinery builds on earlier ideas, the higher-level feature learning of deep learning, the word embeddings of Chapter 21, the RNN and LSTM text networks of Chapters 19 and 21. But generation needs to relate words that may be far apart, and the mechanism is attention. A series of matrix operations computes attention scores for every token pair, converts them into weights, and revises each word's embedding to emphasize the most relevant content wherever it sits. Attention demands parallelizable computation, which is precisely what GPUs, graphics cards built for computer games, supply, which is why NVIDIA, their primary maker, became the great beneficiary of the generative AI boom. Image generation combines text processing with image synthesis. The dominant diffusion approach. Assemble real images with text descriptions, embed the text, create a random noise seed image, denoise it iteratively toward the real image while incorporating the embedded text conditioning. Train by comparing the denoised image with a reference, and, once trained, generate images from text alone. Text and image are both represented as high-level numerical vectors and can, in effect, speak the same language, alignment learning. Earlier architectures include GANs, which pit a generator against a discriminator that learns to tell real from fake, and variational autoencoders, which seed from the latent feature space. LLMs predict the next word given a long context. An old autocomplete idea scale with attention to relate distant tokens. Attention and GPUs. Attention scores re-weight every token pair's relevance. Parallelizable computation made GPUs and NVIDIA the infrastructure winners. Diffusion image generation. Denoise a random seed toward a text-conditioned image. GNs and variational autoencoders are earlier architectures. Data and infrastructure requirements. Scale is the defining fact. The tiny illustrative network had a dozen parameters. GPT-4 has 1.5 trillion. GPT-3 was said to be trained on the entire internet, taking weeks across thousands of computers and the daily electricity of a city of 280,000. And by one forecast, future LLMs will require an entire 100,000 server data center per model. Computation happens in the cloud. Electricity demand, flat in the U.S. for years, began surging, enough by 2030 to power New York City 7 times over, fueling a nuclear renaissance. Amazon bought a reactor-equipped data center. Microsoft is restarting 3 Mile Island. Google finances 7 reactors. The gold rush echoes 1848 California. The miners rarely struck it rich. The merchants selling them goods did. So, too, NVIDIA's market value went from about $10 billion to nearly $3 trillion, while many AI hype companies lack a clear business model. Trillion parameter scale. GPT-4's 1.5T parameters, entire internet, training, weeks of compute, and surging electricity. The gold rush sells picks, not gold. Adapting models for specific purposes. Private, domain-specific data is where generic models fail. GPT cannot report on a drug distributor's prescription patterns because the public internet lacks the data. Fine-tuning trains the pre-trained model further on domain data, a call center's query. Response pairs teaching it to answer new queries. Retrieval Augmented Generation, RAG, instead specifies or retrieves a reference set of records relevant to the query and lets the LLM craft a flowing response from them. The model is not trained on the records at all. RAG wins when reference records change often and when closeness-based retrieval suffices. Fine-tuning wins when deep knowledge of the reference data is required, medical diagnosis, because it actually modifies the model. Fine-tuning. Further train a pre-trained model on domain data when deep knowledge is required. RAG. Retrieve relevant records and let the LLM craft the response. Best when records change often and closeness search suffices. The model itself stays unchanged. Prompt engineering. Prompts conduct a conversation, not a one-shot search. The model handles specific, detailed queries, responds at length, remembers its own prior answer, and refines on follow-ups. The most important attribute of good prompts is high-quality writing. Clarity. The model ingests your query literally. Adequate context, specificity. The specific trumps the general, and clean grammar. Open-ended prompts. Tell me about. Suit early exploration, but invite the model to fall back on its well-learned, possibly irrelevant, content. Summarization and follow-up requests are strengths. Tune conversation is a real skill. Duolingo supports learner-level dialogue that references prior sessions. A flower described earlier calls back to your blue vases mentioned in a previous conversation, a feat of conversational memory. Good prompts are good writing. Clarity, context, specificity, grammar, and follow-ups, since the model remembers its own prior response. Uses of generative AI. The most compelling near-term uses are incremental improvements to existing processes, not science fiction. Mass General Brigham physicians record sessions and let generative AI turn them into grouped, summarized clinical notes. Lawyers get conversational research, drafting, summarization, document analysis, and link citations. LexisNexis's advantage strengthens precisely because the enormous data hunger of these models favors its proprietary legal corpus, said to be 790 times Wikipedia's volume. Coding has been transformed as LLMs master programming languages. Game producers use reinforcement learning plus generative AI for personalized enemies and quests, a capability that also personalizes casino games and can deepen compulsive gambling. The Wall Street Journal's Joanna Bot, Gemini flash-tuned on a reviewer's past columns and Apple specs. illustrates that many applications are about convenience. Users could research iPhone upgrades themselves. The bot just makes it faster, and an untuned GPT gives similar but less specific answers. Other business cases: drafting first versions of marketing documents, gathering evidence on fraudulent transactions, and augmenting marketing response models. Generative AI also augments training data, producing variants of costly brain scans, like Smote's synthetic minority records or jittering in plots, to enrich underrepresented classes. The limits are sharp. Generated data inherits gaps in the original, garbage in, garbage out, may carry its own artifacts, and as ever more AI-written content floods the web and gets swept into training corpora, degrades model accuracy, in severe cases causing model collapse. This circular training is termed data cannibalism. Deployment ranges from a free account to tuned, integrated applications. Customer support tuned for airline reservations and embedded in operations, APIs for company developers, SaaS and consulting. The revenue model, so the offerings will deepen and cost more, with care that systems cannot be abused. Copilot is now in Microsoft Office and GitHub. Google plans generative features for Workspace. Business uses: clinical notes, legal research, code, drafts, ad copy, fraud evidence, and training data augmentation. Data cannibalism: AI-generated content re-entering training corporate degrades models, in the extreme causing model collapse. Caveats and concerns: generative AI is early stage and prone to hallucinations, elaborate factual errors. A lawyer who trusted ChatGPT with an entire legal motion was fired and his firm fined when his impeccably formatted citations turn out fictional. Businesses hesitate to replace rule-based chatbots because even rare inflammatory errors can trend and harm reputation, as Microsoft's Tay, which learned racist, sexually charged posts from Twitter, demonstrated. The root cause is the model's perfect command of language without reliable command of fact, a very human failing, compounded by training data that mixes genuine value with froth. Code assistance can muddy audit trails and compliance. Fine-tuning on company data can leak confidential information. Goldman Sachs banned popular tools until it built a controlled internal platform. Entertainment faces its own legal knots. Generating images of actors is constrained even under new contracts. A 2024 California law lets performers exit contracts over unauthorized voice or likeness use. Training data carries intellectual property risk, and studios are reluctant to hand film libraries to third parties. Deepfakes: a Harris video. This is diametrically opposed and reposted by Elon Musk. Classmates' faces grafted onto nude bodies. HeyGen's lip swap app, abused to create promotional videos of unwitting celebrities, have put the technology in anyone's hands, magnifying the Chapter 22 harms. Hallucination and risk: perfect language without reliable fact. The lawyer's fictional citations, audits, confidentiality, and legal hazards. Deepfakes put impersonation in anyone's hands. Summary: generative AI produces well-written text, images, and video from prompts, built as an extension of deep learning and enormously more complex. Trillions of parameters, massive data sets, commensurate computing, and electricity. Its generality is both strength and cost, so fine-tuning and RAG adapt it to specific purposes. Its economic promise is real, especially improving human-involved processes, drafting reports, generating ad copy, interacting with customers, writing code, and its power heightens the urgency of responsible use. LLMs in video generation can impersonate and deceive. Balancing transformative potential with ethical safeguards will determine whether its impact is positive. Part 8: Cases. Chapter 24: Cases. Charles Book Club. The Cases chapter turns the book's machinery loose on real business problems. The Charles Book Club case is the classic database marketing problem. The U.S. book industry, 50,000 new titles a year, a $25 billion market, changed fundamentally by discounting superstores and then by Amazon, pressures book clubs, which once relied on continuity programs, monthly shipments the reader accepts at sign-up, and negative option programs, The selection of the month arrives unless the reader explicitly declines, a model that breeds dissatisfaction and mailing costs. Charles Book Club, CBC, founded in 1986 on the premise that deep understanding of customers could differentiate it, built a database of 500,000 readers from enrollment inserts, but saw profits fall as mailing volume climbed. Its solution is database marketing. For each new title, test on a random sample of 4,000 customers, build response models, score every customer, and mail only to those above a threshold. The art history of Florence is the test, with the data partitioned into training, 1800, validation, 1400, and holdout, 800. The assignment walks through the modeling decisions. RFM segmentation partitions customers by recency, frequency, and monetary value into 60 combinations, finds those with above-average response, and draws a 3-point lift chart for 3 response rate tiers. K. Nearest neighbors classifies by proximity on recency, frequency, monetary, months since first purchase, and related book purchases. 10-fold cross-validation choosing K, normalization required, producing both classifications and propensities. Logistic regression builds 3 models, full 16 predictors, a best subset, and RFM only, each yielding well-defined purchase probabilities and lift charts. The final step is the discipline this book teaches throughout. Choose the best model on the validation evidence, then estimate its true performance on the holdout set before deploying. RFM segmentation, recency, frequency, and monetary cells, 60 combinations, with above-average response drive the mail target, the industry baseline. Model trio, K, nearest neighbors on proximity variables, 3 logistic regressions, full/best subset, /RFM only, compare by validation lift, confirmed on holdout. German credit. The German credit case confronts a historically rooted problem. Money lending long ran on reputation and incomplete data. Thomas Jefferson borrowed all his life, unreliably, and kept being lent to until the 20th century's retail credit company, now Equifax, with TransUnion and Experian, systematized credit risk, pushing out individual judgment in favor of huge predictive databases. The dataset holds 30 variables and 1,000 applicants, 700 rated good credit, 300 bad, with the consequences of misclassification explicitly quantified. Incorrectly accepting a bad risk costs 5 times what correctly accepting a good risk earns, formalized in an opportunity cost and average net profit table. The assignment is first to reason about the predictors, checking account status, credit history, purpose, amount, employment, age, foreign worker status, and more, then to fit logistic regression, classification trees, and neural networks, reporting each model's confusion matrix and cost/gain matrix on the holdout to find the highest net profit. The refinement is the lesson of Chapter 5. Rather than accepting the model's default classifications, use the logistic propensities to rank applicant from best to worst credit. Plot a cumulative gains curve of net profit against the number accepted and find where net profit peaks and what probability of success threshold that implies for scoring future applicants. Cost asymmetry. Accepting a bad risk costs 5 times the benefit of accepting a good one. So rankings and propensities, not raw accuracy, drive net profit. Taco Software Cataloger. Taco is a software catalog firm whose customer list is a key asset. It joined a consortium that pools member lists, drawing 200,000 names for a mailing after contributing its own 200,000. To select names, it ran a test mailing of 20,000 names, 1065 purchasers, a 5.3% response, and analyzed a stratified sample of 1,000 purchasers and 1,000 non-purchasers, requiring a 0.107 adjustment back to the true response rate. The case has 2 outcomes, whether a prospect purchased and how much they spent. The assignment develops 2 models, a logistic regression with L1 regularization to classify purchasers, yielding the probability of purchase, and, among purchasers, multiple linear regression with stepwise selection and a regression tree to predict spending chosen on validation performance. The capstone combines them on the holdout. Multiply the oversampling adjusted Purchase probability by the predicted spending to get expected spending per customer. Plot its cumulative gains curve, and estimate gross profit from mailing the remaining 180,000 names. The entire predictive machinery aimed at one business number. The data for this hypothetical firm come from a real software catalog company and the consortium concept from the Abacus Catalog Alliance. Two-stage prediction. Classify purchasers, L1 logistic, and predict their spending, regression tree / stepwise. Then multiply adjusted probability times predicted spend for expected value. Oversampling adjustment. The 50-50 stratified sample scales back by 0.107 to the true 5.3% response for honest profit estimates. Political persuasion. The political persuasion case is the uplift modeling story told in Chapter 14, grounded in the true history of predictive analytics entering U.S. politics. Campaigns are less about persuading people to switch sides than persuading those who agree with you to vote. Individual targeting via surveys was effective but prohibitively expensive, and in 2004 John Kerry's Iowa caucus upset came in part from using predictive models about individual voters to shift resources to the close precincts. The three traditional targeting forms, geographic, demographic, individual, each carry limits that predictive analytics at the individual level overcomes. A model rolls predictions out to the entire voter base, not just those surveyed. The data are actual voter records, public voter files, party poll watcher derived data, census neighborhood data, purchase consumer and demographic data, augmented with a hypothetical experiment. Pre-survey, random split into control and treatment, a pro-democratic flyer to the treatment group, post-survey. The task is to build an uplift model predicting each voter's increase in propensity to move in a democratic direction from the flyer. The assignment is carefully sequenced. Assess the flyer's overall effect, explore the predictors, fit 3 models on the provided partition, and choose the best. Score the holdout under the actual treatment, and again under a reversed flyer variable. Compute each voter's uplift as the difference in propensities, and finally determine the uplift threshold for mailing the flyer to only 10% of voters. A direct exercise in deciding whom to contact with limited resources. Uplift targeting. Rescore each voter under the actual and reversed flyer variable. The difference in propensities is the per-voter uplift to rank and threshold. Taxi cancellations. The taxi case comes from yourcabs.com, a Bangalore taxi booking portal, which by late 2013 faced drivers not showing up for book calls. Cancellations that stranded customers in a city where a tech-driven ride-hailing era was just beginning. Uber started in Bangalore in mid-2014. The company posted its 2011 to 2013 booking data as a Kaggle contest. In this case, uses a 10,000 booking subset with 17 input variables: user ID, vehicle model, online versus mobile booking, travel type, booking package, geography, and trip date and time, to predict the binary indicator cancellation, which runs 7 to 8%. The assignment foregrounds the 2 uses of the model: prediction, which bookings will be canceled, to intervene, and profiling, what predict cancellations to understand them. The practical coaching is itself a lesson in messy real data. Defer the GPS challenge since other geographic fields exist. Decide how to handle missing values. Mind the date and time fields, and think about which categoricals to dummy. Models are then fit and judged twice, by error rates, the confusion matrix, and by ranking lift, with a candid question of whether the model can actually be used in practice. Prediction plus profiling. Use the model both to flag likely cancellations and to explain them. Judge by confusion matrix and lift. Segmenting consumers of bath soap. The bath soap case puts clustering to work in consumer goods marketing. CRISA, an Asian market research agency, tracks purchase behavior for consumer goods across Indian urban households, from transaction data and household data that include demographics, durable goods possession, and affluence index, and monthly purchase data. Its clients traditionally segment by demographics. The forward-looking request is to segment instead on variables closer to the purchase process and brand loyalty, so promotion budgets can be deployed more effectively. Multiple promotions, each aimed at a tailored segment. The data profile each household. demographics, affluence, and purchase summaries over the period, number of brands, brand runs, consecutive purchases, volume, transactions, average price, promotion share, brand-wise purchase percentages, price category shares, and proposition category shares. Brand loyalty itself has three measurable facets: how many brands, how often the customer switches, and how concentrated purchases are across brands. The assignment is a complete clustering exercise. Choose K, guided by how many marketing approaches the strategy can sustain, 2 to 5. Decide how to treat the brand share percentages. A customer buying all of one brand is as loyal whoever the brand is. A distance measure on raw shares would be distorted. Consider a single derived variable. Run K. Means on behavior, on basis of purchase, and on both. Select the best segmentation. Characterize the clusters by their demographics, loyalty, and basis of purchase. And finally, build a model that classifies new households into the segments for targeting. Loyalty facets: number of brands, switching frequency, and purchase concentration. With brand share percentages collapsed, so loyalty is brand agnostic. Direct mail fundraising. The fundraising case is direct marketing under asymmetric costs and oversampling, explicitly pointing the reader to Chapter 5. A national veterans organization, one of the country's largest direct mail fundraisers, with 13 million donors in-house, mails at a 5.1% response rate. Donors give an average $13, and each mailing, with its personalized address labels and cards, costs $0.68. The sample is deliberately weighted to equal numbers of donors and non-donors. The assignment proceeds in careful steps. Partition 60/40. Build at least 2 classification models, abstaining from target_D, donation amount. Explain the reasoning for weighted sampling over a simple random sample. The rare, valuable responders must be dense enough to model. Then the distinctive step. Compute net profit on the actual 5.1% per 94.9% response distribution by dividing each holdout row's net profit by its oversampling weight, 9.8 for donors, 0.53 for non-donors. Draw the net profit cumulative gains curve for the models and select the model that dominates. Finally, score the future candidate dataset in descending donor probability and decide how far down the list to mail. The operational question every direct marketer faces. Weighted sampling. Equal donors/non-donors, let the rare 5.1% responders be modeled. Net profit gains undo the weighting, 9.8 for donors, 0.53 for non-donors. Catalog cross-selling. Exeter, a catalog firm, wants cross-selling. Once a customer has purchased from one catalog, enclose or link another catalog with a discount coupon. The essential question is which catalog to promote. The biggest cost is printing and mailing to people who buy nothing, so the choice should be informed rather than a random catalog. The data come from the DMEF's multi-division catalog company. The assignment is a focused association rules analysis. Interpret lift, confidence, and support in plain English, and form a rough estimate of how much better than random this will make the choice of which catalog to cross-promote to a purchaser. An exercise in translating the Chapter 15 machinery into a practical business value. Informed promotion choice. Association rules lift/confidence/support. Choose which catalog to cross-promote. Better than random. Time series case. Forecasting public transportation demand. The time series case is based on a 2006 business intelligence competition for Santiago de Chile's public transportation system, then undergoing reconstruction. A transportation company planning to buy buses and extend terminals needs reliable forecasts of passenger arrivals at its terminal, and the historic data are 15-minute interval arrival counts between 630 and 2200 hours over 3 weeks, with a future 3-day period to be forecast. The evaluation setup is the discipline of Chapter 17. Train on the first 2 weeks, test on the last, and judge not only MAPE, and RMSE, but time plots of actuals and forecast errors. The competition spot-ME criterion is deliberately replaced by the realistic business goal of reasonable forecasts on any time and day. The suggested steps are the chapter's method in full. Identify components, trend, seasonality, how many seasons, global or local patterns, Consider the data's frequency practically and technically. Compare weekdays and weekends. Handle missing values. Choose methods accordingly. And mind what a zero actual count does to MAPE. Workflow: train on 2 weeks, test on 1. Evaluate MAE/MAPE/RMSE plus actual versus forecast time plots. Components: seasons, weekday/weekend first. Loan approval. The loan approval case closes the book by combining its last 2 threads: responsible data science and classification. A data scientist at Universal Bank must develop a prototype automated loan approval model to compete with online lenders, using 5,000 records of prior applications and human decisions, and must do so under the Equal Credit Opportunity Act, with a 2-part reminder. The ECOA governs the basis for credit decisions, and proportional approval across groups is not the legal requirement. The assignment is the Chapter 22 framework turned operational. Identify and remove ECOA prohibited features, race, and the like. Explore approval rates by group. Fit several models on permitted features and evaluate sensibly. Then assess fairness across protected categories. Probe whether other variables serve as effective proxies for race. The correlation matrix is the tool. And implement any mitigations available in the data. The report should be short and candid. A draft to discuss with superiors. It is the fitting capstone. The whole toolkit deployed to a real decision, audited for the harm it could cause. ECOA discipline. Exclude prohibited features, then assess fairness across protected groups and hunt proxies, the correlation matrix, before any mitigation. Quote, both dimensions are remarkable and require huge amounts of training data and lengthy training times. However, both have mimicry at their heart, not independent creation. Conclusion. This book is not a catalog of algorithms, but a discipline, and its spine is the disciplined handling of data. Its central doctrine is that a machine learning model must be judged by what it predicts on data it has never seen. Hence the holdout set, the training validation holdout partition, and the ever-present danger of overfitting taught through the advertising curve that fits every point and predicts nothing. Around that spine, the authors organize the whole analytic toolkit. The preliminaries of supervised and unsupervised learning, data visualization and dimension reduction as the honest first contact with data, the elaborate machinery of performance evaluation, from the confusion matrix and the ROC curve to cumulative gains and lift and the adjustments that oversampling demands. Then come the methods themselves, linear and logistic regression, k-nearest neighbors, naive Bayes, classification and regression trees, neural networks and deep learning, discriminant analysis, and the ensembles and AutoML that combine them. Each presented with its worked example, its coefficients read in the author's plain register, and, crucially, its limitations stated without embarrassment. The linear trend that misses the U-shape, the regression tree built on a diagonal it cannot draw, the neural net that overtrains. What gives the book its coherence is the problem-first insistence that every choice be justified by the business goal. Prediction versus profiling, explanatory versus predictive modeling, global versus local patterns, precision against recall. Each opposition is resolved by asking what decision the analysis serves. The forecasting chapters carry this through time series. Components of level, trend, seasonality, and noise. Regression-based and smoothing-based families with their benchmark-naive forecasts and their honest failures on holdout. Autocorrelation and the 2-stage correction that turns forecast errors into information. The unsupervised chapters. Association rules with their support, confidence, and lift. Collaborative filtering with user and item-based variance. Clustering from distance metrics to dendrograms and k-means. Apply the same discipline to relationships among records. The later chapters widen the lens from technique to consequence. Experiments, uplift, and reinforcement learning make explicit what the earlier chapters implied, that analytics guides interventions on real people, with real responses and real costs. Social network analytics and text mining bring the book's methods to the data structures of the digital age, to whom you know, and what words reveal. Responsible data science then turns the lens on the field itself. The compass algorithm that is accurate overall yet biased in its errors, the proxy variables that smuggle in discrimination, the principles of non-maleficence, fairness, transparency, accountability, and privacy, and the framework of justification, assembly, preparation, modeling, and auditing that puts them into practice. The generative AI chapter closes the circle, showing the newest and most powerful extension of the deep learning the book taught, with all its mimicry, its infrastructure hunger, and its deepening of the same ethical stakes. The book's abiding lesson is that analytics succeeds where the business context is understood and the methods are understood in equal measure, and that the unglamorous steps, the data cleaning, the partitioning, the audit, are where its value and its risk actually lives. Its 10 closing cases, from the book club's response models to the loan approval audited under the ECOA, are not separate from the methods, but the whole point of them. Tools that inform and provide insight, deployed to make decisions, used responsibly. Index of key concepts. Holdout set, the sample of data reserved and used in fitting or even in model selection to estimate how the final model will perform on genuinely new records, the unbiased ground against which overfitting is detected. The book insistently prefers this term over validation and test, reserving validation for model tuning. Overfitting, fitting the training sample so closely that the model captures its random peculiarities, the noise, rather than its structure, the cost side of the bias variance trade-off that motivates data partitioning, cross-validation, pruning, and regularization throughout. Data partitioning, dividing data into training, validation, and holdout sets so that models are built on one portion and honestly assessed on another. In time series, the partition is a chronological trim rather than a random split to avoid punching holes in the series. Cross-validation, the extension of partitioning that fits a model k times with each fold serving once as validation, combining the predictions to stabilize the estimate of performance. Essential for choosing parameters like k in nearest neighbors or a tree's depth without touching the holdout. Propensity, the probability that a record belongs to a class of interest estimated by classifiers and converted into a classification by comparing it to a cutoff. Propensities also support ranking and lift analysis when scarcity makes acting on the top records the real goal. Cutoff value, the threshold on a propensity that converts probabilities into class assignments. The default 0.5 can be lowered to catch a rare, valuable class of interest at the cost of over-identifying it, or adjusted to reflect asymmetric misclassification costs. Confusion matrix, the table of predicted against actual classes from which overall accuracy, sensitivity, recall, specificity, precision, and the false positive/negative rates are all derived, and whose per-group breakdown is where discrimination, such as compasses, hides. ROC curve and AUC, the plot of sensitivity against 1 minus specificity across cutoffs, with the area under the curve summarizing discrimination from 1, perfect, to 0.5, random. A useful comparison tool, though the authors warn against AUC as a single selection metric. Lift, the ratio of a model's gains, responders captured or value accumulated, to what random selection would achieve, displayed as cumulative gains and decile-wise lift charts, the central measure for direct marketing and other ranking applications. Statistical Mahalanobis distance, a distance weighted by the covariance matrix so that variables spread and correlations are accounted for, in contrast to scale and structure-blind Euclidean distance, foundational to discriminate analysis and cluster analysis. Maximum likelihood, the estimation principle, used by logistic regression, that finds the parameters maximizing the chance of obtaining the observed data, requiring iteration where least squares is linear and closed form. Recursive partitioning, the tree construction mechanism that repeatedly splits the predictor space at the points reducing impurity most, producing the transparent if-then rules that give classification and regression trees their interpretability. Impurity, Gini, and entropy, the measures of class heterogeneity within a rectangle that tree algorithms minimize at each split. Both range from 0, 1 class, to their maximum at equal class proportions. Bagging and boosting, ensemble strategies, Bagging averages models fit to bootstrap samples, resisting overfitting, as in random forests, while boosting sequentially reweights the record's previous models misclassified, sharpening performance on a rare class of interest. Backpropagation, the neural network learning algorithm that distributes each output error back through the hidden layers, updating weights by an amount controlled by the learning rate, case by case or in batches, for sweeps until convergence or early stopping. Attention! The mechanism by which large language models assign each token a weight reflecting every other token's relevance, distant or near, and revise embeddings accordingly, making generation possible and demanding the parallel computation of GPUs. Uplift. The difference between a record's outcome propensity under treatment and under no treatment, estimated by scoring a model with the treatment variable set each way. The basis for targeting persuasion where resources are limited and some individuals would act anyway, or even in reverse. Market basket analysis. The association rules study of what is bought together, expressed through support, frequency, confidence, conditional probability, and lift, beat independence, powering placements, bundles, and frequently bought together recommendations. Collaborative filtering. Generating personalized recommendations from the user item matrix by finding similar users, user-based, or similar items, item-based, or by dimensionality reduction, with a cold start limitation for new users and items. Term document matrix and TF-IDF. The table of terms by documents that turns unstructured text into analyzable data, with a TF-IDF weighting rewarding terms that are frequent in a document, yet rare corpus-wide. Dimension reduction to concepts via latent semantic indexing makes the matrix tractable. Time series components, level, trend, seasonality, and noise, identifying them and their global or local character from the time plot decide between regression-based and data-driven forecasting. And the naive forecast is the benchmark every method must beat. Naive and seasonal naive forecast. The most recent value or most recent similar season projected forward, surprisingly hard to beat, and the essential yardstick for any forecasting model. Responsible data science, RDS, the framework of justification, assembly, preparation, modeling, and auditing guided by non-maleficence, fairness, transparency, accountability, and privacy, aimed at catching unintentional harm like the bias that overall accuracy metrics conceal. Reading comprehension questions. Why is the holdout set essential? And what specific bias does evaluating a model on the same data that trained it introduce? Scaffold. In what ways do training, validation, and holdout sets differ in their roles? And why does choosing a model on validation data still make its validation performance optimistic? Mechanism. Explain how the phrase, fitting the noise, not just the signal, relates to overfitting, and why a lower degree function can predict better than a higher degree one even when the higher degree is known to be correct. Mechanism. When classes are rare and misclassification costs are asymmetric, why might the highest accuracy classifier be worthless? And how do propensities, cutoffs, and lift charts recover the value? Critical thinking. How do the Euclidean, statistical, Mahalanobis, Manhattan, and correlation-based distances each compensate for a different flaw? And what does the choice of distance imply about the nature of the clusters you expect? Mechanism. Compare bagging and boosting. What error each is correcting? Which one typically improves the rare class? And why might each still overfit if its parameters are tuned on the data used to evaluate it? Mechanism. In logistic regression, why are coefficients interpreted in terms of odds rather than probabilities? And what does the statement, the change in probability is not a constant, imply about which quantities generalizes? Mechanism. The compass algorithm has similar overall and per group OROC, yet is criticized as biased. What measure exposes the bias? And why does a single overall accuracy metric obscure it? Critical thinking. What does it mean for a time series to be a random walk? How would you test for one? And what are the forecasting implications? Mechanism. Why is a naive or seasonal naive forecast the baseline every forecasting method must be compared against? And where would relying on it go wrong? Critical thinking. Explain the explore-exploit tension in multi-armed bandits. and why committing fully to the current best treatment can be the wrong long-run strategy. Critical thinking. If a system is fair, transparent, accountable, and private yet still harms, is it responsible? What does non-maleficence require that the other four principles do not? Critical thinking.